All right, okay, guys, so what I'm going to do now is I'm going to mute everybody out.
Welcome to APEC. We're starting up shortly.
Okay, so everybody is muted now. And so I'm going to read the introduction, and then I'm going to hand it over to Gabriel and Sergio. There may be a couple of bumps because I got people coming in left and right. But okay, so starting in 3, 2, 1. Welcome to APEC. It's July 31st, and I'm your moderator, Tim Ventura. First, I'd like to thank everyone for joining us on this call, along with everyone watching us on YouTube. In today's session, Gabriel Granziera and Sergio Zanotti will be discussing the field self-interaction electromagnetic thruster. Stephen Lutz will be providing observations on superconductive gravity modification experiments from working with Podkletnov, Modanese, and Poher. And Ken Griggs will be discussing Phoenix theory. After that, we'll catch up with the latest research from Falcon Space and Associates, and we'll be wrapping up the event with open discussion and ad hoc presentations. So a couple of quick reminders. You can view conference replays, details, and speaker info on our website at altpropulsion.com. Please save your questions for the Q&A session after each presentation. You can go ahead and type those questions in a chat at any time. We'll go through them after each presenter finishes. And of course, you can always raise your hand during the Q&A session as well. So let me get started now by introducing our first guests. Gabriel Granziera and Sergio Zanotti are with the ASPS in Italy, and they're joining us to discuss their team's experimental research and testing of the PNN, which is a non-Newtonian thruster that emits electromagnetic fields which interact to generate a force. So let's welcome them both to today's event, and now I will hand it over to them to get started. Oops, and okay.
Sergio, launch the PowerPoint. Share it.
There we go. Wonderful. Yeah. So take it away, gentlemen.
Okay. Okay. Hi, everybody. Hi, everybody. I'm Gabriel Granziera from Genoa. I'm an ASPS member. As ASPS means Association for Space Propulsion Developed. I apologize, first of all, for my rude English, but I'll do my best. Me and Sergio are here to introduce you to PNN. That means not Newtonian propulsion. ASPS was founded by Dr. Emilio Lauretti, a physicist, and other people in 1979. Emilio and the association have the aim to overcome rocketry. Since his youth, he understood that the classical mass ejection spacecraft would never take humans to Mars, nor allow to create a permanent base camp on the moon. Just think about Apollo mission. All rockets come back to Earth with less than 1% of the mass they lift off with. The 99% was lost during the space travel. Here's the key points. Humans gonna be space cowboys only with propellantless spaceship thrusting, only overcoming the fatal Newton's law. Astronauts can bring with them all the needed tons and tons of equipments. The first researches were focusing on mechanical thrusting. It happens during the 80s. In the photos, you can see the model SC23. The first idea was to create a delay between an action force and its reaction force in an enclosed system. During this delay, a movement in space should be observed. Unfortunately, Emilio realized that the mechanical system not complied with the superposition principle, so it was not useful as functional thruster. After the mechanical approach, Emilio changed his mind and switched to electrodynamic. All experiments were performed in his private lab. In 1998, the first prototype was built. In the early 2000s, public tests were performed around Italy. The Italian army was involved too, but no financial support provided, especially because the know-how of PNN wasn't public until 31 October 2020. Another issue was that the trust was too little to be believed as real. We are talking about milligrams, less than 1 grams. This device is called F432, and the shown technical details are just about it. By experimenting over and over again,
can I take it from here, Gabriel?
300 grams, more or less. But this device appears to generate a thrust. It shouldn't exist by the classical law of dynamics, including the momentum. The prototype emits electromagnetic fields which self-interact to generate a force. The thruster can work as long as the energy source is turned on. In my opinion, tiny nuclear reactors would be the clear choice in an ideal PNN spacecraft. As long as the electrical generators feed the thruster, the spaceship will constantly accelerate, theoretically, only theoretically, up to the speed of light. What makes PNN possible? Which physics PNN is based on? The Lorentz forces. Every physicist knows that these forces violate the third law of Newton. They are very, very little, but they can be augmented up to a measurable and exploitable thrust. Its working principle is based on the idea that Lorentz forces exist in open circuits too. The final result is a neat thrust which can push a spaceship without expelling reaction mass. At this moment, the latest version is equal or higher to IELTS engines. The net thrust comes from the vectorial sum of the Lorentz forces, which are present and normal in the arms of the V-shaped dipole that you'll see soon on the screen. F432 is basically a trouble, the overheating. The materials used in F432 are not exactly designed for it. Actually, nothing almost does. The device can properly work for 19 seconds maximum. After this time, it starts to smoke and then working anymore, and not working anymore after this. But that time is enough to prove what Emilio said. After the engine is turned off, it doesn't immediately get to rest, but the device keeps pushing and constantly decreasing back to the starting position. The reaction forces appear to not be present and the inertia changed. This is a new phenomenon that we want to share with you. Sergio, come on.
Okay, thank you, Gabriel, for your introduction. And now I'm going to introduce our audience to PNN thruster and its working principle. I have prepared this slide. Okay, here you can see in figure 1, I hope it's clear enough for everyone, and it's not too small. You can see a PNN thruster. Basically, it is a dipole, like the antenna used for radio application, and but the core or the phenomenon of PNN is focused in the near field area. The dipole is fed through a coaxial cable, as you can see here, the cable CX, and the input signal is a 432 megahertz sine wave at 250 watts of power. The length of the arms must be such that the dipole is in resonance with the frequency. So in this case, this is the F42 thrust scheme. In this case, the length of the arms is about 16 centimeters. The angle of the vertex, as this angle here, is 28 degrees. In figure 2 and figure 3, you can see what happens when the dipole is powered. We have in figure 2 the situation with the positive hemiperiod of the sine wave. And in this hemiperiod, we have a current in arm A flowing toward the vertex in this direction, and the current IB flowing toward the vertex in this direction in arm B. In the negative hemiperiod of the sine wave, the currents switch versa. So we have current IA going toward the vertex and current IP going outward the vertex. In both cases, the circulation of electrons inside the arm of the dipole generates electromagnetic waves, which will interact with the opposite arm. So the waves emitted by arm A will interact with the current flowing in arm B, and vice versa, the EM waves emitted by arm B will interact with the current in arm A. According to the Lorentz law, the result is the formation of two Lorentz forces in both arms, which are perpendicular to the arm themselves. If we apply the parallelogram law to those two forces, the resultant is a force Fr that you can see here, and this force is the actual thrust that the device can provide. As you can see, in both periods, the hemiperiods of the sine wave, the verse of the forces doesn't change, so the thrust is constant. And we can say that if we imagine the dipole as the head of an arrow, the dipole is pointing at the direction of the thrust. This is the constructive scheme of the dipole. We can see here the coaxial cable CX, which splits in two arms that are made with Lutz wires. And surrounding the arms, there are ferrites. Those ferrites are used to, let me say, capture and increase the electromagnetic waves all around the arms of the dipole. Here you can see the front view of the arms, and you can see the arrangement of the ferrites. This is the practical realization of our thruster. You can see here in the middle the dipole kept in position by the frame here. Here there is the coaxial cable which splits in the two arms of the dipole. Around here you can see those black foils are the ferrites used to amplify the EM, to capture the EM waves. And those white foils are silicon foils that are used to slow down the overheating process, because this device is subjected to quite a lot of overheating, and without protection, it burns or melts in a little time. Around the frame of the thruster, you can notice those gray pipes, and those are used to discharge hot air during the tests when the box is closed. Because as you can see here in the background, basically this thruster has two doors that can be opened like, let me say, the Seagull doors of a sports car. And when the box is closed, those pipes are used to expel hot air and avoid a hot air balloon effect that might distort the test results on the scale. Those are more in detail the zone nearby the vertex of the dipole. And this is the detail of the Lutz wire used in the to make the arms of the dipole. Laureati chosen this kind of wire to reduce the skin effect during its functioning. Now I'm going to show you the phenomenological model immediately used to test the working principle. You can see here in the left picture the equipment used to power on the device. So we have the oscilloscope to check the signal. We have the preamplifier here, this one, and then an amplifier here. Together, they provide the 432 megahertz sine wave at 600 watt. Sorry, I forgot to mention, at the start of the test, we use 2,250 watts. Then the power is slowly increased up to 600 watts. All the power line from the prototype to the power supply, it is a coaxial cable. The preamplifier is a model made by ICOM. The model is the IC910H, and it has 3 output options: 144 megahertz, a range between 430 and 440 megahertz, or 1.2 gigahertz. F42 works in the 430 and 435 band because the amplifier can only output in that range. The amplifier is made by Italab, and the model is Archimede, and the power output is up to 600 watts. At the moment, it is out of production, but I think modern alternatives can be found quite easily. In the right picture here, you can see the shielding of the equipment, in this case of the preamplifier, because as you can imagine, a 400 megahertz sine wave at 600 watts make this thruster also a microwave emitter. So for safety reason, observers and equipment must be kept at safety distance. Here, this is the ballistic pendulum used to test the prototype. You can see it is attached to by its coaxial cable. And this part here is a second experiment that I'm going to show you later. Now I'm going to show you more in detail this part. Okay, here you can see that at the bottom of the thruster, it is attached to this wood rod. At the end of this rod, it's not very visible, but there is another metal rod here, which ends at the height of this box. Inside this box, there is a laser projector, which is used to cast a shadow of the rod on the wall, as you can see here in this picture. This is used to actually see the movement of the prototype for 2 reasons. The first one is that the thrust is in the order of milligrams, so it is too small to be noticed at naked eye. And the second reason is that, as I said before, it is very dangerous to stay too close to the prototype while it's operational. So we expect, once the prototype has been turned on, we expect a thrust in this direction because the dipole is pointing in this direction. And therefore, we expect that the shadow on the wall will move toward the right accordingly to the direction of the thrust. When the prototype is powered up for about 30 seconds to 1 minute, Then it's turned off to avoid the overheating that can burn down the prototype. And when the power is turned off, Lauretti noticed a peculiar phenomenon of this transfer. That is, it doesn't immediately go back to rest. The shadow that you can see in the reference index here doesn't go immediately to rest, but it stays tilted, like if the prototype is still producing thrust. Lauretti called this phenomenon virtual mechanical energy. It is like the prototype has to first disperse the thrust, the accumulated thrust, before it can go back to rest. This is the second test that can be made on the ballistic pendulum. We are looking at this dipole here. This is the naked dipole pointed upward. And this is the constructive scheme. So we have the coaxial cable CX here and one arm of the dipole here locked in position by those locks ST. And then we have one of the two arms, in this case this one, that is free to move. View the picture. Okay, this is the practical realization of the scheme. You can see here, I hope you can see here the boot lock that keep this arm in position. This other arm has one part of the protection removed, so it is more flexible. And here it is attached again the rod that is used to
and there's
project
a
the
beautiful
shadow.
door at Home Depot
Sorry?
that has like a frosted window right here.
Sorry, well, what's the problem? Sorry. I don't. Okay, so I go back. Where was I? Ah, yes, here it is attached again the rod that will be which shadow will be casted on the wall to check the movement. But this time we want to check the presence of a Lorentz force on the arm of the dipole. This will be evident because with this index reference, we expect that the Lorentz force that is present on this arm will push the arm toward the right. So here too, we will expect the movement of the shadow on the laser here. We expect the same behavior as here. The power, the test procedure is identical. The dipole is powered for a period between 30 seconds and 1 minute. And here too, it is possible to observe this phenomenon of thrust, let me say, thrust dissipation. That is, the arm will not return immediately to rest once the power has been turned off. This part concludes the description of the experiments, and I have grouped here some big issues of this technology at the state of the art of these technologies. One is that further experiments must be conducted to exclude the thermal deformation or other misleading problems. For the moment, however, we have conducted the following tests. One was to put the prototype on a scale and make it generate thrust upward and then downward. That is, the dipole vertex is oriented upward in this direction, and then downward. The test detected respectively a weight reduction when the thrust is upward and a weight increase on the scale when the thrust is downward. We think this could exclude mistaking for thrust a thermal deformation of the coaxial cable when the prototype is on the ballistic pendulum. That is, if this is, let me say, this is the prototype, and there is a thermal deformation of the coaxial cable, there could be a tilting of the prototype, but it might not be due to the production of thrust, but because there is the illusion of thrust due to the deformation. But this kind of test should exclude this problem. Another test that has been made was to punch holes in the coverage box to avoid that the air trapped inside is heated by the dipole and triggering a blimp effect, sorry, a hot air balloon effect. The gray pipes I had shown you before are the air exhaust to avoid this problem. And this eventuality seems it can be ruled out since the prototype still thrusts downward and the weight, sorry, when the prototype thrusts downward, the weight on the scale still increases. Another test was to enclose the prototype in a plastic bag to rule out any movement by hot air currents, and it has been observed that the device behavior doesn't change. An important point is that this setup is, as everyone can see, is made with do-it-yourself materials, so like wood. There is the need to rebuild the system with more suitable materials, starting from the ballistic pendulum and up to the ferrites that are the general ones that are sold in stores without specification. There is also the need for specific testing instruments. For example, a field detector with a sensor small enough to be fitted between the arms of the dipoles as close as possible to the vertex. The last two problems are connected with the do-it-yourself problem. That is, a lot of the input power is lost with irradiation and overheating, and that the prototype can operate for about 1 minute. Then it must be turned off to let it cool down before we can operate it again. If we move to now we can imagine this is a way to demonstrate the presence, the existence of Lorentz forces in the PNM dipoles. Let's imagine that instead of having a 28-degree angle here at the vertex, the angle is 1 degree. At this point, the dipole is highly mismatched and it is unsuitable to function as an antenna. However, the Lorentz forces are still present and they will cause the two arms to repel each other. As force A and force B will be present, they will tend to repel the two arms and therefore to increase the angle of the dipole. And this is the basis behind this experiment. And this is a very important point for us. We are suggesting, we are encouraging people to replicate this experiment because at the moment we haven't got any external validation of this of PNN. So we are encouraging people to replicate this experiment. And I'd like to close this part of the presentation with a silly picture. It's famous, the motto, don't try this at home, but instead we say, please do try this at home. With, however, the disclaimer that this invitation is aimed for people who have the skill, the knowledge, and the equipment to replicate safely this experiment. Because I remind you, this is basically an open air microwave oven. And so it might be dangerous if one doesn't know what is doing. After the development of our F432 thruster, Lauretti worked on a new class of PNN thruster, and he invented the subitum class thruster. Now, subitum comes from Latin, and it means literally right now. It's because subitum is not what PNN could be with appropriate industrial solution and technological research, but it is the best the PNN can be with the current materials and resources. So the first subitum class thruster is sub 321, and it is actually capable of reaching 15 grams of thrust, 15, and it is already competitive with, it is already overtaking ion propulsion. And this new thruster is made with new material, for example, steel, aluminum, copper, fiberglass, new ferrites, and other material that can slow down the overheating process. And it is also present a partial thermal dissipation system, and altogether they allow longer ignition times. You can see here omitted for no hour retention. You can see this part. This is because subitum class is actually under validation for patent, under patent validation. And we are looking for, once the patent has been granted, we are looking for collaboration or funding to improve and to industrially develop PNN and to commercialize it as an alternative to ion thruster. Okay. Emilio Lauretti calculated that with this new thruster, if it could thrust for infinite time, it will take about 2 hours and 33 minutes to achieve the takeoff. This is because it seems that at the same power, which is 250 watts with the Sub 321, the thrust keeps increasing, accordingly, apparently in contrast with the second law of dynamics. Sub 321 has been tested on a new kind of arm scale. And on this scale, Emilio Lauretti obtained this graph. This is an important graph for us because it shows the potentialities of subitum class. This is, as you can see, is not a recent diagram, graphs, because it's from March 2021. And at that moment, the thrust was almost 2.5 grams. This circle here represents the range of thrust that the F432 thruster, the thruster I had shown you on the ballistic pendulum, could achieve. As you can see, the 321 can keep thrusting way more than, we are not anymore in the milligram range of thrust, but we are in gram range of thrust. And here you can notice the thrust dissipation phenomenon. Here, Lauretti powered off the system, and as one would expect, so we would expect a vertical drop of thrust, so an immediate drop to zero of the thrust. But instead, it slowly go back to zero. Here, he powered on again the thruster, and we can see the thruster. It started thrusting again. I can show you some videos, some footage of the first test of F432. I have muted the audio because it's noisy and it's in Italian, so it's not very useful here. But here you can see the shadow of the rod that is used to detect the movement. In this part is still on. We are waiting for the rod to stabilize. I'm going to, okay, here it started to immediately powered on the thruster. So it's a bit, it's not very stable, the video. Okay, and as you can see, it slowly moves toward the right, as expected. So now the prototype has been turned off, but instead of going back immediately to rest, we can see it remains tilted. That is, the shadow is still not in the middle of the laser. Now here it has been powered again, and so this is the in the subtitle you can see the Lauretti's consideration of this phenomenon. He admits he doesn't know actually what is happening. This is a supposition, and because we haven't got the testing instruments to investigate further this phenomenon. Okay, this concludes my presentation. I hope I have been clear enough with the description of the working principle and the experiment of BNN. I think we can. I think I can stop here. If you have got questions, I will try to answer them with the help of Gabriel and Emilio if he's connected. I don't know. I haven't seen.
Emilio is listening now.
Okay.
Wonderful. Well, let me do this then. Since you're concluding your presentation, I want to put this on. Let me see. Why don't I here? I'm going to stop your screen share, and okay. So now let me put this on gallery mode, and everyone, please give a giant applause for Sergio and Gabriel.
Thank you
Thank
very
you
much.
both. And let me apologize for the interruption. I had it unmuted
don't worry.
because Gabriel dropped
Apologize
out.
us for our bad English.
Well, when Gabriel left and he came back in, I wanted to let him unmute himself, and so that was why I had it disabled. But it backfired on me. So in terms of questions, actually, I've been going through chat. Let me ask David Mathis. David had a bunch of questions. David, do you want to go?
Yeah, sure. I'll go. I got to find my list of questions.
Yeah, you had several, and that was why that was why I wanted to start with you.
I didn't get to see a picture. I came in about 5 minutes late, so I didn't see all the test instruments set up. It looked to me like you had made great accomplishment with whatever you had. And I presume you're doing this at home?
Yes, that was Emilio Laureti's home.
Okay.
He actually had a lab, but there has been an earthquake at, maybe you have heard the Amatrice earthquake in the middle of Italy. And this earthquake destroyed his lab.
Oh, okay.
So he has to move all the instruments to his home.
From just the experiment, great setup. It's great, and it actually, the protection, I think you need a little more protection, maybe a radiation badge, who knows? Okay.
Yeah, thank you.
Have you looked at the sources of weight reduction? Is it a single effect, or do you think it might be multiple effects?
This is a question for Emilio. I don't remember if I said that, but I am not a physicist, so I can't reply to many questions.
That's fine.
Oh, if I could jump in really quick, I should mention. So Emilio Lauretti is the primary. I believe he's the primary inventor, and he's really been in charge of this project. English is not a native language for him, so he's actually with us. And if he feels comfortable speaking, I would love to have him speak and answer questions. But Sergio and Gabriel they communicate much more fluently in English, so they did the presentation.
Okay. What percentage weight loss has been achieved?
Sorry, this is not weight loss. This is a weight increase. This is the direct measurement of thrust on a scale. So it's like the prototype was pushing on the scale, or trying to lift off from the scale.
Okay.
So this is not anti-gravity. Let's say.
So then what is the thrust to mass ratio?
Nice question. I try to ask to Emilio if I can find him around the participant. No, he's not here. Okay, yeah. I'm asking.
Okay, that might take a little bit. Another question that I have is this a time-dependent operation? To me, it appears to be, it's not an on-off operation. There's some sort of charging going on. You mentioned that if you turn it on too quickly, that it shorts. Is that a? Can you explain what you mean by shorting?
The basic concept is that the thrust increase over time.
Okay, so it's a time-dependent operation.
Mhm.
All right. Do you know what that?
The more the times the PNN is fitted, the more thrust it has.
Okay.
The thrust depends on the time.
Have you
More time, more thrust.
Have you tried to do curve fitting for the charging or discharging, or the thrust increase or the thrust decrease once you turn the switch off?
Can you
Is it a linear increase, or is it a parabolic increase, or is it?
I don't know if it's the correct curve, but it's not. It seems to not be linear.
Okay.
Okay, that's fair enough.
It's not properly linear.
All right, gentlemen, thank you. Tim?
One thing I'd like to add is that I forgot to mention before is that some people have made an observation about PNN, and they have said it works by photon recoil. Emilio asked us to underline that this is not the case. For Lauretti, it works only through the interaction of Lorentz forces.
Okay, so, all right. So have you measured the magnetic portion of the Lorentz force?
Those are questions for Emilio, but unfortunately.
Do you have a trimeter, or do you have a magnetometer in your instrumentation?
I know he has a field detector, but we haven't got. There is the problem that they're too big to be placed nearby the dipole, and the measurements we require are nearby the vertex of the dipole, and so it is difficult to measure that part of the dipole.
Okay. All right, Tim. Gentlemen, thank you.
You.
If you have question, I think you can directly write those to Emilio, either by chat or I show you again the email. I share you the email address. Just a second.
I just write the email address of Emilio on the chat.
Okay.
Hello, Sergio.
Yes.
Hi, can you hear me?
Yes, I can.
Hi, my name is Eric Hermanson. I had just a couple quick questions. I missed the first 10 or 15 minutes, so I apologize if I'm re-asking. And so I'm looking at the force vectors, and seems like if you would make it a diamond shape and have a back end on it, wouldn't that push? Wouldn't the back thrusters, if you reverse the phase in the back two thrusters, wouldn't they all result in a forward push?
You mean changing? You'd like to change the shape of the thruster, am I right? I have understood right.
Yes, make it a. What would happen if you made it a diamond shape? Would the back the back thrust, the back forces would cancel, But if you reverse the current, would the in the back part of the diamond, would that add to the front thrust? You see what I'm saying? Instead of having it a triangle,
Okay,
it would
yes.
be,
You
what
mean
if you
to
made
make
it a diamond shape?
like those in play cards, the symbol in play cards, sorry, the seed in play cards? You mean that kind of shape?
A diamond, a diamond, yeah.
Yeah, the card
Okay.
chip. Yeah.
Okay. I don't know if Emilio ever tested this kind of shape. However, he said once that there are, we found 11 possible shape for this thruster. Another shape that has been experimented is an semicircle, about 1/6 circumference.
Okay.
And-
I'm just talking about the back part of the diamond where you rotate the force vectors so they're also pointing in the same direction. I don't know. I don't know if that would work. Have you tried running this underwater?
No, this has never been tried.
Because it would definitely cool the mechanism. And I don't know how the fields the fields are would create currents in the water and things like that. But I don't know.
Yes,
You might want to try it.
or oil, for example. This is we are working on some kind of cooling system. For the moment, it's only passive cooling. However, we have taken into consideration some other cooling system, water or oil, that they might work. But at the moment, Lauretti wanted to keep the thruster as clear as possible without anything on it, paradoxically to avoid other things that might break.
Now, if I could jump in really quick, and Eric, thank you. So I spotlighted Emilio's video. Hopefully you can all see that. He's demonstrating a device. And Sergio, if you'd like, feel free to describe this. It looks like this is SV432. So
It's, yes, F432.
F432, I'm sorry.
Don't worry. Okay, yes, here you are looking at the thruster. This is the frame that keeps keep in shape. Move it. Give the shape to the nipple and keeps it in shape. This is another thruster. This is an improvement of that thruster. This was made by Emilio after some criticism about the testing procedure, because some technicians say that the external power might lead to measurement errors. So he created this new thruster. This part is showing is the signal generator part, and behind this side, on the other side, there are the batteries. So in this thruster, it is a single piece all together with the batteries, and the whole structure is put on the ballistic pendulum for testing. Here you can see this is the signal generator. This is the amplifier part. And then this is the amplifier part. And above this, there is the attachment for the F432 thruster. So basically, this is an add-on to make it independent from external power sources. I think I can show you some picture.
Little card.
Little card, yes.
Boa failure. Pre-amplifier. Amplifier. Thermal dissipazione, dissipation. This.
Thermal dissipation, yes.
Wow. In this part, this is
This should be
remote control radiator.
yes,
Two
this thruster has
lithium batteries here. The prototype is in this part. A moment.
Video we can see it.
Aspetta, moment.
Oh, okay.
In this part, prototype, this. On to scale, bilancia.
Yes, scale.
This is a remote control on off. Not more. I have a problem.
Okay, meanwhile, I can show them a picture of little cart.
Little cart
I
on
share-
Oh, sure,
The-
sure.
the wall structure is about 3 kilograms.
the
3
total
kilograms.
weight of the prototype. Of the structure.
This part and prototype. But lithium battery, about a minute finish, stop, not
Yeah,
are able to have long duration.
and yes, they deplete
Battery has
quite
a
fast.
short lasting batteries.
And about 60 seconds, if I'm not wrong.
Oh, so he's saying it's self-contained.
The problem to show all. Moment. These are ferrites.
Ferrite.
All right.
This is another ferrite of megahertz. This. They're in the prototype. These are about 15 centimeter. You can see.
Yes, so about 15 centimeter, I believe.
You can see this. This is a piece of Lutz wire. 600 wires. 600. To have maximum current. Current is fundamental for every
or solid.
course. You must soldare.
Solder. You have to solder.
And then cut ferrites you need.
And there is a need to adapt all the materials to the to create the dipole. The ferrites are not of the right length. They are not the right.
Non mi vede più. Scusate.
Well, Emilio, thank you for sharing it. Thank you for sharing that with us.
Good evening to all.
Is it stranded or solid wire
Oh,
in
okay.
the vertex?
There we go.
Can you repeat, please?
Is the wire, okay, you have these two wires coming like this. Okay, these two wires, are they stranded or solid?
What is this?
It looks like that's stranded. I
Looks
believe
like
you
a
said it was
stranded wire.
600 strands.
600 wires.
Okay,
Thin
600 strands.
110 millimeters.
Okay, very good. That's what's my question. Okay, and the frequency, what was the frequency? 432 megahertz, correct?
Yes, yes, please.
Okay,
Not never magnetism, never. UHF with UHF
UHF.
megahertz.
UHF current.
Because magnetism, never.
so the ferrite,
Never.
is that like a shield or a choke for the RF somehow? You know, like when you buy a choke for you know, the little ferrite coils that you buy. It's a little circle ring, and you put it in the wire, and it takes out the RF signal. It takes out the RF noise when you put this around like a wire. You know what I'm talking about? It's called an RF choke.
On my opinion, one will be convinced if repeat the experiment. Only repeat the experiment with patience. You can say all, but you need to try to repeat the experiment, because we have now another type of physics. If we third principle of Newton is violated, change the second principle. Is not the same, can't be the same mathematically. So another physics, you must study another physics, and many experiments.
Well, I think we all want to do that.
Do it. I can see more. I can see more.
With you.
Yeah. Well,
You must
so
do.
let me
change inertia principle. The same.
So I got this book I wanted to share, which I think has a lot to do with what we're talking about here. It's about metamaterials, and that figure you're showing me. And so my question was, it describes what's called a thin wire epsilon negative metamaterial. And this is what it has written. It says,
Zanotti, digli che non capisco quello che dice. Zanotti, digli che non capisco.
Sorry, Michael, he doesn't understand.
Yeah.
What we're trying to say.
Michael, that might be better. That might be better to email, actually.
Yes.
Okay, certainly.
Would you
post your email in the chat, please?
Yes, I recall that.
Okay, very good. Thank you.
Yes.
It's just a comment. I'm intrigued by what your results are. I'm just trying to figure out why. It's just natural. We like to do that. So
yeah. Well, thank you, Michael. So let me go to Harold Tavares, who's been patiently waiting. Harold, would you like to go, sir?
Yes, I have a question. Is why the 28-degree angle? Have you done other tests at different angles, and why that one is the one you chose to produce the Lorentz force that created the thrust?
The basis is to violate third principle. Third, the first this. Violare il terzo principio. Dopo, mantenere la spinta nel tempo. Perché solo se uno mantiene la spinta nel tempo esce fuori un cambiamento del secondo principio.
Translate, Sergio.
Yes, no,
Second principle. It is PNN is a artificial procedure. Is not natural. Is not natural. Don't exist in nature. So as a radio don't exist, and a television don't exist. So don't fix PNN naturally.
Okay, well,
You need to enter another type.
Emilio, hold on for a moment, because Sergio is trying to
Excuse me, but I
Fai
don't
parlare
have.
Sergio, Emilio.
he's trying to translate for us, sir.
Yes, no, sorry, I talk a moment in Italian to Emilio. Emilio Harold stava chiedendo perché l'angolo di 28 gradi, se ci sono altri angoli che si possono usare.
Tutti in teoria sono possibili tutti, dipende from impedance. Impedance, matching impedance is the very important.
Okay,
and
Harold,
I see trust when at 90 gradi, 90 degree, I see. So I see when angle is about 7 degree. So the very important problem is that mismatch of the line that destroy amplifier. So you need direct energy, reflected energy elsewhere. You must power effect must go elsewhere. If so is not so, amplifier is destroyed. Hanno capito, Zanotti?
I don't know. So the question, Harold, was to answer your question, Harold, the angle can be anything.
28 degrees.
Any degrees, yes. There are different shapes that can be experimented with the PNN. So the dipole is the basic one, but there are many.
Yeah, my final question is radiation taken into account as producing thrust of the part of the Lorentz forces?
Radiation?
The radiation produced, the V-shape produces radiation. What is doing the Lorentz thrust? Is the radiation produce part of the thrust or zero?
No, the complete thrust, all the thrust is achieved with Lorentz forces.
100% Lorentz force, no radiation.
I think 100%, yes.
Where does the reaction go?
This is a good question. Yes, it appears to not be present. This is what we have observed so far.
Okay, because the reason I asked that question, September 6, 1952, in Nature, there's an article that is electromagnetic momentum and Newton's third law, in which they said that when you are producing reaction thrust, if you take into account the radiation produced, for example, during the Lorentz forces, then you can say, that energy conservation momentum is conserved because part of the thrust being produced by radiation. And that's why I'm asking, since machine is producing radiation, is that radiation producing the thrust or part of the thrust, even though the Lorentz force is the one getting the credit for all the thrust?
I forward this question to Emilio, but I think 100% trust. Just a second. Emilio.
Cosa?
Sì, chiedeva Harold se tutta la spinta è prodotta da Lorentz oppure anche dalla radiazione del dipolo.
Che cosa hai detto?
Tutta la spinta è prodotta dal dipolo, cioè dalle forze di Lorentz, o c'è anche qualcos'altro?
Solo forze è la risultante di due forze di Lorentz sui bracci.
Ok, so Harold,
la regola del parallelogramma rule.
Okay,
So,
it's only
it
the
is,
Lorentz forces, Harold.
So forces. And then resulting. Digli che è violata pure i collider la quantità di modulo. Momentum si collider in collider.
Mm-hmm.
Thank you.
Zanotti.
Okay, and thank you as well, Harold. And Sergio, I should ask, are you doing okay? I'm worried that we might be exhausting you because we have so much back and forth in language translation.
Oh, well, for the moment I can manage it.
Okay.
Thank you.
I just wanted, I wanted to check. I wanted to check because I know that you're right in the middle of everything, and I appreciate your efforts.
Thank you.
Let me see. Who should we go to for questions? Who would like to go next? Actually, there's a ton of stuff in chat. Maybe I should bring Remy. You had several questions and comments. Would you like to come on?
First of all, just thank you very much.
Oh, sure. Remy, could I get you to enable your camera, if that's okay?
Oh, you don't want to see me.
Oh, okay.
I want to see him.
No. Right, seriously, thank you very much for the presentation. You've done some good work there, and I think there might be something there. What is saying that the usual disproof for Lorentz forces is you take it around a loop, and with an antenna is not really, how would you identify a loop unless it's a displacement current? So he's got two arms. They've got two arms of the antenna reacting against each other, and you get this resultant force. I think there might be something there. And the thing is, Harold was saying, how does momentum balance? You know, he's saying this Nature paper from '56, saying that it would be taken up by the radiation reaction. It's a very small force. It may be something that you can directly push against the 0 point, and that would explain the momentum balance. So I just keep an open mind. I mean, you guys, you carry on what you're doing. I mean, you're doing brilliantly, you know? So, I mean, on that basis, I mean, it's good to see people making the effort. And yeah, I think you might have something there. That's just my belief. Yep.
To read this part. Okay, in the magnetic interaction between two electric wires in which the current flows, there is a factor of 4 pi Greek for 10 to minus 7. This is the force, the actual Lorentz force in two parallel wires with direct current. This force is very negligible. We need to amplify this force, and the trick is to amplify this force through the ferrites and through this dipole, through the PNN thruster, so through the field interaction and the ferrites all around the wires.
Okay. Who would like to go next? Let me see. So we just went to Harold. We went to Remy. Let me see. Michael Boyd, did you have more questions, sir, or were you set for now?
I just wanted to say I posted in the chat a link to Amazon for the book that I told you about, and I also sent it to the email address that I was given. And just also wanted to thank Michael Himes. He's the one who turned me on to this book, and it's pretty good. So, and what I like about it is it does metamaterials from both what I would call dielectric planes, and then also transmission waves, and if you're doing experiments with RF, I'd recommend you get this book too, because it has some important information about harmonics, conjugate waves, that kind of stuff, which are, I think, important to understanding space-time modification. So in any case, thanks. That's all I just wanted to share that.
Okay, well, thank you.
But I think it's pertinent to what he's doing. I think that's what he's doing is described in there.
Oh yeah. And I'm sorry. I'm not trying to sound dismissive at all.
No, you don't.
Okay. So let me jump around here. Let me see. Did anyone else have questions?
Yes, hello again. One question. I want to ask him if he have used pulsating DC for that experiment to see if he produced any Lorentz forces and thrust instead of AC.
No, this works only with the AC. I can share you a video where a video explains the whole principle of PNN. So just wait a second, please. Okay, this one.
Excellent.
So this is the start for PNN thrust.
Simple explanation.
So in this case, with a continuous current, we have 3 Lorentz forces. And the trick with the PNN is to remove one side of the circuit. So now the forces are only 2. And by applying the parallelogram law, the resultant force is a forward thrust. Yes, this is the problem. The forces are very weak, let's say in network, let me say. I hope you could see the subtitles. I hope you understood.
Yes.
Thank you, Jeremy. You're welcome.
Thank you as well. I'm sorry.
Thank you.
I got distracted by email there for just a moment. I had people asking me questions via email. So, well, so I think that is it for right now. So why don't we do this then? I want to put this back on gallery mode. Everyone, please put your hands together once again for Sergio and Gabriel and Emilio as well. And gentlemen, thank you very, very much for joining us today. I sincerely appreciate it. And I know that the language barrier made things difficult, but I sincerely appreciate your.
Thank you very much. I'm glad you appreciate it.
Thank you for your time.
Thank you.
Thank you very much.
Thank you for the explanation.
Okay.
It would be better.
Mille grazie.
Prego.
So let me see, everyone. Let me mute everyone out. And so Stephen Lutz is next up. Stephen, we are a bit ahead of time. Oops. Let me see. I'll ask you to unmute though. Okay.
I'm unmuted.
Okay. So Steve, let me do an intro real quick. I mean, do you feel comfortable speaking now or?
Sure.
Okay. So everyone, please welcome Steve Lutz, who currently works in computer security and has past experience with corporate projects in physics and engineering on a variety of incredibly interesting topics. He also is involved in propulsion and works with several well-known theoreticians and experimentalists that get regular mentions in our event. So he's going to be talking today, at least in part, on some of his observations on superconductive gravity modification from working with Podkletnov, Modanese, and Poher. So welcome, sir, and feel free to go right ahead.
Thank you. My talk is going to be mostly non-technical, I would think, or medium technical. I appreciate the fact that Remy Cornwall, because he can backstop some of the things I think or speculate about. But I'll just go into I'm actually using this new iPad, and it follows you around if you notice. It's weird. Wherever I go, it just follows me. So I'll just give a little brief background how I got involved in this space. I started a company overseas that was researching novel methods of fabricating group 3,5 nitrides in the semiconductor space. So that would be your gallium nitride, your indium gallium nitride, etc., right? Which is a big thing in the space now. I mean, my house mostly is GaN lighting, and my iPhone charger is a GaN MOSFET, which is tiny and very powerful. So it's a great material system. Anyway, I got involved in the propulsion space simply by reading papers that Professor Modanese, Giovanni Modanese, had published, along with Eugene Podkletnov, a Russian-born scientist. And in those discussions, back and forth with them, I started having discussions mostly with Eugene about his experiments. And then through that, I think it was Giovanni introduced me to Dr. Claude Poher over at in France. Working with the two groups, I noticed a couple of things. One, obviously they're both working with the same material systems. This was YBCO superconductors, and both required liquid nitrogen cooling. We'll call it LN2 for now. One thing I noticed when talking with Evgeny, he was using very high pulses of electricity and getting these very dramatic effects. There was a beam that would, a force beam that he could measure. They did measure the speed of this thing using a couple of rubidium clocks. And let's see what was interesting about it. It was a mono disc of material. He described crystallinity to me being, I would say, high order polycrystalline, not quite monocrystalline, but decent quality. And he told me that he was getting a self-collimating beam out of it, which I thought was rather interesting, out of a single piece of material. So anyway, back over to Claude Poher, I started actually working with him because he had some interesting applications. What he did was he went to thin films. I'm going to call them low order polycrystalline. He was making himself, and he would stack them. I think when I was working with him, he was up to maybe 12 layers. All of this is published, so I'm not violating any non-disclosure agreements that I have with him. And he was getting, he got the voltage down, I think, to 1,000 volts, rather than Evgeny was using 1.5 million to, I think, up as high as 3 million volts at some point. And he was getting a similar effect, but it was not self-collimating, it was conical. It kind of fell off pretty quick. But he had measured the propulsion from it. It was quite high. He showed me a chart comparing different rocket motors, scramjets, ramjets, and so forth. You had this graph. And then as far as his measurements were concerned, it was way up above anything that we currently use in the rocket space or whatever. So very interesting. One of the things I was tasked with was to work on the cooling budget, the LN2 budget, to see if we had a side application we were working on, and there was a cooling budget involved. So I got in touch with some companies that build such equipment, back and forth, getting budgets. It turned out the budget was quite high. Cost of that cooling equipment is high, doable, but bulky and big. Nothing you could certainly fly around with. But this was a ground-based application we were working on. That led me to looking at raising the temperature of the superconductor. So I started looking into metamaterials, which looked very promising, that were offering potentially superconducting properties. And that was interesting as well. I think at that point, I reached out to a couple of different research teams that were working on it, and then I had to leave the project for other reasons, more in the information security space, which is where I normally reside. Half the time, the other half the time, I'm in the semiconductor space and material science. But anyway, one thing that he said, I asked him a question about these craft. You see them zipping around and whatever. We've seen the videos I think they've released. And I asked him about, I kind of felt foolish when I asked him, but I said, I used the Star Trek term inertial dampening or whatever. I was like, how do they get away with this? How does the craft survive it? And if there's any, say, occupants, for example, biologics, how would they survive it, with these G-forces that are happening? And he kind of said, well, I'll show you how it works. And he started doing some math. And then he pointed me to the quantum locking that Tel Aviv University had demonstrated. And he said, it's similar to that. It's related to that, but it's not the same thing. It doesn't involve magnets or whatever. So I kind of, that stuck in my head. I left the project, but I still kept thinking about, as an engineer, I kept thinking, how would you establish a field like that? And I built a craft in my mind. It's a shape, maybe it's a sphere. In this case, I did like a sort of a saucer or whatever. And I started looking at the material. I said, okay, let's say magically we have metamaterials that are room temperature superconductors. Great. Now, how would you? I already know the thruster part of it. That's pretty well. They're pretty far along with that. But I was like, how would you create this field and sustain it in the craft? And I thought about the Tel Aviv stuff, and I was like, well, okay. First thing I thought of was, took me back to the group 3,5 nitride research, right? So in 3,5 nitrides, you work with C-plane, which is normal. That's what I was working with because I was on a low budget. Then you can work with M-plane, which is like semi-orbital. And then if you got a real big budget like military, you would work with the P-plane, which is non-orbital planes. And I knew I had discussions with the chief scientist over at DARPA, the Defense Advanced, well, I think they call themselves ARPA now. But we were talking about these problems, and it became very clear that if you could grow the materials, it's a hexagonal structure, GaN or InGaN. It's similar to zinc oxide, if you're familiar. So if you grow it C-plane, it's kind of flat. If you grow it M-plane, it's at an angle. So you have these crystals growing, and they're rather delicate. If you heat them too much when you're growing them, they'll just kind of crumble. And then the hardest one was the P-plane, the non-orbital. But as you move from orbital to semi-orbital to non-orbital, you get amazing performance increases out of the material, right? So the brass ring in the nitride space is non-orbital. And you can Google it, and there's a lot of papers on it. But I started applying that thinking to this hypothetical metamaterial I had in my head. So I put it non-orbital on the shell of this craft. So the craft has a surface, and I've got this magic metamaterial that hasn't been invented yet, and it's in a non-orbital state. It's sitting there. So the next thing, I was reading some patents by a gentleman by the name of Levengood. Has anybody, I don't know if anybody's read any of his stuff. He, how did I find him? He was the guy that basically got involved with, there's a researcher, Linda Moulton Howe, and he was investigating these crop circle things. And through an audio recording, I think he was able to reverse engineer to some degree what was going on in those fields. And he built an apparatus. He patented it. Basically, what it did, it was like you had an anode or a cathode, and he would hit it with the DC voltage with a AC ripple superimposed on the DC, which I thought was very interesting. And what would happen was there would be like this self-organizing plasma cascade of ions. And in the middle of that, he would put a variety of different seeds and treat them at different, intensities, and then, measure the output. It was very interesting. The plants, depending on the plant, would grow either 15 to 25% faster, or you could tune it and it would grow at the same rate, but 15 or 25% bigger, more yield. You get more corn, you get more whatever. Anyway, I was thinking about that patent, and I was reading it, and I thought, what if we took that superconductor material and we hit it with that same type of energy, right? We hit it with DC to saturate it, and then superimposed AC on it, and maybe got it to resonate, right, in some way. And the thought I had in my mind was, what if you cranked up the AC portion so that you were in the gigahertz or even terahertz frequency range? And if you did that, would you create standing waves inside of this craft? Would that occur? Like you do with audio, you can do it all the time, standing waves. I used to be an audio engineer, and it was a big problem for us with standing waves. So anyway, I thought, what if you did that, and you could create this field that Dr. Poher was referring to, which was that related to that quantum locking? Would you get a field that inside you're in the craft and you're basically quantum locked? So you wouldn't feel any inertia if the craft was zigging around or whatever. You probably wouldn't feel gravity fields that are outside it. Basically, this field would stand in for the mass, all the atoms inside and including the skin of the craft. This is my thought anyway. This could all be way off base. I don't know. So I was playing with that in my head and thinking, okay, maybe that would work. I'd have to talk to somebody who's well-trained in physics to see if there's any merit to those thoughts. And then later, I was working on hypersonics. I was looking at hypersonic aircraft. I had a mutual friend with Mark Lewis over at the Department of Defense. They're heavily looking into, obviously hypersonics. And I started studying the problem, and you see this on the skin of the craft. You have crazy things happen at hypersonic speeds. It's chemistry. It's like, for example, if you have a hypersonic aircraft that's going through the atmosphere and it hits a pollution layer, that changes a lot. You have to account for that. You have to adjust for it. At the skin of the craft, there's some crazy physics happening. So I thought about that, and I was looking at using practical mathematics to model that problem, which after I Googled it, the Chinese are already doing exactly that. So I was a little late to the game. However, I thought about my fictional craft, right, with that fictional metamaterial, with that field, the standing waves inside, and everybody's all comfy inside, not subject to inertial, movement or whatever. And I started thinking about the skin of that craft and the field, right? My non-orbital metamaterial. Obviously, from the skin in, you have this nice standing wave thing that you've put together. But the outside of that is going to be, because it's non-orbital, for example, you're going to have whatever this field is going to be projecting out a short way off the skin of the craft. And the thought occurred to me, how would that change the drag coefficient of this thing? In other words, you have, let's say we're in atmosphere, you're going through nitrogen, oxygen, humidity, whatever. When it comes in contact, would that change the drag coefficient? The answer is I have no idea, but it certainly would change it. If you have, it might pin, right, what Remy just said, it might pin the air around it to some degree, or who knows, right? But it's like a half field. It's not a standing wave at this point. It's going to be like this. I thought of it in my mind as like hairs or cilia coming off of energy, right? Coming off the skin. Probably not a long distance, depending on the intensity of the field. The other thing that came to mind, I was thinking about it, is when let's say this field is standing in for the mass of the craft, and the mass would be the material itself, all the atmosphere inside, if there's any beings in there, or people or whatever, everything. Is there a relationship between the amount of energy you need to establish that field and the total mass of the craft? Or is it independent? It's just a volumetric thing. You don't care if you've got lead in there or if you've got aluminum or whatever. I don't know, right? But the thought, I was trying to wrestle with it in my mind. Let's see what happened next. So I thought, okay, that's a question. If you can create this field, would it impact the drag coefficient of the craft? The answer is maybe. Who knows? The next thing I thought of, I was rereading the old stuff with Einstein's work, and everybody knows that you take mass, accelerate it, and it comes near light speed, approaches light speed, the mass becomes infinite. There's a lot of debate about why, what's the mechanism. And I thought in my head, what if, just like you take a ferrous material and run it through a magnetic field and it picks up energy, right? Like they had this problem when they first came out with steam engines, and they would run them and the axles would become energized because it's, moving through a magnetic field. And they solved the problem. But that idea, only you have this field that's standing in for the mass. And so as, let's say the field is standing in for it, I call it a substitution, from a mass substitution kind of thing. The field itself, as you approach light speed, instead of the mass increasing, it would pick up energy from the ether, or whatever we're calling you guys would know the terms better than me, but it might pick up energy, and your only problem at that point would be bleeding off that energy. But your mass problem might not be there. So you might even be able to approach or hit light speed without the headaches of infinite mass, right? Maybe. I don't know. It's another idea. But the thought occurred to me, if this thing is standing in, if it's not only like doing this quantum locking thing for the craft and the occupants or whatever, but if it also might stand in for the mass, which I kind of skipped ahead a little bit, but I started thinking about it. If you had this craft and you energized it and put a mouse in it, you shook it around, the mouse would just sit there, right? It would be almost like a zero-G environment, right? And let's let's see. So yeah, so if you have this thing and this field is established, right, you would feel like you're weightless inside. So I did talk to Dr. Poher about this problem. And basically what you could do is set up a field within a field. You could, and he showed me how you would do it. You just, those thrusters we're talking about, you would just have a 1G down thrust. Let's say you pick the floor of the thing, and you'd have this thing constantly going. It would be like a magnetic field. It would circle around, and you'd constantly have this 1G. So you could create an atmosphere inside the craft. We had this constant 1G, no matter which orientation it had, you'd always be, stuck to the floor. That was interesting. But the thing I thought was, if you establish this craft with this field, and it's standing in for the mass temporarily while the field is up, you would be able to, let's say you had a 10,000 kilo craft, right? And then you turn on the field, and it might turn into a 10-gram craft, let's just say. And at that point, how much thrust do you really need? I mean, Remy could do a quick calculation. He could go up to it with a baseball bat, hit it, and probably knock it down range, depending on the drag coefficient, a long way, which is just a baseball bat. And I thought, okay, if that's the case, that would be quite interesting, because that field, which I was only focused on making that field for the quantum locking and the benefits you would have of not having to deal with G-forces, might also give you a couple of other very interesting benefits. One being a modified or reduced drag coefficient, right? It could also reduce the mass of the craft. And this kind of a light bulb went on, because I had several discussions with Jack Sarfati about this. And, he was talking about it. It's a low power, space metric engineering approach. And I thought, what I'm talking about is not high power, right? This would be just hitting with DC, maybe, I don't know, the voltages, but could be in the thousands, or maybe, 10,000 volts, whatever. And then creating this AC ripple over it in let's say the terahertz range or gigahertz range, and getting this effect that you want. And maybe you would have this craft that would have this amazing performance capabilities. You'd have this, you're on vacation from a lot of the physics that would normally affect mass. And this is interesting, if it is nearly massless, then the amount of thrust you would need to propel it at high speeds, whether it be in atmosphere or space or underwater, wherever, wouldn't be a ton of, if it's a low mass. There was a gentleman that posted something today, I think his name is Charlie, on this group. It was about an insects with this hexagonal secondary wing system that they pull up, and that it might have some, I don't know, anti-gravitic effects. And I thought, yesterday I was looking at insects, and there was one insect that can jump and exhibit 400 G, 400 Newton, 400 G force. And the scientists were looking at how does it survive that. And one of the things, obviously, is that it's a low mass insect. And it can do these 400 G jumps. And it got me to thinking, if the craft is low mass, all of a sudden you turn it into a low mass object, you might be able to get away with all types of maneuvers and use very little power to make it move about, as opposed to high power thrusters or rocket motors or whatever you like. Anyway, those are my thoughts. I just want to lay them out there, and kind of the journey I went through, and some of the stuff I brought in from the material science world, specifically the group 3,5 nitrides, InGaN, indium gallium nitride, and how that might be applied. There was a gentleman on this call that mentioned, I'm sorry, I don't know your name. You were mentioning some of the stuff just in brief comments before I started talking, and I'd like to hear your thoughts on that. But I don't know your name, but you were talking about some of this stuff. So I'd like just people to chime in and at this point, just tell me what they think of any and all of these thoughts.
Okay. So why don't we do this? Before we go to questions, let me put this on gallery view. Now, everyone, please put your hands together for Steve. And that was one heck of a stream of consciousness. Actually, you went over a bunch of stuff. So actually, let me start the Q&A out by asking. So you'd worked with Claude Poher. You know a fair amount about what he was doing. Now that's something that actually Mark and several of the other people in this conference are familiar with as well. His work is not as well known as Podkletnov's, but it's very interesting, and he claimed to get some results. What are your thoughts on him specifically?
So my impression, so like, for example, Eugene, he's a very bright guy. He's got his master's, and, you know, he's you know, fairly well trained. Poher is in a completely different category. The man is absolutely brilliant. I watched him doing calculations in his head that I couldn't do with a calculator when I was really good at this stuff back in the day. He was just ripping it out. He is a professional. He has a lot of experience with aerospace. He has connections at NASA. Everyone, he's well respected in the space. So he's a serious operator. I went and he showed me his lab. We went and did some things down there. It's a good lab. It's small, you know, but it's in his in Toulouse there, and he's very disciplined in his work, right? So I would say, if he does a calculation on it, you know, the only thing, you know, you could argue with him is he's got this pendulum thing that he uses to measure the thrust that it's putting out. And people have criticized and say, oh, maybe that's an electromagnetic artifact or whatever. So you could maybe go after that. But if the measurements from that are correct, his calculations would be dead on the money, in my opinion, right? When he showed me that chart, that would be correct. If he tells me, oh, this is related to Tel Aviv experiments, I would take it quite seriously. I would look at it, which is what I did, right? So that's my general impression of him. And he had some great applications. You know, when I met him, he was looking at microthrusters for satellite applications. Now, from my side, I come from an aerospace background at Northrop Grumman. I know the ramp to get that, to get something into space. Like, I talked with the director of the Air Force Research Lab about this. It's like a 7-year minimum ramp to go from I got a new thing to it's going to be flying around in space. And the only way, and that's if you partner up with an existing supplier that knows the supply chain. If you try and do it on your own, he says, you might be dead before it gets into space. I said, okay. And so he knows that space very well. So that was probably a really good application that he was targeting, you know, initially. His wife is a medical doctor, and she had a great application, which I thought was phenomenal. And it worked like this. I think I can talk about it because I think she's not trying to keep it a secret or anything, but basically she took that same gravity wave, or whatever you want to call it, this force beam, and she, being a medical doctor, was looking at it for medical imaging. And I thought, this is fantastic. And I said, how would it work? She said, well, it's a gravity wave. So your body is going to absorb it at different rates. Or the bone would absorb it differently than muscle tissue, than, you know, organs or fat or whatever. And I said, okay, on the back end, we're looking at piezo sensors, right? Yep. And I said, the idea here would be to get the tiniest piezo sensors you could and get a whole bunch of them, millions, like you would do like for a TV, right? A large screen TV. And so I went out and did some research for her, and I found a Japanese company that indeed makes those piezo sensors, really tiny. You could make an array of them and have, you know, I don't know how many, but good resolution, right? So you could stand someone in front of this screen, if you will, of piezo sensors, and you'd fire this thing, and they'd feel like a gravity push, right? Be like a G-force push. It's non-ionizing. We knew that, right? Claude had done a bunch of measurements on this radiation, you know, so it should be safe. You obviously want to do a lot of safety testing before you try this, and you get this image. So imagine that you, instead of going in for an MRI and sitting in that machine and the magnets bouncing around, banging around, you could just have a single pulse and get an image, maybe do another one or localize it, the focal length, right? And I thought that was really, really good idea. I don't know if she pursued it, but I thought that was a really, really good application. So those are my impressions of both the Claude Poher and his wife. She's quite brilliant.
Well, thank you. Let me go to Jeremy Reese next. He's got his hand up there. Jeremy, go for it, sir.
Unmute. Okay, there we go. Now we're unmuted. All right. So a couple things that you mentioned in your thoughts, which were that was awesome, by the way. I wanted to you had mentioned the word ether, which is, you know, like a really old term that's been thrown around, and it's kind of unsure what we were talking about here with regards to the ether. And I think that many of these scientists over the past 10 to 20 years have really defined more specifically what an ether is, or what the ether is, and it's an UNRRA radiation bath. I don't know if anyone else could correct me or kind of elaborate on this, but essentially that there's this microwave background radiation that's just ever present everywhere in the universe, and that there's also an ever present exchange of electromagnetic energy and photonic energy between all parts of the system at any given time. So I think that I think I like that model of the UNRRA radiation, is that it's UNRUH. If you want to look it up, and it's this idea that there's this radiation bath that sort of holds everything together and connects it in a matrix, and that's what gives rise to space, which space is essentially a structure which is created by the path of photons through space. So yeah, I wanted to elaborate on that. Then the other thing that you had just mentioned was you had worked with Claude Poher, and you said that what was there was something else that we had just talked about with regards to Claude that I want. Oh man. Okay, yeah, I wanted to talk about this idea of in conjunction with some of the ideas that you had about the craft. So the idea is that we could use microwaves to sort of eliminate. You have to kind of move the air out of the way, and air is relatively easy to move out of the way. So is water if you have the right physics. The South Korea has already posted their videos of their supercavitating torpedo technology, and if it works in water, you're damn right it works in air as well. So there's a number of countries already looking into this supercavitating technology. In conjunction with the other propulsion tech, because once you can force something and get it going really fast and get it going, you then need to move the air out the way in order to get it going faster. So there's a whole bunch of puzzle pieces beyond just propulsion that are involved in this whole UAP issue that we want to address and talk about. One of the things that it was interesting that came to mind is you talked about these left-handed metamaterials. Metamaterials, specifically left-handed metamaterials where they have negative permittivity, but some that also can exhibit negative permeability as well, and the very odd optical effects that can occur with those types of materials, where it's essentially like the skin of the craft. If it were a left-handed metamaterial, would essentially it would turn it completely invisible. It would almost implode the optical illusion of space-time around that object. And if you could combine that type of technology with, of course, the supercavitating tech, you essentially blast a laser beam straight ahead of you, really, really small, and energize just a short distance, maybe like 20 feet. Well, that's going to be calculated because, of course, if you're going through swamp gas or water, you're probably going to have to, readjust how that works. But it's essentially like a laser that focuses on a point right in front of the craft, or a line of points in front of the craft, and it puts so much energy into that in such a small space that it supercavitates. And that supercavitation effect causes, that bubble, that supercavitating bubble, and you want to time it right so that you fall through the hole created by the supercavitating bubble in front of your craft as you travel. So I think that as long as you have the right physics there, you can do it. I think that in conjunction with these other types of left-handed metamaterial skin coatings, they could potentially do other space-time warping effects where you pump a lot of optical energy into this type of thing. So there's this whole idea of you know what a Crookes interferometer is, right?
Yes.
So it's weird that photons have momentum. It's proven
Right.
with the Crookes interferometer that photons have momentum, and that momentum could be a potential source of gravity if we have the right mathematics and understand the interactions properly, and the dissipation of energy and the exchanges that are taking place. So I think
funny you bring up supercavitation.
Yeah,
because I have some experience with that. So there was a group of scientists that were doing some research, and they asked me to come over to the lab. So I went. They were looking for funding, and we were looking at it as a way, or they were looking at it to use it to split H2O. Cheap way to split H2O. And I looked at the demonstration or whatever, and I understand the principle of what you're talking about. I don't know if that's like, depending on, like, if you look at these nutty craft that fly around, you'd have to have some really high speed switching to, like, if you go in one direction and decide you're going to make a right, you have to switch that cavitation to this other direction. I don't know how it would react in different media density. Like if you're in water, you have to do a lot of adjustment to it. You'd have to constantly be adjusting this thing, just like you do with the hypersonic, right? If you're going through this atmospheric layers, and you're carrying, even pollution is a big deal with the hypersonics, right? So you'd have to do that. My thought was more like, if you have this weird field and it's extruding from on the skin of the craft, would that just in and of itself change the physics of drag? Would it be like a quasi-crystal? Are you familiar with the quasi-crystal concept?
Right. Yeah. So crystals, amorphous amorphous materials are glass, and then quasi-crystals are like the main three structural forms of matter. Randomly oriented, crystalline oriented, and then quasi-crystalline oriented.
And then the quasi-crystals, right? So I have a set of pots and pans I bought from France that are supposedly quasi-crystals, right? Which would mean that they would be non-stick 100%. It's a marketing thing. Things stick in there, but it is really slippery. But in theory, another physicist explained. He said if you can get a perfect quasi-crystal, it would be frictionless, right? Frictionless material. I said, okay, well, I'm still waiting for those pans to come out. I'll have to do with Teflon and my Citroen pens or whatever for now.
Wow, could you imagine that if it was more durable than Teflon and didn't have like the cancerous byproducts?
This is regular metal, but unfortunately, it's from Citroen, the French company, which is, I have a lot of Citroen cookware, and I was like, well, great, this is going to be non-stick, but with just metal, no Teflon, none of that. But it didn't live up to. Actually, one of them pitted really bad because I left sauce in it, and the acid ate through the coating, and that was the end of that. But the idea would be electromagnetic quasi-crystal type action, right? So like this field that we were talking about, this non-orbital material that's exuding this field outside the skin, would basically might change the physics of when, for example, water, air molecules or whatever come in contact with the skin, instead of like rubbing against it, do they get, I don't know, is there some sort of, maybe Remy could chime in, but would there be some sort of
it's called laminar flow, I think.
Laminar flow, correct? Yeah,
and
that's right.
You want to create like that supercavitated bubble around just the surface of the craft, so that it doesn't actually come into contact with anything, right?
That would work. That's
the idea. If you blast that supercavitating bubble in front of the craft, and you're traveling fast enough, and you're continuing along the line, blasting that bubble in front of yourself, and just falling through the hole that it creates.
That would definitely work. That was a big thing when I was a kid. My dad explained that to me about UFOs, and he said it was basically what you're talking about. That was a big theory back in the 60s, I guess, and 70s.
And that they're using light. They're using light to push around, so they have a lot of light trapped inside of them, and they can create or generate light through I don't know, whatever energy exchanges they're using. they can create and generate large amounts of light as thrust. And I don't know if there's another effect that goes on at the surface of the craft. You've seen that those videos from UAPtheory.com, where he goes into a couple of very interesting cases of UAP where they have like a mirror lens. It looks like a mirror distortion, like almost like what's called an Einstein ring.
Yeah. Well, Jeremy, if it's okay, I want to jump over. If it's okay, let me jump to Remy for questions and then come back. And I just
this
don't want
is
to
cool
take too
stuff,
long.
man. Though I thank you for presenting and taking part.
Yeah,
well, thank
for
you.
whatever it's worth. I hope it sparks some ideas, maybe.
Yeah. So let me go to Remy and then Michael Boyd after that. Remy, go for it, sir.
Yeah, thanks, Jeremy. That's interesting. And Steve, it's very interesting what Steve says as well. I like this idea that you saw. Did you see what I put up on the chat there with the frog levitating in the high magnetic field? Maybe it's something like that inside these crafts, like he's saying, like an inertial dampener. You set up this standing wave, and it kind of pins you to the craft, and then you get this kind of evanescent wave outside the craft, which the accounts that these craft don't generate sonic booms. So I think Steve's onto something there. That's sort of what I wanted to say. And as regards Jeremy, what Jeremy is saying as well, I think that's interesting. That's interesting too. I think you can, he's talking about laminar flow and so forth. I think if you have air bubbles around whatever, say torpedo, it slips through the medium. You release bubbles around it, and it slips through the medium much more easily. And I think shark skin does the same thing. It doesn't have the smooth skin as you think. It has a rough skin, and somehow that allows it to slip through the water. So there may be something to what Jeremy is saying too. That's all I had to say. Yeah.
I appreciate that, Remy. Yeah, I was thinking about it because I was studying the hypersonics, and obviously the sonic boom, problem, right? Shockwave collapse and whatever. And yeah, I just wonder if you had a low drag coefficient, and you're moving the thing through, are you going to get those shockwave buildups? Are you going to get the sonic boom? I don't know. It's a good question, though.
I have a quick question.
Yeah, go for it, Michael.
Shoot.
Could I trouble you to turn your camera on though, if that's okay?
Okay.
Thank you, sir.
Sure. So, how would you define a non-orbital or semi-orbital material?
Right. So if you go, like, I'm speaking from group 3,5 nitrides, right? So you can, for example, go and Google C plane, M plane, P plane, right, in that space, because that's where I'm speaking from. And basically, and I can send a link out if everybody's interested in that sort of thing, and I think it's interesting myself. So, but basically, C plane, when you have a crystal structure, you always start with a substrate, right? So we would use either sapphire or silicon carbide, right? So that's your nice structure there. And you would get an orientation from it, right? You would, there's 1-1-1 orientation, it's crystal orientation. And when you're growing crystal on it, for example, you're growing gallium nitride or InGaN, if it's C-plane, it's basically gonna grow sideways. And what that means from a physics standpoint is the electrons in orbit in the material are gonna remain in that layer you've grown when you fire it up and use it as, for example, a LED light or whatever, or a laser or whatever. Let's just stick with the LED light because it's simple. When you fire it up, the electrons are basically self-contained in the material, and at the surface of the material, there's very little of this. What would we call these pi electrons, or they're orphans that would go out into space above the surface of the material, right? If you grow them semipolar, which is like this, let's say, some of the orbits are going to escape from the material. Not all, but a fair amount, right? Because it's at an angle. It's polarized, correct? It's polarized, non-polarized, polar, non-polar, and semi-polar. In the semiconductor world, that's what I'm speaking from. And then when you go to non-polar, which we call P-plane, that's where the crystals are growing straight up, right? These are hexagonal crystals you're dealing with here. And really tricky because what they want to do is fall down. It's very unstable, and it grows straight up. Actually, the chief scientist from DARPA, he's like, we're trying to do this in our labs, and he's like, the slightest energy burst, like when you're using, let's say you're using heat or lasers or whatever you're using to sinter this stuff and make it grow, and then obviously you're going to activate it, right? That's the final step. The slightest increase, and all the blades of grass just fall over flat where they want to be. And it's basically, you might as well have saved the time and went with seaplane, which is really cheap to do, and that's what I did and what everybody does. So the idea that I had was, and again, the physics of it are, if it's non-orbital, you get a lot of electrons that are going to escape from the surface of the material. And I guess from a performance standpoint, when you have that unstable or semi-unstable material, that when you, for example, use it to make a light or a laser, you're going to get extreme performance out of it, right? As opposed to the seaplane or even the semi-polar crystals, right? And it's stuck in my head as a thing to look at. But if you're interested in the physics of it, just Google GaN, gallium nitride, and then C-plane, M-plane, P-plane, you'll see it come up, and then you'll see some recent articles talking about the non-orbital P-plane stuff and the promise it holds for the future and what you can do with it and so forth.
So also, I guess, is this just for 3.5 semiconductors or all direct bandgap stuff?
Probably for all direct bandgap, but I can't speak to that because my expertise is solidly in 3.5 nitrides. So in that world, like if you Google it, it comes up right away. Like if you just Google P-plane, C-plane, M-plane, it right away comes up nitrides, because that's the name of the game in the nitride space is can you grow this way? Can you grow this way? And then obviously cost effectively and so forth. But it's a great material. I mean, InGaN is great because you can tune it, the frequency of the thing, the band gap, you can tune it just by changing the ratio of indium and gallium, right?
When do you think we'll get to aluminum nitride?
You have it right now.
I mean, like,
nitride stuff is everywhere.
Fidelity as the others.
Yeah, the one that interests me the most, what I talked to the CEO of a company that's building stuff in Massachusetts is indium phosphide for switching applications. It's really high performance stuff, but obviously very tricky to make, as with everything. What else in that world was interesting? I think just understanding that the less stable the material is, if you can get it to set up and activate it, your performance characteristics go way up. That was the interesting takeaway from all of that.
That makes sense. I mean, I'm curious though why they don't use absorption chemistry to their advantage. What temperature range is this?
You're talking about you're asking the right questions here. So when I entered the space, the problem was for, let's say for GaN or InGaN, was you're talking about 500-600 C to activate it, to crystallize it, and so forth.
That makes
so you
sense.
get problem number one, thermal coefficient of expansion, right? So you have this substrate. Let's say you're an enterprising young man. You say, I'm going to use silicon carbide. So you look at the TC of that, right? And then you have lattice mismatch issues, right? Which you can solve with buffers, right? You can lay down buffers. Aluminum's popular. There's other things you can do to that, but you still can't get away from the thermal coefficient of expansion. So you have your wafer. And let's say you want to go with a nice 100-millimeter wafer, big size, so it's cheap to make. And you lay the GaN or InGaN down on it. You get it to crystallize. It's at 500 or 600 C. And as you're cooling it, the thing starts bowing up, right? I actually talked to the CEO of a company when he was trying this in his thing, and he said, I went over to it with the tweezers and I grabbed the end of it and it just shattered because of the stress it was under. And that's why they were all doing these small wafers, right? For that TCE issue. What I was looking to do in my company, the reason I put all that money and time into it, was to drop that to 300 C, if I could. Less than 400, 300, like in the range where you could use Kapton polyamide, right? Which is the stuff they used to put on the hard drive. It's a plastic type. You get it from DuPont and special stuff. And I was thinking,
if I could
this would be great if we could put it on Kapton and get it to lay up.
If I could add something, also once you get to 300C, now you can start using organic solvents potentially.
Yeah.
And then that is what opens up all the adsorption chemistry that allows you to limit the crystal growth in certain directions much more easily.
Right.
And, yeah.
There's all kinds of things that open up at low temp. I recommend
trying borax and erythritol. It's an interesting solvent. It's yeah. Well, I don't know. Actually, that might. No, not for your application. Not with nitrides.
We were using chemical etch for it. You know, for the lithography side.
Hey, drop me. We'll talk about it. We'll. Yeah. I mean.
Yeah, I'd love to. You know, the one thing that I wish we would have tried was graphene on the subject. I so wish we would have done that. We might have succeeded. I mean, our main competitor did succeed, and they have the current record for solar efficiency at 43.5%.
Nice.
And we were stuck. You know, the problem was we were stuck with the same problem they were, which was we were trying to make the InGaN graded InGaN, right? So you have different band gaps that respond to different photon colors, let's call it, right, of the sun. And you could tune this material. And, you know, they were transparent. If you did the wider ones at the top and narrow at the bottom, the sunlight would get through and you would get this massive, it has a 70-something% theoretical efficiency of the sun. That's why I targeted it. But the problem was as you start adding indium to it, we had the low temperature thing because we used a different type of physics to set it up. We weren't using heat primarily, we were using something else, right? Something else to basically saturate the atomic structure with energy so that it would crystallize and then activate. We have to activate it obviously with dopants and whatever. But in this case, so the InGaN, so we were playing with it and we kept hitting a wall where if we added too much indium into it, it would phase separate. It would phase separate. We were beating ourselves for a couple of years on this problem. It never occurred to me. I mean, I did ask the guys, I said, why do we do a tandem cell, right? Where we go with the indium content, stop, and then do something else. But then you have current mismatches, right? And you have tunnel junction diodes you have to engineer into the material. So in the end, we kind of stuck with that. We didn't have the budget to try for a tandem cell, right?
Again, multi-junction cells are just harder, yeah.
Correct, right? You know about that. So our competitor did this. They would work in the same material system. I met with them and I met the VC that was backing them out in the Silicon Valley. And what they did, they hit the same wall we hit, the indium wall. So they stopped. They had a nice graded multi-junction, multi-band gap, layer. And they did the second layer. They used a different, I don't know if it was germanium something, right, to pick up the other band gap that were missing from the high indium content. And they engineered the current matching so that, because if they're doing two different currents, one will drain the other. You have to kind of, match the currents from the two levels and you have an insulator between them. And they did it and they hit the record, man. They hit it at 40%, 38% at first. And they got it up to 43.5%. And they're using that stuff, I think. They were going to use it in these concentrated photovoltaics, right? CPV. We have all these mirrors and it's concentrated and handle like 500 suns. And, it's really as good. This stuff will handle high temperature, an InGaN solar cell. It will handle high radiation. I did the math with the Air Force. It'll be good in space for 150 years.
Yeah, I mean, if you have a very expensive material, might as well get as much energy on that surface area as possible.
Right. And in space, the other problem with solar is degradation from radiation, right? Radiation hardness. That's the name of the game up there. Its weight is one thing because it's about $10,000 a pound to get it up there. And then the other thing is obviously vibration with the rocket launch. You want to, survive that. And then once you're up in space and you unfurl, it's radiation is your problem. That will degrade your cells.
You just wait till we get the stuff Remy's team is working on in terms of Maxwell's zombies or whatever. I mean, once you have non-ergodic systems, like you can get crazy efficiencies without even trying. It's fun stuff.
Yeah, I mean, the basic thing that Jack always talks about. Jack Sarfati, have you seen his stuff?
Sure.
All right. So he's always talking about Froelich pumped systems that are far from equilibrium. There's
a little bit more to it, but yes.
Yeah, you know what I'm saying. That theme of having something that's unstable and pumping it far from equilibrium, you get some interesting effects. And the same thing is true from the semiconductor side. they're far from equilibrium, or they're out of equilibrium, and they exhibit these characteristics that are very interesting. Yep. So.
Oh, okay. Well, Michael, thank you. So let me go to. Let me go to Michael Boyd, who had asked a question. That and when it comes to band gaps and hard drives, which Steve, you mentioned both of those. Michael Boyd is like hardcore into both of those. So
great.
He's your guy. Michael?
This is the gentleman I was asking, Michael.
Yeah,
okay.
yeah. Oh, he and band gap. I'm not to tease you at all, but that is probably the word he's used more than anything else for the last couple of weeks. So
got a band gap, even time. I'm almost out of my band gap. So you were talking about this idea of basically gravitational or space-time metric engineering, basically, is what we're talking using embedded materials. And it sounds like you're pretty knowledgeable about semiconductor physics. So you noticed that.
Oh, Michael, I'm sorry, your mic is fading out for some reason.
Oh, how is this better?
Yeah, better now. Thank you. Sorry.
Yeah, closer to it. So, are you, Steve, are you familiar with the term lattice matching?
Of course. So it's the bane of my existence. Yeah.
So basically, when you're putting up what's an insulation layer or a passivation layer,
yeah, you're putting a lattice matching layer, right?
You need to have, and one of the ways that they do that is they like gallium arsenide, or what was gallium indium, what was the one?
Yeah. Gallium arsenide is a good buffer. Aluminum you can use, right? That's another good buffer.
Right. So like I worked with mercury cadmium telluride. Mercury cadmium telluride. Oops.
Oh yeah. Yeah, we looked at that. Toxic.
They make infrared detectors.
Right.
And so one of the techniques we would do is we take when we cut the semiconductor tool and then we etch off a layer, get rid of all the damage and stuff, and we got down to the good stuff, I call it. Then we would let it sit for a certain amount of time, and then what was called a native oxide would grow on top of that.
Right.
And then we would grow what we would call glass or some kind of silicon oxide.
Right. That's a whole industry unto itself. That's right.
That would be a type of passivation layer that you would use commonly. And so what we would, and then what I got a patent on is I would take, when I was doing that process, I'd put a bright light on it. And what that would do is it would polarize the dielectric, and that would make it more resistive.
Correct. The light is the key. What frequency light did you use?
This is like back in the.
Oh, so white light?
It was just like a
xenon lamp?
An incandescent lamp. Like
yeah,
one of those bright 1,000-watt ones or something.
Right. That's what we were using. We were playing with different frequencies, and you got different results based on the frequency.
Certainly.
But
so basically, what you're doing there is you're changing the dielectric properties of it.
Correct. That's one thing you're doing. That's one thing. That's a result.
And so, but my point here is, in order for this thing to not build up charge at the interface, you had to lattice match. You had to get, because if you did, then there are these little what we call dangling bonds or traps. It would trap charge.
That's right, trap charges.
That created in the silicon oxide, it wasn't a crystal, it was amorphous, it was a glass, right?
Right.
So that meant there was lots of, it wasn't SiO2, it was SiOX.
Right, SiOX.
So you had these, what I call dangling bonds. Well, right. Put that in a gamma ray source, it would like disintegrate. Right. Disintegrate and still be there. This would be like
garbage.
Like a short.
Yeah, that's right.
Okay. And so the way we developed to get around that is we came up with another passivation called silicon nitride.
Right. Okay.
Si3N4. And
Yep.
that would, and we could lattice match that to in this case, we're using Indian antimonide, INSB. And it's like a 5.
SB, that's tin, right?
Indium.
Indium is IN. SB would be stibium, right?
Antimony.
Tin.
Indium antimony. Antimony is SB.
Tin, right.
Okay, so in any case, that was the material, and both of them are what's called a zinc lattice. You know what I mean by that? It's like a diamond lattice.
Yeah.
Lattice, and that's how we would match it.
Okay.
So now, the reason I'm going through all these details is to try and explain to you how that works with the gravitational.
Okay. Get to that. Let's see that.
So now you have this whole lattice, these two lattices, you're changing the medium. You're going from a dielectric medium to a semiconductor, right? That's
right.
There are two different types of matter, or two different types of compositions of matter, okay?
Right.
But by matching the interface, basically that's what makes it so that it works electrically.
Correct.
The same thing happens with gravity at the interface, okay? So, but with gravity, it's not just the electromagnetic part, there's what I call a translational part, or it's like, you think it's still, but if you get down to the protons, they're moving, they're shaking.
Yes.
Okay, and the way they shake, and they send out these signals, what I call a song, the electron. Okay, so what happens is you got to get the electrons and the protons all shaking and singing and dancing to the same tune. And if you do that, you can create an artificial medium of space-time where it's expanded, like more like Hal Puthoff's. You know Hal Puthoff?
Oh yeah, I've talked to him. Yeah.
Well, he talks about expanded space-time and denser space-time. So when you get closer to a star, right, gravity is stronger. That when you're closer to the increased gravitational field, time slows. As you get farther away, it speeds up. So time goes faster in space than it does on Earth.
or outside our galaxy, for example.
So think of outsider, that's expanded space. Now get rid of all your electrons and think of just the protons are there. And in the, you know how you have intrinsic properties to a semiconductor?
Yes.
So like, so there's an intrinsic density of protons in outer space that's different than it is here on Earth. So think of the like lattice of just the protons are there without any electrons, and they have this little structure to them, but they're farther apart. So you get what I'm saying? So if
I do. I'm thinking.
Spin it. Like the way I found this is by spinning using spin by the motion. Everything's in motion in our universe. There is no at rest. You know when they talk about
Right.
All mass is relative.
Even absolute motion unto itself.
Yeah.
Right.
So there's nothing sitting still. The Earth's moving around the sun pretty damn fast, and then the sun's moving in the arm of the Milky Way galaxy pretty damn fast, and then the galaxy's moving even faster.
Right.
Well, yeah, and wouldn't that go back to what Mark Sokol's working with the Elzephon stuff? Because even your atoms are spinning, right?
Yeah.
So
that's the whole point. The atoms, the nucleus of the atom That's where the gravitational field is carried, because that's where the mass of matter comes from. That's why photons don't have mass. You know, we were talking about that in the chat. You got two beams of photons going past each other in the opposite direction. They don't attract each other. That's because they don't have any mass. But matter does. And it's the protons, not the electrons, really. You can freeze out, essentially, the electrons just by cooling down there.
So, Michael, let me just see if I get this straight. So you're talking about two different materials, for example, like you were talking about SiOx or whatever, and you're doing something else. So you have two different materials, but you're lattice matched. So everything's working together, which I know very well, right? Because we had to lattice match for our stuff as well. You know, you had your lattice matching, you had your point defects, you had your interstitial defects, and then you had your, what do you call it, thermal coefficient of expansion, right? Which is the, you know, and these are all the challenges we were dealing with. We did figure out a way to get rid of the defect stuff really well with our process, and we used light to do it.
Yeah,
we were able to get rid of, we were able to push impurities out of the material, which is great, right? Depending on the material.
Depends on what you're using it for.
Yeah, right. So we had that. We had micro hardness. We also observed from this process, which is very interesting. And the lattice matching thing is obvious. Got to have it. You don't have a functioning device if the lattice mismatch is there, or if you do, it's like unstable. But I never thought to sit down and say, lattice match dissimilar materials, what can you do with them? I was more, well, when I was working on that, I was just trying to get the damn thing to work and get out the door and make money, right? But later I was thinking about, when we were talking about superconductors, is how would you engineer the material like a metamaterial to get the properties you're looking for, right? How does that work? And so but it's kind of over my head every time I read these metamaterial papers. They start talking about ellipses and everything, and I'm kind of lost sometimes with it. It's quite intricate.
Well, the book that I put the link in, you should check that out, because it's got some really good information.
Oh, you put a link in there?
What?
You put a link in the chat?
Yeah, I put a link up above in the chat too.
You know, Michael, I didn't see that either. Could you tell me what the name is? Let me look that up. It was metamaterials.
I'll find it. Hold on, give me a second. I'll tell you that.
Maybe you typed that in and it went directly to somebody instead of to everybody.
I'm looking for the times here.
I'm looking in the chat, some really good comments. You know, I'm so busy talking, I don't even read these things. So,
yeah, well, and I am.
Okay, here it is. It's at 1:11 p.m. I put this link to the book.
Oh, there we go.
Okay, so what I was talking about though is when you're going between one space-time medium to another space-time medium, there's a difference in the inner atomic difference. And what I'm talking about is the protons are like there still, because of virtually being in the crystal, but the crystal lattice dimensions are different. So you have to figure out a way to get between those two dimensions. And that's where this what I call vibrational mode thing comes in. So you get them both vibrate, or the base, they're not really vibrating, it's more of a spin state.
Right.
But you get these two mediums into a spin state where they're basically synchronized, and the way I like to think about it is like a capacitor, okay?
Mm-hmm.
And you have like and that's why this book is good, because it has a double negative dielectric, where the permeability and the permeability are both, and if you put them both, if you get these two dielectrics next to each other, you can basically make it disappear. Make it like optical cloaking. essentially you're trying to do the same thing, but not optically. We're trying to do it basically with the space-time movement.
I got you.
And so, and then you talk about the word ether and the
yeah, I use that because I'm like an old guy. Like I started studying physics in the 60s.
The word
and a lot of the material still had that word in it.
What's the word? It's like talking about ghosts. You know, it's like certain subjects, you bring them up and they're like taboo. Okay.
Yeah. But I'm old school.
One of those taboo subjects.
Yeah. What do they call it now? Remy might know. What do they call it now?
They call it vacuum energy.
Okay, dark energy.
But they also talk about like these virtual electrons and positrons propagating
right.
existence and all that kind of stuff, which I frankly don't buy that. I think it's of course I have what is it called? I have my own biases. Okay.
Well, does anybody have a copy?
Protons, are in a flux in the universe, and there's regions of low flux density, like where we are, because our sun creates a bubble around it of protons that are coming from it. Okay, but the intergalactic space has got higher flux density of protons. Okay, but intrinsic, it's like an intrinsic value of. And that's the energy that we're talking about. It's these
interesting.
Moving are creating an energetic field.
You have to read. I'll have to read up on it some more. The one paper that interested me was there was one paper that Albert Einstein tried to publish. He sent it for peer review. The guy that was supposed to peer review it sent it to a couple other guys without asking him, and they had him pull the paper. Right, it's the only paper that they ever pulled of his, never got published, and they had a problem with the title right off the bat, which was "Gravity Does Not Exist." Right, and I'm trying to read the thing. I found a copy of it online in German, but it's like a photograph of it, and I was trying to find a text version of it because I'd love to see what it was that he never was able to publish about the subject of gravity and how it works. Right, but I read all of his other papers. And he's always very careful to talk about gravity in a certain way. And even his colleagues were back in the day about what it is and how does it work. But I'm really curious to see what that paper is that they rejected of his. I don't know if anybody knows where I can get a copy in English. That's the title of it.
I heard a lot of his work came from his wife.
Maybe. That's behind every man there's a woman, right?
I heard that the rumor I heard is that he wasn't so good at math.
No, he wasn't.
And his wife was great at math.
And he was the front man?
And in reality, even though he won the Nobel Prize, his wife got all the proceeds. Now, I think there's a reason for that. Besides,
wouldn't shock me. Wouldn't shock me at all. But I'd love to get a hold of that paper.
That was
his
ex-wife at that point, by the way.
Well, I was going to say the wife always gets all the proceeds. That says nothing.
In the divorce, yeah.
So Michael, let me see if anybody else has questions here. Who else has questions for Steve?
I have a question.
Yeah, go for it, Harold.
Okay, what I want to ask, very interesting conversations, a lot of futuristic stuff, look like a lot of promising research. So I ask you, give me, what do you see coming down the pipeline in terms of gravity research, anti-gravity metamaterial that will help a spaceship better, especially for the military in the near future? What do you see there? Give me your educated guess.
Okay, my guess is a low budget version of it, which I think they might already have. I should elaborate a little bit on this, right? I'm pretty sure they have what we're talking about, and I'll tell you why I think that. I used to live in Arizona, in a town called Maricopa, right? It's just south of Phoenix, near Casa Grande, if you know the area. Huh?
That's all over the news now, with all that what's happening there.
Oh, okay. I didn't know. But I lived there. I had a house, and there's a highway that goes from Phoenix out there, right? It's really long, dark at night. Some parts are lit, some parts aren't. I drove up and down that. That was the only way to get to Phoenix. There's one road, right? And if there was a traffic accident, you're there for hours. But anyway, on this road, I noticed I was driving with a friend, and he's in the construction business. And there was this, it's all Indian reservation, wild horses and whatever. There's nothing out there, absolutely nothing. And all of a sudden, there's this one ranch house on reservation land with a long driveway off the road, and not much, it looked pretty whatever. And he said, well, yeah, he pointed that ranch house to me. And I said, yeah, I've seen it a million times. It's probably, owned by the tribal people. He says, I don't think so. He says, number one, look at it. And I said, yeah, it looks like maybe a 2-bed ranch, maybe that. He says, how many cars and vans are outside of it? I said, wow, there's like a dozen. He says, where are all the people? They're not out on the ranch. So they must be in the house. And if they're in the house, they're standing shoulder to shoulder. There's nowhere to move. I said, okay, I'm a little, okay, fine. But then he pointed up to the power for it. So the power lines are up there. You have main power lines to run out to Maricopa and beyond. And he's like, you see that transformer up on the pole there? I said, yeah. He says, that's not for a house, Steve. That's for a factory. They're running enough power to that house to power a factory. So I said, okay. So I called up a buddy on the East Coast that works in defense, and I said, if you guys have an operation going there, the locals are getting suspicious, right? So I think it was like a month later, they put this sign, they built a little sign thing at the front. It was like one of those brick things, and they put a sign on it that said, U.S. Space Command. So apparently my buddy was right. It's some sort of underground thing. And they put this thing on U.S. Space Command. And then, so that was there for a while. Then they took the emblem off and they put another one on it. It said something else. U.S. Air Force something or other. Then they took that one off and put something else. And finally, they just took it off, and there's this placard there sitting there. But here's the interesting part of the story. So I was driving on that same road with a couple, a married couple, and we happened to be discussing these topics about UFOs, UAPs, and so forth. And lo and behold, right over where that location was this triangular craft. It was massive, massive. It was lit on the edges. It was sitting there. We pulled over. Thing was dead silent. I'm going to say 2,000 feet up, directly above that, whatever you want to call it, Space Command thing. And we're watching it. They wanted to take pictures, and I discouraged them, because I figured it was one of our craft, And then the thing just took off so fast, you couldn't follow it with your eye. It was gone, right? And silent too. There was no noise. So I'm pretty sure they have something cooking there, right? In other words, the things we're talking about, the military probably has a lot of this stuff. I think they have a low budget version as well, which is like where they took like some A-10 Warthogs and maybe some other aircraft. And rather than spending all the money to make them, you take an existing aircraft, right? And you put in some sort of a lifter, if you want to call it that, or some sort of, part of the system that just gives it lift, nothing else, not propulsion, nothing else, right? And so budget-wise, you've just got that, and you have this craft. And again, Linda Moulton House, somebody sent in photographs of these things, and I looked at them very carefully. And they were reporting that they had sounds of jet engines like right over their house, really loud, and then they would cut out, right? And then they would start up again and cut out. They couldn't see anything. They're looking up in the sky and so forth. And imagine a low-budget version where you get an aircraft like a Warthog. It's got the lifter, so you take off. You could do a short takeoff and landing situation, right? But you're using your regular jet engines, okay? And you just fire the engines up for a while and then coast. And you could use the regular, ailerons and everything to go. You can even go up to the jet stream and ride that for a while, all without burning fuel, and silently too, if you're not running the jets. And if you turn the jets off, once they cool off, you won't have a thermal signature. So that's pretty good, right? And then finally, these craft, they said they were invisible. And I saw the photo. Somebody took a photo of them when they were, decloaked. And they were all white. Every part of the plane was white. And I could see they had four A-10, Warthog aircraft. And then they had a refueling tanker with it, which I recognize as KC, I don't remember what the designation was. And then that thing had this weird popsicle stick, I call it, on the back, on the tail. So it was strange. They were all white. And I thought maybe they put a coating on it where they could energize it, and it would have, you know, it'd be invisible, negative index of refraction type situation. And if you look at that, that's a cheap way to get tactical or strategic advantage without spending a ton of money. You know, you coat your craft with something that makes it invisible to radar and also visual light. You put this little one lifter or whatever they are to get rid of the lift issue, and you use your standard jets and jet fuel to propel it around. But if you think about it from a combat scenario, you could get these things near the theater and get them going at a pretty good speed, and then shut off the engines and let them cool off. And you'd essentially be invisible and silent. And then you could attack from the air. So I think they're already doing things like what we're talking about. And for the future, I guess just imagine that they're continually, you know, improving and dropping the cost, you know. But the one thing when I saw that triangular craft, the only thing I could think of was how long were they doing this and how much did it cost? Was it 50 billion? Was it 100 billion? Was it 10 years? Was it 30 years? How much went into it? How many people died? You know, test pilots, scientists, who knows? That's all I could think of was cost, you know.
Look like, you know, that was very perceptive of you to notice that transformer, because looked like when they installed it, everybody else missed the clues, what it would give out. And I'm going to ask you the next question, because look like you know a lot, and I want to take it to the edge. Now, about 10 years ago, maybe more than 10 years ago, I saw that the Japanese did, you know, the invisibility cloak. And in the video, it worked so extremely well. It was incredible. Now, I had never heard of anybody, you know, in the Defense Department or any project or anything that they're using that invisibility cloak to be, you know, to make airplanes invisible. They talk about, you know, the Black Project and so on, you know, like the F-114, the invisible, but I never heard of that. I mean, what do you know about that? I mean, have they done any project like that in which they can shroud it with invisibility, with metamaterial, however they do it? But I know the Japanese did a very good job. What can you tell me?
When I left defense, the whole thing, and I worked on some of these projects, was we had low observable, then we had VLO, right? So we had LO, then VLO, which is very low observable. Then we had ELO, which is extremely low observable. And this had to do with coatings and whatever, which are, you know, you can just look this up on the internet now. It's anti-reflective coatings for radar, essentially, right? When I worked in defense, we had these coatings for the military aircraft. And one day, some of the guys took a van and they put this special paint on it. You had to bake it in an oven to cure it. So we put it in the oven or whatever. And then it was that we had it out on the runway, and we had a cop that we knew come in with his radar gun. And a van is probably the easiest thing to track on with a radar, right? Because it's flat-sided. The hardest thing to track is a VW Beetle with the rounded surfaces, really tough. But this one was easy, right? And he stood on the side of the runway, and somebody drove up by him doing about 80, and it didn't even register on his radar gun, right? So those are the types of coatings that we had when I left. And I knew people that worked on the F-117, you know, and my friend was the director on the B-2 program. But we don't talk about the very specific things, and I still don't talk about those things. But all I could say is that was back in the 80s and early 90s. So I would imagine they've progressed quite a bit. And from what I could see, maybe they have, you know, conquered some of these issues with even the what we'll call invisibility to visible light as well. It wouldn't shock me if that were the case.
I haven't heard anybody, you know, in the defense or program, anything, you know, and I was in the Air Force many years.
Right.
Anybody is thinking of making an airplane optically invisible, because for a fighter pilot, for example, being up in the sky and having an airplane like the invisibility cloak that you don't see it with your eyes or with the radar, I mean, it's quite an advantage, but I haven't seen about it.
Yeah, no, absolutely. And if that stuff is going on, it's going to be in black programs, way off to the side. Servicemen are not going to know about it. And the ones that do, that interact with the craft, that deal with it, are going to have these special clearances with lifetime secrecy, right? You know, I've signed a bunch of them. And it's just, that's the way they're going to manage it. And that's the way they should, because they're spending gobs of money on this stuff. And if they do get it, they don't want to just parade it in front of the public, because that also includes our opponents would also see it, right?
That's
So,
true, you know.
right.
Yeah. Well, thank you, Harold. So let me go to Mark Sokol, and we've got probably just about 15 minutes left, Steve, if you're okay with that. And
yeah, sure.
Okay. Mark, go
Hey.
for it, sir.
Hey, Steve, I'm here in the
Hey, Mark.
Falcon Space Lab. I heard you talking before about inertial mass cancellation or making something weightless. That's actually something that we're working on with the Alzaphon experiment, which is we're trying to create coherent matter states in the core of the atom, like get all the spins oriented.
Okay.
What was your theory behind what makes matter weightless? Like,
Yeah. First, before I say that, is there some sort of a link where I can read up on your project? Because I did see a spreadsheet where you have tasks and everything, which look like great project management you're doing. But is there somewhere I could read on it and see an overview?
an overview. I mean, there was presentations here at APEC, and we just give updates every time. I'm going to show you guys it live in a couple moments.
Okay.
And you can come down to the lab and help out with it hands-on.
Where are you located again?
Hawthorne, New Jersey.
Hawthorne, that's right.
Well, and Mark, don't forget, in between then and now, yeah, we do have Ken Griggs, who's going to walk us through Phoenix theory. So.
Oh yeah,
okay.
I'm real excited to hear about that. But,
maybe Mark, you could send me a link to it, and I'll read on it before I make any comments. You know what I mean? I'll like immerse myself in it.
Okay. Okay.
You know,
it's basic. Sam Thompson's actually holding up the book, Gravity Control with Present Technology. That is the book that his son wrote. Frederick Alzaphon's son, David, wrote that book. There's also
Gravity Control with, okay, I'll Google it and I'll buy a copy. Let's say that. That's a probably good place to start, right?
That's an Amazon. But the real scientific paper is, it's available online. It's called Anti-Gravity with Present Technology.
Okay, let me write that one down. Okay.
It's from 1981.
81. I think I've seen that one. I've never read it, but I've seen it around.
Yeah, that's the experiment I'm working on.
Okay.
Also, are you working on any experiments?
Are you kidding me, man? I'm so busy. I barely had time for this. I'm doing quite a few other different projects completely unrelated to this. Some stuff with geopolitical analysis, some stuff with we're looking at crop projections. So it's for a hedge fund, so they make investment decisions based on analysis, and so that's taking up more than half my time. And
so
the other
where
half
hedge funds stand on anti-gravity investments?
What is what?
Where's the hedge funds and the anti-gravity investment?
You know, it's funny. I had this chat with Eugene, and I said, Eugene, because he sent me his presentation, you know, his pitch, right? And I said, I know a lot of VC. I know a lot of them, all over the planet, right? The big ones. And I said, none of them have a flying saucer fund, right? Because you go to a VC or whatever, they have, you know, they have your alternative energy guys, and then you have your physics, and then you have your, you know, they have everything. Social media is a big thing, whatever. And I said, none of them have a, and I said, this is usually governments do this type of thing, not private investors. I mean, it's a big ask, right? So I was like, if you can come up with something for alternative energy, yeah, right away, walk in, and these guys are throwing money down on it, you know? So that was my thing to him. But yeah, I mean, the most money I've seen thrown around toward this type of thing is from angels, individual investors that are just really you know, fascinated by the field, and they want to throw down on it, and then they'll give you money. But I haven't seen venture capital, you know, the big players that are willing to take the risk and then tell their limited partners why I just blew $20 million on, you know, anti-gravity. You know what I mean? Like they're always looking for an exit. Where's their exit? Right? You know, so,
oh yeah, I mean, if you're investing in anti-gravity, your exit's going to be
30
a
years.
decade or two out at least. You're talking about starting a company that's going to need to be the size of Toyota in order to be profitable.
Right, or bigger, right?
Yeah.
And have the cooperation of various governments and FAA and God knows who else is going to sign off on the thing. It's a long road, but it's worth pursuing, in my opinion.
And it has the capability of changing the world.
Absolutely. Yeah. Game changer.
So yeah. Let me jump in real quick. Mark Steele had a question too. So Mark Sokol, were you just about there? Or?
I'm done. Yeah.
Okay.
Yeah, Mark, just to follow up with you, what I want to do is read about your project, and then I'll answer your question about how I think my thoughts integrate with what you're doing. Is it fair enough? Okay.
Yeah, I think Remy just posted a link to the paper in the chat, so you can check that out.
Awesome.
Fantastic.
Yeah. And then let me see, Mark. Let me ask you to unmute Mark Steele. Okay.
Sure. So I put in the chat, but I'll try to summarize it. I was curious. Steve mentioned the levels of secrecy and everything, and I was a military officer, so I'm familiar with the clearances and stuff like that and the structure. How do you think those apply to like the Pays? I'm not sure if I'm saying his name right. Salvatore Pays patents via the Navy that they filed, because those all seem like pretty far out, almost science fiction-y kinds of things. I've got a good friend who's got 2 graduate engineering degrees from MIT and is a patent attorney for the DOE, including Los Alamos and Oak Ridge and all those types of labs. And she's pretty convinced that the Navy would not file patents like that unless they had something either working or pretty close to working, that they wouldn't be willing to go public, because she said basically filing a patent is the opposite of all those levels of secrecy.
Correct. Right. How they work it, how they've always worked it. And again, I'm speaking up to early 1990s experience, is that the U.S. Patent Office, when they get patents in, if there's something and the UK does the same thing, right? They call it something else over there. If there's something that has implications for national security, before they, while they're processing it, and it takes a while to process patents, provisionals or formal filings, while they get the submission, they run it by the defense guys. And they have tons of scientists, really good ones. And if it looks like it's something that might be, they don't want the public, to be published, they'll vector it off into a black patent program. Right? It's all patents that are black. And if they let it go public, it could mean one of 3 things. One, that's not something they think would work practically. In other words, you're not warm, so they'll let it out. The second one would be, something that's might partially work, but is far enough off where, like, their competitors, and let's call them in my day the Soviets or Russians or the Chinese or whomever, would maybe spend money on, waste money on, right? That might have some merit to it. And the third possibility is that it actually slipped through the cracks. You know what I mean? The patent examiner was like, it was a Monday and didn't catch it, and it went through and nobody caught it in the system. So that's also, you got to hang that one out there too. If it was one
that's
that
a fourth option, that it was actually intentional, they're putting it out there and it actually works, because they
she's more than familiar with all those black patent things, and
right.
I mean, she works with Los Alamos and Oak Ridge and all those places, right? She works for the DOE,
stuff,
so she seemed to think the patent office, even with those kinds of patents, is pretty adamant that if you can't at least show them that there's some chance that this thing works, they're not gonna grant you the patent.
Right.
And
right.
that, so there's at least something out there that, I dismissed these patents initially. I read them and I'm like, this is a BS, or it's just a psyop, or it's just something thrown out there to muddy the waters or something. And I was surprised because she took a completely opposite view of that.
Well, there's another concept that we used to use a lot in the black world, which was HIPS, right? Hide in plain sight. So one was like, yeah, that's it. We're going to put it out there and nobody makes a fuss about it. It's sitting right in plain sight. And their opponents will look at it and say, they would never let this out. This is nonsense.
Right, like your Space Force base that you mentioned. I don't remember where you said it was from, but.
Yeah, it's Maricopa. Yeah. I can show you the exact location, but it's still there. I looked at, from Google Earth, and it was like all kinds of weird stuff happening on that property. Weird things that, and they cut every couple of years they come out with a local news article about what's going on there, and it never matches up with what I see from the sky. So it's pretty funny, but almost certainly it's an underground base of some sort. The official explanation now, since all this happened, is that they use it to monitor space activity or something. It's part of that network, and that may be true. I don't know, but I saw some other real funky things going on there at one time.
Makes sense. I'm actually, I find all this pretty fascinating, but I'm an engineer, but I haven't been this deep into the physics for a long time, and so a lot of this is over my head. But it's a pretty
Right.
fascinating
too.
discussions. You know,
A lot
so.
of this is over my head. I just relate what I see and know and my thoughts, and that's about it for what they're worth.
Yeah.
Thank you,
Well,
Steve.
And thank you as well, Mark. Okay, so let me see. You marked out. So let me see. Do we have a couple more questions? We have just about 5 minutes left with Steve. Steve, thank you so much for joining us today. That was absolutely remarkable. Yeah, and especially for the Q&A too. You've just really drilled through this. Let me see. Eric Hermanson had asked about, he was talking about inertial shielding. Eric, did you want to try to squeeze in a few thoughts?
Hi, Tim. No, I kind of just blurting out some messages in chat. Inertial shielding. So there's a guy named Paul Marmé, and probably nobody's read his papers because they're in his estate, and you have to go to his estate website to see them. And he theorized that the inertia is from the inductance of a magnetic field while the charged particle is accelerating. And if you read Jackson, Electromagnetics book, 3rd edition, chapter 11, and you look at the radiation reaction force, which is a known phenomenon. If you could somehow shield the back reaction so that you're taking advantage of the runaway acceleration without the back reaction, the feedback that comes from the back reaction, then you could essentially have an exponential runaway acceleration where you may not feel any inertial effects. I don't know how to, I think that that propellantless propulsion and anti-gravity are things that are simpler than people think. And I think there's many more than one mechanism that works. In terms of inertial shielding, I think that's a tougher problem to solve. And I'm not sure it can be done, but it's hard enough. People talk about 5 dimensions, 11 dimensions. I think it's hard enough to work in 3 dimensions. And I think it's hard enough to get propellantless propulsion to work. So I say let's tone it down a notch and let's just get something to work. Then we can think about all this other stuff. Anyway.
I agree with you. What you just said about there's more than one way to skin this cat. I totally think that's the case. I also think that although I was very interested in that inertia thing and how Poher was saying, that the step one, the baby step, is to get the propulsion thing working, right? I just thought ahead to that one because I'm not working on the propulsion side anymore. How would I tackle that? So I came up with this sort of mental ideas about it. But I did think that if you could achieve that level of sophistication, you might solve more than one problem, more than just the inertial canceling. It might be you're solving a couple of problems at once. I don't know.
I think it's possible to create, it probably is possible to create force fields that are impenetrable, that aren't based on a black hole or white hole creation. I know Jack Sarfati has this pretty cool idea where you can create a white hole where things can get out but nothing can get in. I'm not so sure you need to do that. I think there's other ways to do that. So you might be able to create a force field shield. If you really look hard on the internet, you'll find some examples of things that have occurred in manufacturing plants where and one of them was written up in a electrostatics journal where it seemed to the people, to the scientists working in the plant, that there was some kind of a force field being produced through the motion of electrostatic charges. So, I think a lot of things are possible. It's just a matter of figuring them out and testing them and making sure the government doesn't classify everything so that we could at least, because that would be a great asteroid shield, right? If we get that to work. So, who knows?
I think to answer your question, actually, the gentleman before was asking what I see in the future. I think looking at this field now, and I've only been looking at it for the last, 6 years or whatever. I didn't even know it was a field before that. But looking at all the data and knowing the military as I do, and knowing the black world, I think they're getting pretty close to like letting chunks of this out to the public to use for the common good, right? The always thing about that, you know, the pushback on that is always non-proliferation, right?
Yes.
Same with the nuclear stuff. It's like their obsession, which is their right to be obsessed. It's a lot of lunatics in the world.
There are, and there's two problems that I see. If it's possible to easily create antimatter or have some kind of nuclear reaction where you get protons or positrons flying out, that's very dangerous, right? You could blow up a city block with a teaspoonful of antimatter, I think. I don't know. I've never calculated it. Then the other thing is...
No, you can blow up more than that. With that antimatter, it's absolutely, you know, incredible if you get enough of it. Yeah.
Yeah, we can't let that kind of thing out. And then there's the kinetic energy weapons, right? So anything that's over a Mach 5 weapon, it's hard to stop that. And so, I mean, a vehicle. So if you have a Mach 5 or higher vehicle, you could deliver like a nuclear weapon. But that's actually bad, especially if it's a thermonuclear weapon. But it may not be as bad as being able to attain like a Mach 30 and smashing a much smaller heavy object, right?
Yeah, kinetic.
You know, one half mv squared. So the v is to the square, and you could destroy a city block maybe with a softball going at Mach 30. I don't know. I haven't calculated, but you get what I'm saying, right?
I do.
So that's the problem: is the kinetic energy. You know, we don't really want people to be able to launch things that can fly extremely fast, even if they take a long time to accelerate. You don't want that, and you don't want, at least you don't want that till there's peace in the world. And you also don't want, and that's why I created the Peace to Final Frontier peace initiative on Facebook. But you also don't want people to be able to deorbit satellites, or especially like the space station, right? Because that thing's going at what, 22,000 miles an hour, and it's damn heavy and big. And if it survives reentry, that could, you know, that could tear down a row of skyscrapers pretty easily, right?
Oh yeah, kinetic weapons from space are a real problem.
Big problems.
Yeah.
So those are the things you got to classify. But like, we don't really need to have airplane crashes anymore. Why have families suffer, when their loved ones die in an airplane crash, when maybe there's a better way to do it? And
I gave this a lot of thought, looking at this whole thing and seeing, for example, just the electromagnetic, or gravitation stuff that I was working on. Think about it. Do I have time for a quick story?
Well, no, actually, we're out of time because I'm a minute over.
Later.
Yeah. So let me do this. Yeah. If you'll be here for the Q&A session later, and if not, we could do it another time. But so let me go back to gallery view real quick and let me see, mute everybody out. So everyone, please, again, put your hands together and give Steve Lutz an enormous thank you for his time and very long, detailed Q&A session. And again, thank you again, Steve. We're just squeezing up on our time. So I want to go now to Ken Griggs, who has joined us, and I've been getting emails about Ken. So let me read you his bio first. Ken Griggs has a Bachelor's of Science and Engineering degree in Aerospace and Mechanical Engineering with a minor in Theoretical Physics from Princeton University, as well as an MS in Theoretical Physics from the University of Maryland. He's worked for the DoD as a software engineer through GE Aerospace and has career experience with Martin Marietta and Lockheed Martin. He's also the founder of Imagine Studios and has recently joined up with our very own Jeremy Reese to create Hover Brothers in 2018. So let me see, Ken. There we go. Thank you for joining us, sir. Thank you very much. And let me hand it over to you. Okay, and I can't see. Oh, you're muted. Okay, let me ask you to unmute. There we go.
Fantastic. Can you hear me now?
Yeah, perfect.
Okay, this is my first time on doing this on Zoom, so I apologize for any technical difficulties.
Well, and you don't need the mask on Zoom, but you.
Well, no. For to appreciate the time in which we're living, in particular, you know, look, if we went back to where Newton did his work, he went home because of a pandemic.
Wow.
So we just kind of want to be reminded in the future when we look back at this time, what was really kind of happening, even if people don't believe it. But, you know, so I just want to, you know, just as a mark of history, that's all.
Well, thank you again for
I'm protecting all of me from me. How about that?
Thank you again for joining us. I've gotten, I think, 5 or 6, maybe even 7 emails from people who are just super excited. They're like, Ken's coming on to speak. That's awesome. So thank you.
That's very special. I really appreciate that. So let me just also make sure that I can get the presentation working well enough. We'll be sharing screens, obviously. So again, really my first time. Can you see my screen, or have I shared it appropriately?
I don't think you've shared. So it's still focused on you. So try clicking. There should be a green share screen button down there at the bottom of your Zoom.
There we go. Somewhere down there. There we go. Okay.
There we go. Yeah. Oh, perfect.
Okay. Fantastic. So I don't really know what you guys are actually seeing, but I hope it's the right thing. Okay.
Yeah, no, that looks great. So let me mute myself out and again, just take it away, sir. And thank you yet again.
Well, thank you guys for having me. My name is Ken Griggs, and I created a theory called Project Phoenix. And what we're going to be doing today is just kind of walking through scattering theory in quantum physics and in relativity theory, but scattering theory overall through the lens of Phoenix. So the question that everybody, I guess, should be asking is, what is Phoenix? And in short, Phoenix stands for the physics of entanglement, networks, and information exchanges. And basically, the central question, of course, that we're asking is, can we wrap all of everything we've ever known about anything in the universe up? That's a huge question, obviously. But that's what we do in foundational theoretical physics, as you guys are very well aware of. The essence of how Phoenix approaches this is to drop down and dirty into asking some of the simplest questions, like, what is a measurement? Now, all of science is based on that question. Science is, and exclusively, only about measurement. So the central theme of what we'll be talking about today is exactly that. What I've listed here are some of the informal definitions of Phoenix, like everything in the universe necessarily needs everything else in the universe in order to exist. That's a nice idea. What does it mean? That measurement is nothing more than counting patterns. That's a huge idea. But what does that mean? Or that the measurable universe is really a way of talking about the flow along a well or fully connected network. And again, what does that mean? All of these things have relevance. One of them has relevance to math. One of them has relevance to all of our experimentation. And another one has relevance to algorithms in computer science. So, you know, can we tie all of these things together under one very nice structure? And that's what we'll be talking about today. Oh, by the way, if you guys have any questions, I've got certain moments in the presentation. I could just call them random commercials. But really what they're meant to serve as is for you guys to go, hey, stop, you know, tell me something more about this. I also have a slide number up on the upper, I guess, right-hand corner of the screen. It's a, you know, kind of a strange gold. So, you know, mark the slide if you're not, you know, if you really want to get back to that one. You guys have probably seen this particular slide. And what we do here is to basically turn particle physics into effectively Lego pieces. And what we establish, and we're going to get into this only loosely today, but I wanted to mention that all of this is actually tied to exactly what we mean by scattering theory. So here you're just looking at what those pieces are that we talked about basically back in 2012, 2016, 2018, if you ever see any of my past videos. But these are quarks and leptons. So we're going to get through this. We'll deal with this. So formally, what the heck is Phoenix? And formally, I mean, all of y'all can read. So the essence is that you'll be able to read this into the future. So I don't just want to read the words on the PowerPoint. But nevertheless, Phoenix is again, a principle, a method for constructing all of the parts of physics that we already know, and then using those parts of physics in order to construct things in physics that we don't know. So, for example, quantum gravity. That was something that we were able to achieve back in 2012, but we've just been building up on that. How far do you go beyond quantum gravity? For example, warp drive. So warp drive exists. We're not going to be talking about that today. That's the next lecture. But here we just have to establish the actual background. How do you understand what we're going to be talking about later on? Okay. So beyond the formality, let's get into what the heck do we mean by measurement? Okay, and this is a critical thing. I mean, when we're asking the question about science, when we're doing anything dealing with theoretical physics, if you can't answer this question, where are we really? So quantum mechanics has worked very long and hard through the years in order to try to establish what do they mean by measurement. Einstein was fairly certain what he meant by measurement. But as it stands today, it's still a question. So the best way for us to describe this concept, and if you can contradict it, I always welcome anybody to find a contradiction in anything I'm saying, or a counterexample contradiction. So the question is, what do we mean by measurement? And all we've ever meant, from as far as I can tell, is all we've ever meant by measurement is just counting structures. What is a structure? A structure is anything that's different from something else, right? So anything that can be established as, it could be a word, it could be an alphabet structure, it could be, you know, an actual physical structure illuminated by gravity or by light, it doesn't matter, as long as it's a distinct pattern. And that distinct pattern can be counted. This is what we mean by measurement. The question then becomes, how do we make that relevant in terms of a mathematical underpinning? And so what we're engaged with here is demonstrating that quantum field theory easily comes out of the question of what do we mean by measurement? Now, the main principle when you're asking this kind of a question is something that has generally been called general covariance. So in Einstein's general theory of relativity, general covariance is the principle that underlies everything. And effectively what it says is that, and by the way, this is in a prior paper that we produced about 3 years ago on relativity theory in Phoenix. And in that paper, we described the same set of things we're describing here for scattering theory. But nevertheless, general covariance is really a nice way of saying that the universe that we live in doesn't really ask, how are you labeling things? By virtue of however you choose to label them, the underlying physics should be the same. So the principle of general covariance is our mathematical way of framing that. Okay, so what we find is that in the language of things not having, what do we call them, labels, or making how we do physics label free, there is a concept in mathematics deeply devoted to that, and we call those permutations. So general covariance that we can demonstrate is actually another way of saying permutations. And then the question is, what the heck do you mean by permutations? Well, then we have a mathematical structure that we can turn to. And the best one that we found is called combinatorics. And a good reference that we use all throughout this particular presentation are two mathematicians / computer scientists who devised something called analytic combinatorics back in the 1970s and 80s and 90s. And one of them has recently passed. His name was Blachelet. And the other one used to be a computer scientist. He actually started the computer science department at Princeton. And his name is Sedgwick. But I put references to their work at the bottom of most of these pages. Okay, so the main item that we deal with in permutations, in combinatorics, is something called generating functions. Now let's just be perfectly clear about it. A generating function is a simple data counting device. It's nothing more than a spreadsheet, right, where you mark something, some pattern, and then you put a count on it. And the way you assemble the patterns and a count, we call it a generating function, is nothing more than a polynomial. So z squared, z cubed, z to the fourth, all of those things are basically different patterns. And then the numbers in front of those z squared, z cubed, z to the fourth would be the count of those patterns. So when you formally see what a generating function looks like, it looks like a polynomial. It's just got z and some variable, which is a way of accounting for some type of pattern. What do we mean by pattern? Z could represent red. Z squared could represent blue. Z cubed could represent green. We don't care what you mean, what you're assigning to the z squared, z cubed. It's just that they have to be distinct things. Could be oranges, apples, and bananas. And then the number in front of that would simply be the number of oranges, apples, and bananas. But when you look at it, you see a polynomial. And you're like, okay, that's just a polynomial. Well, that's good. It's a simple mathematical device that we're now using in order to count things. You determine what those things are. Okay, so that's what we mean by generating function. It's nothing more than a polynomial with integer coefficients, okay? So what we can establish here is that there's a specific type of polynomial. And this type of polynomial we're going to call a cyclic generating function. Now, I'm kind of praying that everybody is kind of okay with math. You're not so bad with algebra, you're not so bad with matrices. So I'm depending on that kind of a level of proficiency. But if you have any questions, don't hesitate. So what we have here are statements about how a generating function can very simply look as the sum of z squared, z cubed, etc. And then what we recognize is that this cycle, this cyclic generating function, this very easy polynomial, if you exponentiate the whole darn thing, you get something even more substantial. It's called the permutation generating function. And that permutation generating function, and by the way, I'm in Las Vegas right now. The only reason why casinos work, the only reason why people make money on casinos is because of the permutation generating function. It tells the casino veritably how much they need to invest in order to get this machine to produce money back for them. So this tool, this permutation generating function, is your mathematical card counting mechanism. Okay, I don't want to get too far outside of it, but to keep it real, for everybody, this beautiful thing called the permutation generating function is veritably the essence of what we do when we deal with statistics, when we deal with, well, just about anything that requires math. So for us, the permutation generating function, this piece of T thingy, is really a statement about general covariance. It tells you that you can switch labels on anything, and these are the sorts of ways of accounting for how labels can be switched amongst, bananas, oranges, and apples, and yet you're still able to perform a count. You're still able to get something valuable out of that system. Okay, I'm going to go on. Okay, so what we're showing here is that in a universe where we're talking about something called the number of vertices, I think of the universe as a bag of vertices. And what I'm trying to do with those vertices, or a bag of cards, or a bag of marble, it really doesn't matter, but some very finite system of stuff. And how we mark that stuff is called vertices. So, one thing might be on one vertex, something else might be on another, whatever. So the idea, though, is that if we basically define that the number of vertices of our system, the number of cards in our deck is fixed, then we can begin to talk about whatever card game Vegas is about to win money from you with. Okay, so what we're establishing here is that there's a very, very elegant statement about the permutation generating function, this thing we call PT, and this other thing we were talking about called the cyclic generating function that we call GT. And again, all the cyclic generating function is a way of counting things, objects, cards, etc. And then exponentiating that gives us this other way of statistically talking about the arrangements and rearrangements of those cards, this permutation generating function. And what we find is it has a very, very elegant form, 1 over 1 minus z. Now, think about this for a second. We had one thing, this thing we call GT, the cyclic generating function, it's veritably an infinite series, or it's very big, you know, and it's got z to the 100th power to it. But all of a sudden, if you exponentiate it, you get this very small algebraic structure, 1 over 1 plus z, or 1 over 1 minus z. This is elegant. This means that something that looked unreasonably big in size is now something that's a very simple algebraic equation. 1 over 1 minus z, you can probably do it in your head. Tell me what z is, I'll do the calculation. The point, though, is that the permutation generating function takes on a very small, tight form. And that tight form is veritably fixed. 1 over 1 plus z, or 1 over 1 minus z. It's a beautiful thing. Okay, so what we demonstrate here is that what we call Feynman propagators is directly related to this concept of a permutation generating function. In fact, we can show in this slide how you get from one to the other. What assumptions do you make to make this transformation possible? And we'll get back to this. Okay, so what do you do in terms of getting real physics out of either one of these things? So where we're going to start, which, by the way, there was a paper that we produced before on relativity theory, where we start exactly here. What we demonstrate is that when you look at those cycles, like the z squared, z cubed, you know, this generating function, and you just split the generating function into two pieces. One of the pieces only has odd cycles, z cubed, z to the 5th, z to the 7th, etc. And the other one has even pieces, you know, z squared, z to the 4th, etc. The thing about these two generating functions, this breaking apart of the cyclic generating function, the beauty about that is that all of these parts are always added together. You're not really breaking the generating function into two pieces. What you're really doing is choosing one part and then later adding the second part. But the point here is that physics, as we know, the equations of physics, simply come about by how you choose to look at that cyclic generating function and just to break it into pieces. Relativity appears when you break it into two pieces, odd versus even. Quantum field theory occurs in this case when you randomly break it apart, which is bizarre. But quantum field theory is a much more basic structure than even relativity theory is. And for this reason, because when you're choosing how am I going to, you know, am I going to look at the z and z squared part of it? Again, when I say generating function, think of a polynomial and just ask yourself the question, okay, do I want to just move some parts over here and other parts over here and then deal with them in different ways, deal with them later from each other? Or do I want to look at the whole thing? And what we're saying is that the physics that we actually use in our world is really simply how someone has decided to break apart the cyclic generating function and to proceed to measure one part of it or proceed to look at another part of it. So what we're saying here is that formally, scattering theory, how we take a ball and throw it at the wall and then watch how it bounces off. How does the wall react to the ball? How does the ball react to the wall? That's scattering theory. And every trick about quantum mechanics comes down to that. Here, what we're saying is that all of the equations of quantum field theory simply come about because you're looking at this thing we call a generating function, a cyclic generating function, and you're just dividing it into several parts according to whatever your whim is. The measuring device, the Large Hadron Collider in CERN, Fermi Labs collider, all of those colliders are just different ways of looking at the cyclic generating function and breaking it down into different pieces to measure different things. That's the whole thing. Okay, so the idea is very simple here. That if you give me the cyclic generating function, you break it into two pieces. One of the pieces we're going to call an arrangement, and the other piece we're just going to call it a derangement. And they actually have special and different properties to them. We're marking the arrangement and the derangement by an A, obviously, and a D. And we're saying that, again, in the cyclic generating, you're just pulling it apart additively. But in the exponential or the permutation generating function, this thing called PT, it's really the product of those two things. But we'll get to that. Okay, and here all we're showing is that the permutation of the bullet, the thing you're throwing at the wall, is really just the exponentiation of the cyclic generating function that you pulled apart only for the arrangement. Again, the arrangement is just something some way of separating some part from another part. Okay. So here's a random commercial break. Now, if you guys have any questions right now, please don't hesitate. And by the way, you can silence this part, or I'll put it on silence, whatever. But it's just a random commercial break, and I'm inviting any questions at this point because I know it's been a lot so far. I know it's a really cool animation. But are there any questions?
Well, Ken, typically we do questions at the end of the overall session. Now, so Jeremy Reese had said he's having trouble with your audio because of the mask.
Yeah, I can just hold this thing up to my mouth.
There we go. Yeah, and I can hear you okay, but he indicated that he was having some audio issues with it.
Okay. Is this better?
I'll leave. Jeremy, do you want to text me and let me know?
Come on, Jeremy, let him know. Okay, so
I think that's better.
We'll wait till the end for the questions. I pray, Jeremy, that you can actually hear me through this. If not, we'll have a one-on-one.
Yeah, well, Ken, I can definitely hear you okay. I think I have everybody else muted out, so but I'll put myself back on mute. And sorry for the interruption, sir.
Oh, no, please interrupt. Okay, so here, all we're saying is that when you define both the bullet in terms of a series of cyclic generating, or sorry, a series of cycles on a generating function, and you equally then can define the target as the remaining cycles. We call it the Recontres number. It's French. I don't know French. I only know Spanish. So forgive me for mispronouncing, for not pronouncing that correctly. But we call this other thing, the target generating function, we have a word, we call it a derangement. Okay. So what we're able to do, again, is to separate out some general polynomial that we call a generating function into two pieces. One piece will serve as a bullet, and the second piece will serve as a target. The beauty about this way of doing it is that when you bring both pieces back together, you get effectively what we call the universe. And all we're really saying is that the universe is nothing more than you randomly dividing it into two pieces. I kind of think about, that Michelangelo picture of Adam and God touching finger. It's kind of like that. It's a whole big darn thing, but for some strange reason, you can divide it into two pieces. You and everything else. Okay. But when you do that, you've effectively created what we call scattering theory. Now, the novelty about this way of thinking about scattering theory is that the whole system is always taken into account. And the way we do that is, at least with the permutation generating function, it's simply the product of both the bullet and the target. And in the end, we get back to something we know very well, which is this 1/1 minus z, very small algebraic representation of what we call the total permutation generating function, the thing that marks all of the different ways you can relabel the structure of measurement, the structure of the universe that you're actually working with. Okay. And again, if I go too quickly through these slides, because there's a lot of reading, don't hesitate. Certainly read it on your own. Come back to me, or read it as I'm talking and come back to me, however it works for you. So what we're showing here is how do you establish special relativity theory from these generating functions? It's really very easy. And we're not going to go through this explicitly here because we do that in a prior paper, but just to give you how that actually looks in this particular slide. Okay. But what's much more important to us here in scattering theory is this idea of the target versus the bullet. And in the target, in regular quantum field theory, we have an idea of how to talk about a target. How do you talk about something that you're firing your particle beam at? And the way we talk about it is we talk about it as a Yukawa potential. It is this energy domain where when you throw little electrons at it, the electrons decide, hey, you know something? I'm going to bounce off of that. So that thing that it's bouncing off of, that target, we actually have a potential energy that's associated with that target. And normally what we're trying to do in particle physics is to understand that target. Because supposedly we already know what our bullets are, right? We kind of know what the electrons are, whatever we're using in our particle accelerator. What we're interested in is what the heck is happening once we hit the target. What is that target? How is that target, effectively described? That's what we mean by Yukawa potential. And in this description, we can always get to what is that Yukawa potential once we've begun to bombard it with our, with our bullets. And here we have our actual definition of that. That's directly from the permutation generating function of the target. I mean, that makes sense, right? Okay. So here, again, we have this two-part series. We've taken the whole universe, we've chopped it in half, or chopped it into two pieces. One piece will serve as the bullet. Another piece will serve as a derangement or a target or a Yukawa potential. And we're just giving you a sketch of what that means. Okay, another place for a commercial, but we're going to get past that since we're at the end with our questions. Okay, now let's be realistic. Having a two-part universe with Adam and God is veritably insufficient. There's no room for anything but God and man love. Okay, we need something more. We need to actually understand that when you actually are doing a particle experiment, you're not trying to measure the whole darn universe. You're only trying to measure something in front of you, hopefully. So we have a nice expression. We can divide the universe not into two pieces, but into three pieces. The generating function, the cyclic generating function that we started with, enables you to divide the universe into any number of pieces. So we're really choosing here to ask, well, what happens if we choose to divide the universe in three things? You, the measurer, whatever you're trying to measure, maybe it's the microphone, and by the way, and everything else. Okay, so I'm looking at you, Tim. You're in the background. So I can't, I'm not watching you. I don't know what you're about to do next, but I somehow know that whatever you're going to do is probably going to affect me and this microphone, such that I have to take you into account to be a realistic experiment. So here's to you, Tim. But the idea here is that if you, instead of being naive about how do I divide the universe between me and something else, I really have to divide the universe in three ways. That is our most basic understanding of experiment. You, the measurer, something that you're measuring, and the rest of the universe. So we have a tripart division of our understanding that we can do. We can do that using this cyclic representation of the universe So we go ahead, we do it, and this is what we get. It's unbelievable. Actually, what we get is something that was already very well talked about by two physicists. The main one for me is Max Tegmark, because he's been talking about this for at least 10 years now. That when you choose to make a measurement in the universe, there are things about that the quantum world requires of you. And one of those things is, what do we mean by two systems in the universe, you and the system you're measuring, being entangled? What does it mean when the system and you become disentangled? What do we call any of it? What the heck is measurement? So Max Tegmark and this other fellow, Mr. I can't pronounce his name, I apologize. I'm just, okay, so the idea here is you've got a trinary system, a trinary representation of the universe, where you have a subject, the experimenter, the experimental device, you have an object, which is effectively what you're trying to measure, and then you have all this background noise that we call an environment. And this trinary operation is fully what we are doing when we are taking this cyclic generating function and dividing it into three pieces. And again, I encourage you to go back to this material and to look at my notes, look at my references, and begin to see the logic in all of this. Okay. And here we're walking through and basically saying, however you choose to set up your experiment, some part of your experiment will serve as the bullets, and then another part of your experiment will serve as the target. And this is a nice, beautiful, sophisticated way of accounting for all measurements that can ever be taken in a world governed by math. Inevitably, that's what we're trying to do. We're trying to this down into the most basic type of math that deals with measurement. And again, that's combinatorics. Because all we're doing is counting structures. That's all these generating functions are doing. Okay, so here, I just wanted to make a note that a really huge breakthrough in our work here was to demonstrate that, that how we talk about measurement is really counting these patterns, and the count of those patterns is really these generating functions and their coefficients. So there's going to have a z squared, z cubed, whatever the generating function looks like, but it's going to be a number in front of each one of those things. And that count in front of this polynomial, in front of each one of the variables in that polynomial, is the measurement. That's what we're measuring. So what we're going to show you in this next graphic, in this table, is how do you make that association? So for example, if our coefficients of our generating function are 1 and then all the other coefficients are 0, so basically what the generating function looks like is just z. That's all it is, just the variable z. Then we account for that as the speed. Yours is what we call the relativistic speed, but it's your speed divided by the speed of light. It's a ratio. But that's what that thing is. If you get that count says you just measured the speed of the object. However, if you get another count where instead of there just being, a 1 zeros, it's all ones, what you've actually measured is what we call the momentum of the particle. And then again, if you get the 1 minus 1, etc. So we walk through to demonstrate how the generating function produces a valid, measurable thing. And in this case, it looks like relativity theory is being measured. Now, in this second table, what we want to account for is what we would call the momentum, what we would call the forces, and what we would call higher order derivatives of the forces. But in general, we call these sequences, which are really derivatives. And so the idea is that however we, or whatever we're measuring, has an associated look to a generating function involved. That look can be, again, relativistic, that look can be quantum mechanical, That look can involve things that change. For example, in our first, in this particular slide, slide 27, we see that the numbers are increasing by 1. That's a momentum. We see in the second row that or rather the third row, that the numbers are increasing by 1, and then 2, and then 3, and then 4, and then 5. We call that an acceleration or force, etc. So how things change is also encoded in this way of dealing with generator functions. And as a sort of a nice little version of that, we can recover what has generally been called the Hawking-Hartle wave function for describing the whole universe. So Stephen Hawking and another fellow named Hartle developed a beautiful way of understanding the Big Bang that was completely consistent with quantum mechanics. And in that description, I'm certain they realized that they were utilizing Bernoulli numbers in order to accomplish, how can something really just always be there and then explode into existence and then collapse and explode and collapse, etc. But that's embodied in this particular wave function description of the universe. Okay. So another aspect is that when we ask, well, if you're dealing with particles, then you're not simply dealing with zeros and ones and twos and threes. You're dealing with other measurable things about particles, like the mass of a particle, or the charge of a particle, or the spin of a particle. Basically everything that we actually measure about particles, short of their momentum, and short of the forces acting on them, involve all of these internal things, like, okay, what is the spin of a particle and why? Well, the beauty about this way of dealing with measurement is that the cyclic generating function enables us to include other ways of marking systems, we call it. And those other ways we call charges. So in Phoenix and in most of the particle physics world, a charge is any conserved quantity associated with a particle. And in particular, they tend to be internally conserved quantities, like charge, like electric charge, like the mass of the particle, like the spin of a particle. All the things that I just mentioned are basically internal conserved quantities. And in combinatorics, the language that we're using here, those things are accounted for by something we call marking your univariate cyclic generating function. Our mark of that is that there's another property we're calling use of I. Okay. Now, formally, when you mark your system, all of the generating functions all evolve. They become a little bit different. They all have a new mass marker to them, or charge marker, whichever label you choose to use. And how Phoenix defines that marker is given by a wonderful concept that in a later talk we'll get definitely in. So when we give a talk, if you guys will invite me back, when we give a talk on general relativity theory and quantum mechanics or quantum gravity, then we'll talk very much about why this definition of a marker, of a mass, of a charge, is so relevant to every part of physics that we know, because it is what is intimately involved in defining quantum gravity. But here, all we're saying is that if you don't know, the trace, this TR0, is really where you take a matrix and you just add the diagonal together. That's what we mean by trace. So in quantum mechanics in particular, the trace is used as a measurable. So when we say, well, what's the momentum of a particle? Well, inevitably we're going to go through and find the trace of some system of matrices. So here, explicitly, the trace of your matrix associated with your particle, that's what that is. The trace of your matrix becomes a marker to the charge, the mass, a property of that system of graphs. So we're not going to work on an example here, but I can sort of have a whiteboard here to give you an example if you're interested in really specifically what that means. But it is how we describe mass. It is how we describe charge. It is how we describe spin. All of those things that we talk about when we talk about systems of particles. Okay, so I am going to come to this slide. Now, what's so important about this slide is that we've been describing particles, okay? We've talked a little bit about the cycles that, you know, systems of particles have, graphs in particular have, etc. The question in how we do physics is not so much the particles, it's about what we call quantum fields. And the question is, in physics, what's the relationship between, let's say, a proton and our graph of a proton, and then the proton field that we seem to measure in the laboratory? And this is the association right here. It simply says that you do what we call a Heisenberg trick on what you're calling a discrete particle, like a proton. And then you can make that simple chunky particle into a continuous field. It's a way of saying, look, I have an ear of corn and I want to describe a corn field. So in math, we have a way for doing that. Okay, you give me the corn, I'll give you a cornfield. It's a beautiful way of Jesus multiplying fish and bread. But nevertheless, it's also a nice way of saying, how do you get liquid water from an atom of H2O, rather a molecule? How do you get that description of water that we know on the macroscopic level? So this particular transformation is the combinatoric way of taking a chunky version of matter and turning it into its continuous field version. And that's, I mean, I can't tell you how important that is. Okay. So what we realized in this exposition is that the technique, the method that we use in order to figure out what the heck we're measuring when systems are changing. And if you go back to the table I was showing you between discrete numbers and then how systems can change, what we have is that our mechanism for describing how systems actually change is known as the commutator. Now this object is given by the square bracket, two things inside separated by a comma, and then the rest of the square bracket. But all that means, if you're not familiar with commutators in math, it just means that Z and G are two matrices, and the square bracket, comma, the other one is really Z times G minus G times Z. It's really a simple way of talking about, do those two matrices commute? So if I take the product in one order and I subtract from it the product of two matrices in the opposite order, if it's equal to 0, then those two matrices commute, like regular numbers will. But if it's not equal to 0, they don't commute, and then you have a whole system that makes quantum mechanics what quantum mechanics is, because its commutators don't usually commute when you have two systems that you're trying to measure that are not compatible for measurement together. Okay. Now, so this thing that's called the extraction operator, it's what combinatorics uses in order to, when you ask the question, what is this thing counting? What is this generating function actually counting? Normally we would say, well, use the extraction operator on the generating function. It will extract out the count, okay? And all that is what is the number in front of Z, Z squared, Z cubed? Your polynomial has some numbers in front of the variables. The extraction operator just gets the numbers. That's all it's doing. It's just looking for coefficients. And by the way, those coefficients are what we call measurements. That's the important part here. Okay. So the thing that allows us to really place all of this stuff that I've just said in the context of physics comes about because we can also define calculus. Now, I don't know how many of you people were ever happy with calculus. I hope most of you were, but nevertheless, calculus is, you know, sort of how we can describe changing systems. And so it's really important in terms of everything that we're doing here as well. Now, we weren't the first one to come up with how do we use everything we've been talking about in terms of developing calculus. The first person to do that I'm aware of was Sir Isaac Newton, believe it or not. Sir Isaac Newton was 400 years ahead of the game, and obviously he didn't know it. But his derivation of calculus is entirely dependent upon a commutator methodology as well, what we call finite differences. But he developed it, and because of that, he developed calculus first. Okay, maybe Leibniz did, but nevertheless. So the idea is we come to a particular mathematician or physicist named Louis Kaufmann, who about 2004, I discovered his work and realized that he and I were speaking the same game. Now, in my work, I expressed a lot of the stuff that I just expressed to you, but I had this evolution equation, which you see in blue in the center of the screen. The evolution equation is very simple. It says that if you give me a graph, this equation will tell me what that graph, oh, by the way, the graph is a particle. It is a graphical representation of a particle, like a proton or a neutron or some other system of particles. But if you give me the graph, the matrix of that graph, then I can determine with that equation alone what that particle can become and also what it cannot become. So this is what we call the evolution of our evolution equation, the evolution of graphs into new forms. And this is how effectively Kaufmann also starts his paper. He demonstrates that this particular evolution equation that we both share actually is the essence of what we call commutator calculus, in particular commutator derivative calculus. And I invite you guys to really read through the slide. But there are two parts. There's the graph that we have given the name chi, or x, if people don't know Latin. And then the thing that changes chi, which is called T, the transformation matrix. And these two matrices, again, have this wonderful property to them. We call it a similarity equation. But these two matrices enable for chi to become another type of chi. And the expression at the bottom here is exactly that. Now, Kaufmann goes into a lot more finesse and detail in terms of, what's really happening here quantum mechanically with these matrices doing the dance that they're doing. But we are very happy to simply reside in the idea that one of the matrices represents particles and space and a graph, and the other, the T matrix, represents a transformation or time. And again, what Kaufmann is doing in particular is walking through how this association between these graphs and this time, these transformations, yields quantum mechanics. And in particular here, we're able to yield Heisenberg's version of quantum mechanics, where we come up with our evolution equation, etc. Now, what Kaufmann really does that is still beautiful to me in so many ways is that he's able to show, and we walk through it here, we're just not going to go through it because I'm sure I'm putting half of you to sleep, but we're able to show, he's able to show, that there's a way of defining a derivative and three different types of derivatives that are associated with these commutators and are associated with our matrix chi and our transformation matrix T, to the point where he's able to define a singular type of quantity in special and rather general relativity theory called the metric. And that metric, this Gij, is actually associated with the commutator of space and momentum. Now, if you guys remember about general quantum mechanics, that these two concepts, space, measuring something spatially, and measuring something in terms of its momentum, are not commuting variables. Okay, effectively what it means is that if I measure something about space, and then I want to simultaneously measure something about, measure a particle's position in space rather, and then simultaneously measure the particle's momentum and speed, I can't measure both of those quantities with arbitrary accuracy at the same time. Because if I measure one very well, the other one gets thrown off. So that's given to us by this commutator relationship. But what Kaufman is saying is that that same commutator relationship describes something called the metric. It's describing a way of defining how things are even measurable in the first place. And that's big, that's huge, because that GIJ is what is the basic tool of Einstein's general theory of relativity. And it comes out of this commutator relationship that Kaufman is able to demonstrate. I'm going to skip through that one. Now, and we're going to skip through this commercial since we've got questions at the end. Okay, so what do we do in Phoenix? We generalize Kaufman's work on derivatives. We give it a much more basic understanding. I mean, he does a really good job. Please don't get me wrong, the man is a genius. But we just take it to a level where we can apply it to any system, any matrix system, not just matrices that are somehow dealing with, a particle. This applies to all matrices. That's the beauty about this. So if you've got a system described by matrices and you want to ask, well, what's the momentum of that matrix? This is the stuff that will get you that answer. If you want to know the physics of a database, I don't care what the database is. The database is described by a matrix or a series of matrices. This math works for it. And you'll have a physics way of looking at your data. It's beautiful. Okay. So we generalize Kaufman's derivatives, and we have a reason for that, because we'll get to that in the last section. But the reason is because Kaufman never came up with integrals. It's wonderful to have derivatives. I grant you that. Calculus is beautiful with it. But you have to be able to undo derivatives, right? I want to know the whole circle, not just a slice of it. So if you want to get the whole circle, you need integrals. So we were able to give Kaufman the integrals that he never knew he had. Okay. But nevertheless, here, what we're talking about is that when we are dealing with these commutator derivatives, we're also dealing with two things. We're dealing with matrices, which are describing sort of a chunky look at particles. And then we're dealing with another type of variable, a scalar variable, that's really associated with a continuous way of looking at our particles. So one is a particle version, the matrix operator, and another one is a field version, or the scalar variable, the scalar operator, if you want to call it that. One of them is describing the wheat, the ear of corn, and the other one is describing the field of corn. One of them is describing the chunky energy associated with a water molecule, and the other one is describing how waves of water crash on the shore. Very different descriptions, right? But these are the descriptions that we utilize, obviously. One of them is fundamentally quantum mechanical, and the other one is fundamentally thermodynamic. Okay, and that's a really important distinction, but that distinction is incorporated in his derivatives. So we can always maneuver between chunky, microscopic reality and the reality that we seem to live on, which is a reality of fields permeating all of space. Okay. So we're going to walk through this, meaning that we're not going to talk about it as much. I'm going to skip ahead to the integrals. But take your time in going through this. You're going to be astounded. By the way, the reason why we like commutators is because they're easy to do. When was the last time you really worked through dealing with derivatives? I mean, it's tough. You got a lot of things to memorize. Here, you don't have to memorize a lot. Okay, so one of our main achievements in Phoenix is coming up with an integral version of what the heck Kaufman was just talking about with derivatives. And although we were able to recognize what this was in terms of Kaufman's derivatives, we were actually beat to the punch by that same guy who I love to hate and hate to love, Werner Heisenberg. Thank you, Werner. Okay, so what Werner did when he came up with his Heisenberg representation of quantum mechanics is he figured out a nice little math trick. And this math trick is governed by this exponential of b and times a times the exponential of minus b, etc. But it's a math trick that allows you to start talking about commutators upon commutators upon commutators. And what we were just talking about is that commutators represented derivatives. Here, we've got all these various, Russian doll versions of commutators all added together that is speaking directly about derivatives, because that's what they are. But Heisenberg, I don't think really realized it in that context, because honestly speaking, it was Kaufman, 40 years later, who really did put it together in the context of derivatives. So now we can utilize both of those to understand how to undo what Kaufman was doing, how to take derivatives and to integrate with them. And that's what we're showing here, that effectively this subtle trick that Werner Heisenberg came up with is really explicitly what we call integration. And the integration is of these little derivative pieces that Kaufman was talking about. Okay. So what we do here is, actually, let me go back one slide, I apologize. What we do here is we show that if you give me a graph, like a graph representing a proton, I'm going to call that A sub alpha, or A sub A rather. You give me that graph, and then you give me a transformation that will take, let's say, that graph and turn it into another graph. We'll call that B. Okay, that transformation we're just going to call B. And you stick it in this and you utilize all of these commutators. What you've actually done is you've integrated that particle, whatever that original graph was, you've turned that ear of corn into a field of corn. The description of the field is this A, and then in parentheses, a function of a scalar parameter or a continuous variable, B. That is your field of corn coming out of your ear of corn. So, I wish farmers would tune in, right? Because if they did, they could probably judge their whole corn crop. Because you just perform this little integration and you get the whole darn thing for the season, okay? That's pretty good. But what's good for us is that you can turn a water molecule into an ocean of water. You can turn something that is inherently quantum mechanical into, in point of fact, what we observe, a cup of water. Or in one more analogy, you can turn binary language, which is the chunky stuff, the A sub alpha, or A sub A rather, you can turn binary language into Microsoft Word. Okay, so it might not work out so well for you that way, but effectively what you've done is to turn chunky objects into continuous form, into field objects. Okay. Now here what we do is just to demonstrate that the Hamiltonian that we're associating with quantum mechanical systems can actually be derived directly from everything that we've been talking about. And we're gonna skip through this, but okay, so this is one of the big kicks about everything that I've been saying. If you give me one of our particles, like a proton, and I turn that into a matrix, like this chi sub I here, I can then use this commutator stuff in order to turn that chunky proton into a proton field. And in particular, the field of the proton we're talking about is its spatial arrangement in space. This X, or chi sub I of t, is its spatial arrangement, okay? How does it smooth itself out in space, or how does it re-chunkify itself according to a continuous time variable? But we didn't have to do anything more than integrate. So what we did here was to perform that integration. And the way that integration actually looks is an extension of what we would call Newton's second law. So you see, there's a location, namely chi sub I. There is a momentum, rho sub j, and then there's a force, F sub k. Those are the chunky things that we would normally associate with your initial position, your initial momentum, and the initial forces acting on the system. So Newton's second law. the way it's written here is so that it will give you how does that particle move through space. The space we're dealing with is the space you see right around you. And the time, how it's, what time is it using to move? That's a continuous parameter as well. So this has turned your corn, your ear of corn, into your field of corn. And you can track how is the corn moving as a wave through the system. That's what the X sub I on the left-hand side represents. It represents a continuous macroscopic way of seeing the particle system. And then the particle system, the chunky particle system, is really represented on the right-hand side of the equation, with where is it, how fast is it moving, and what are the chunky forces acting on it. So in other words, we recovered Newton's laws. We'll get to gravity, Newton's third law, in the next lecture, if I'm invited back. It's a random commercial again. So really, that's what I have. All of this stuff that remains here is really about going into greater detail about how to perform integration. And I'm always asking myself this question: are we done yet? Are we ever done? No, this keeps going. On and on and on. Do you know how much physics there is to show it? Okay, so you get it. But what we can say is that everything that we've just demonstrated here, the reason why I'm walking you through it like this is because you won't be able to understand what I'm going to tell you about quantum gravity if you don't understand this. And that's the power here. The power here is that when we do talk about quantum gravity, then we have a very easy way of understanding how to manipulate it. Because we understand what quantum gravity is at the subatomic level, at the most basic level of particles that we currently do not have except for string theory and loop quantum gravity. And inevitably, when we do introduce quantum gravity, we'll go through what parts of string theory actually are correct and what parts of loop quantum gravity actually are correct. It's nice to know that there's some good parts in both of them that actually come out of our version of quantum gravity. So yeah, I mean, if you guys have any comments, questions, or criticisms, please let them roll like the waves.
Well, so Ken, I think that means we should probably move into our Q&A session then, right?
Yes.
Okay, yes. Before we do that though, let me stop your screen share.
Okay.
And so I want to put this on, oops, sorry about that. Okay, I'll stop the screen share there, and I will put this on gallery view. I hit the wrong button. And everyone, please give Mr. Kenneth Griggs an enormous hand for a tremendous presentation. That was a full hour of super intense math. So thank you, sir. Thank you very much.
I'm sorry.
Oh no, it's wonderful. That's wonderful material. Okay, well, so let me see. In terms of questions, let me see who would like to go first. And we actually, I'm really excited. We had David Chester show up too, which was really cool. So let me see. Who would like to? Remy, go for it, sir. Oh, sorry about that. Okay.
Can you hear me now?
I can hear you, yes.
Thanks, Kenneth. I can't say I understood much of that, maybe 1% of it. I think it needs to be, graduate level physics. But I just got a question for you. Do you believe do you believe in warp drives, faster than light, Maxwell demons, all this stuff which is stock and trade of this forum? Or is it just going to be sort of another sort of brick in the wall where the establishments are saying no, and we're going to make it so complicated that you can't understand it and you can't answer back?
That's an excellent question. Now I don't know about I know that the warp drive stuff, but you said something about demons. I didn't quite understand that.
Oh, Maxwell's.
Oh, Maxwell's demons. Oh, okay, I gotcha. Thank you. Yeah. So the answer is yes. Okay. Yes, we explain warp drive. Yes, we demonstrate how quantum gravity actually enables you to create Alcubierre warp drive. We explain what we mean by negative energy, and all of it is as simple. Okay, I know that this was a lot of math at you right up front, but I challenge you to just read through the description again. If Tim can upload the presentation, which I'm probably sure he will, but just to walk through it again in your own time, look at some of the sources, and I guarantee you, you're going to discover very quickly that this math is beyond easy. But the point there is, because the math is easy, then that enables us to actually describe and to define what the heck do we mean by warp drive in an equally easy manner. This is not difficult.
I'm having trouble linking this to physics we know. I mean,
Okay.
can you give them what I've got in my head? I've got, say, something like a scattering process. So I've got on the left-hand side and I've got on the right-hand side.
Yes.
And you're simply, what you're saying, it's almost like a linguistic manipulation. You're manipulating these symbols in all the permutations they could possibly take on the left-hand side and on the right-hand side. And you're saying it's only meaningful if there are some underlying rules. And when you get these rules, you suddenly output things like conservation of energy, covariance, and things like that. That's essentially what you're saying, isn't it?
Yes, I think it's more sophisticated than that. But yeah, I mean, in a nutshell, what we're saying is that the general principle that underlies all of our equations is the principle of general covariance. And we realize that from this general principle, we can derive quantum field theories, we can derive general relativity theory.
Yeah, but when you say covariance, straight away, isn't that a limiting belief? Because when you say covariance, that's automatically meaning you can't travel faster than the speed of light.
No, not at all. Not at all. That's not what it means. No.
What is covariance then?
So what covariance is saying is that effectively all of our systems do not have a predefined coordinate system. That the coordinates, and so that
I agree. It's the usual definition of diffeomorphisms and all that. Yeah,
that's right.
Continuously differentiable manifolds and all this, and how you can relate to one aspect of physics or one coordinate system to another. Yeah, that's the usual definition of covariance. Yeah.
That's
okay.
Right. And so just based, sorry, go on.
What new is coming out of this? I mean, this is just not to be dismissive. I mean, I don't know if you saw in the chat, but I gave Feynman's recollections would be the right words, on when he moved from undergraduate to graduate school, and suddenly had to relearn everything.
Yes.
So instead of using this, say, forces and do all this, he had to learn things the variation of way, and he took all his homework and converted it to just a sort of Newtonian understanding. He couldn't see the point of it, and then the penny dropped. And then he saw the utility of variational methods. It was much better. It was a much more elegant system, which allowed you to do more things. That's what you're trying to say, isn't it? Is that what you're trying to say?
I mean, I basically say that, yes, we are finding a different mathematical description that actually gets to the heart of what the heck do we mean by measurement in the first place. I think that a lot of the things that we've been doing, sorry, go on.
Yeah, that's important. Yeah, sorry, I'm just wittering away. Yeah, that's important. Yeah, the measurement problem. Yeah.
And so
the loss of entanglements. How things become entangled with the environment and so forth. Yeah, these things are really well understood. Yeah.
That's right. And in fact, in this different way of seeing it, using combinatorics, we're able to define is what the heck do we, I mean, obviously in quantum mechanics, we can define very easily what we mean by entanglement. But here we're actually able to define it in a very different way. And in this particular different way, the edges that exist between our vertices, for example, in our graphs, which we really didn't introduce structurally here. We just sort of, mark at it.
But about Feynman diagrams, when you talk about vertices, is that what you mean? Feynman diagrams?
No, not exactly those vertices, although it still does apply there too. Generally, a Feynman, so when we were talking about the cyclic generator function, the thing I was calling GT, and then the permutation generating function, the thing I was calling PT. The cyclic generating function is what we utilize in every imaginable way in Phoenix, because it is a sort of a binary language, or what do we call it, the game set. It's where you put all the little pieces together and you build whatever.
You're saying kind of like a foundational building block, essentially.
Yeah,
right?
exactly.
You mean like Lego?
Or like a Jenga tower, exactly. And the reason why I mention that is because the way we do field theory is that we don't consider that there are any actual relevant building blocks, sort of fields. And what Phoenix is saying is that's not true. There are actually sort of a binary system of building blocks that can generate a field. And the reason why that's so important here is because with Feynman diagrams, we're talking about a field representation of particle physics. Phoenix can give you that. But what we're really talking about in Phoenix is literally a Jenga tower construction, where we're not dealing with fields on that level. We're dealing with, little Hershey's Kisses, as opposed to, Willy Wonka's vat of chocolate. But the Feynman process utilizes permutations all over the place in order to generate our understanding of modern particle fields. But we're showing you that no, there's a more basic language structure, a more basic alphabet. So the idea is, how do you go between the two so that we can actually generate, once again, Feynman diagrams? But we start off with a basic building block system.
Well, what are your deliverables? Sorry, Karin. What are your deliverables? Where are you taking this? Speaking from a sort of physics engineering background.
Sure.
Is the utility of this? What are you gaining from this? I know you said it's a more simple description.
That's the first, yeah. That's a critical part. Well, the reason why, sort of this particular approach, it's like asking, how do I want to understand how Microsoft Word works? Do I want to understand it by using the program over and over and over, or do I want to go to the code? So if someone could have handed you, that's probably not going to help either, since there's, a billion lines of code. But nevertheless, if you really wanted to understand the system, you're not going to try to figure it out by using Microsoft. You're going to try to understand it by reading the code. So what we're providing is the actual code. And what we're also demonstrating is that the code gives you the most efficient, obviously that's why we try to get down to the smaller parts, but the most efficient language for creating this thing that we call, Microsoft Office, or for this thing we call a quantum field, which we do not have.
To use your analogy, between Microsoft Word and the computer program itself, using it would be like an experiment.
Or a language, the most efficient language for that language. Is that what you just said?
Okay, can you say that again?
Oh, sorry. That was Bernie. But Bernie, can you repeat that? I think he's saying the most efficient language to describe the basic concepts. I think that's what Bernie's asking, right?
It just sounded like you used the definition of a word to describe it. That's
Anyway, I'll get back to the point I was making. To me, your analogy with Word, say, the person who finds out how it works is like the experimenter. Yeah, the person looking into it is like the theoretician looking into the code. Yeah, is that a good analogy?
Oh, no. We're also saying that the experimenter can find this too. Our experiments are not limited to quantum fields. That's my, if you want to have another sort of takeaway from this, there are actually more efficient mechanisms for digging up why particles do what they do, other than the means that we use to do it now, which are, of course, our particle accelerators. In other words, our field scattering experiments. This gives you another way of arriving at exactly those same conclusions, or whatever, wherever nature is leading you, looking at the building blocks themselves, as opposed to, someone giving you the Lego, the museum of Lego statues.
Is there anything that you might rule out? Because, there's a lot of experimentalists here, and they're thinking, oh God, more theory, having to sit through lectures. And one of the things we've all sort of come across is when the teacher says, you can't do that because I said you can't do that, and you find some way around it, that they think they have an all-encompassing theory, but there's a hole in it somewhere, and the theory breaks down.
Yeah. So, so the idea that a good example of what we're talking about with Phoenix is that the idea of the speed of an object that we represent in relativity theory as beta, right? Your speed divided by the speed. Right. So that concept for us is a thermodynamic concept. So it's like temperature. In other words, it doesn't really live at the level of the true quantum. It doesn't live at the level of an alphabet. It is how you scale from your alphabet into, you know, the creation of a word or the creation of a sentence or whatever. But it's not a fundamental thing. And where that lands us is in complete agreement with why relativity theory is not at the same level as quantum mechanics. Quantum mechanics is at a deeper level than Einstein's general theory of relativity. And so this completely agrees, because the marker, the tool that enables you to explore relativity theory, namely beta, in our case, beta is Z. So every time you see a Z, that's beta for us. So but it only lives as a continuous variable that takes you from a microcanonical world into a macrocanonical world. But that's where it doesn't really have a true existence at the most fundamental level.
I think
in other words, at the most fundamental level, our proton, for example, does not have a relativistic speed. It has a momentum. It's got a chunky quantum mechanical momentum, but no continuous relativistic speed. And that's a huge, huge understanding. Yeah.
I would probably try to break it down into sort of primers for different levels. Because I can just about connect with what you're saying, you know, at graduate level, but to break it down for, say, engineers and people not even at university level, it's not really communicating. I've seen this many times with theoreticians.
So
they're in an ivory tower, yeah?
Okay, so a way of making it communicate is this. The space you see around you, I mean, I think everybody in this room probably agrees, but the space you see around you is not continuous. It's chunky. And it's even more dramatic than that. So when we talk about the number of vertices that a particle has, what we're really saying are all of the true degrees of freedom that particles can possess. But what that means is that in the universe around you, the number of degrees of freedom that you think exists is much, much smaller than what you think you're experiencing. It's more or less a holographic idea. But what that means is that space itself can actually bubble. Space itself can actually, the chunky part of space can be made to resonate with each other parts of the chunky part to form regions of space that actually look like bubbles to us at our level, you know, under certain circumstances. But the idea there is that there's a whole different way of understanding space, such that space itself, for example, can be described by fluid dynamics, and that fluid dynamics can actually create turbulence. Space isn't always laminar, okay? And you can utilize that turbulence of space in order to, for example, undo gravity. Because what we mean by gravity is really how space and matter are actually interacting with each other. But if I can resonate that any structure in the space, then I can get space to phase. I can get it to change from the form that we commonly think about, which is smooth and laminar, into something that looks much more chaotic. And when it does that, gravity itself breaks down. So that's an example, I think, of.
Okay.
I would pitch it as sort of good engineers level, good graduate student level. You need to sort of communicate the ideas before they taken up.
Yeah. Well, Remy, let me jump in. I want to try and go to Jeremy Reese if it's okay, because we're starting to get some questions piling up. So let me go to Jeremy Reese next.
Jeremy?
Hey Ken, welcome back to the Alien Scientist channel, and thank you for that presentation.
Well, thanks for inviting.
This is did Wolfram inspire you at all to come forward and share more of your ideas? Because I've got a couple good comments from one of my friends, Carl Cartesian. He's been into my channel since the Hubbard brothers and that whole thing with theories of everything, and he's been big on following Wolfram's work. He says, when you say these cycle generating functions, is that in any way analogous to Wolfram's concept for slicing the multi-wave hypergraph as a measurement of time?
Absolutely. The beauty about Wolfram is that, he's been, attempting to divine, how do we, algorithmically talk about space, time, and matter, and then hopefully, quantum mechanics and relativity theory emerge from it. And so, yeah, the notion of, slicing up he's going to misrepresent and call it a multiverse, but slicing up his causal universe into these variations or into these slices is what generates special relativity theory. Is really, in fact, kind of what we're talking about, definitely. But yes, I was certainly inspired by his work. Because that's exactly the conclusion that we're coming to. The universe is an algorithm, and that algorithm has well-defined lines of code. Those well-defined lines of code encompass what we call the laws of nature. And if you want to understand structurally how nature can become altered or transformed, because you're looking at it, through a quantum mechanical way of seeing it, into something slightly different, then both of these approaches are trying to reach that end. So our algorithm is really the generating function. It's what we would call the program. Each line of code of the program is marked by z squared, z cubed, each of the different parts of that generating function. And each one of those parts talk to each other. So the lines of code can spit out a piece of information that goes to the next line, and it can spit it right back up. So it is a program as well as Wolfram is playing with, definitely, or more than playing with, studying.
So now describe more about how entanglement works its way into the picture, because you had mentioned before, we talked about spatial and temporal entanglement. And what does it mean when things are you have an entangled system, and then what does it mean to have when systems obviously become disentangled or entangled elsewhere? And kind of, I don't know, I kind of want to understand more about this temporal and spatial entanglement and how it works into your theories and that you just showed.
Okay, so the easiest way I think of thinking about it is in terms of our graphs. And the question is, I didn't really show you a picture of, and you've seen too many of them, but I didn't show it generally for everybody what we mean by a graph, which is just a series of vertices that are connected through edges. And sometimes the vertices themselves can be connected to themselves to form loops or arrows. But the point is that the vertices represent all of the different configurations of information on a network. Okay? And those different configurations of information can actually be conjoined with each other. So, for example, if you look at eddies that are formed in a fluid, they don't just sit by themselves. After some time, the eddies will begin to congeal, and sometimes they may even begin to fall apart. Information flows in exactly the same way across any network. There's going to be sometimes disturbances between different information flows. The question is, can that actually be codified? And what we're saying here is, yes, absolutely it can. Our evolution equation that we said there's a transformation on some system and it becomes another system with a transformation nature, that's an evolution equation. But our evolution equation just marks out how vertices can be conjoined with each other over a marker of time. What's allowed and what's not allowed. So the conjoining of vertices to form what we call a graph. Okay, that conjoining is what we mean by those vertices are entangled. So if you've seen our diagram of a proton, it has two loops. It has one loop in the, so there are three vertices, and they're all connected in a line. There's two loops, two vertices on either side that have two loops on them, and one vertex in the middle that has a single loop on it. And that particular structure is what we call a proton. But what it's really showing is that you have three parts of information flow that are somehow hooked up to each other, and they don't want to let each other go. And the way we see that even more, and it looks like a dumbbell with a loop in the middle, but the point is that what you're really seeing is two up quarks, the two things on the ends that have two loops on them, and then a down quark, the thing in the middle that has one loop on it. But what you find is that is a stable information configuration. Now, what we can do when if I'm invited back, is to explicitly show you a network and how the information flowing on that network resembles these different patterns of information that I'm talking about, like the proton and the electron and the neutrino, etc. And then how those things are allowed to combine and disconnect from each other, and that's what we call particle reactions in physics. So when we do a calculation of particle reactions, we don't do long, drawn-out scattering theory processes. We don't. All we do is you tell me what the configuration is that you initially start with, let's just say a proton, or let's say a neutron. And then this will, in one step, bring you to a proton and a W minus, or a chi minus particle. So it's a very, very simple, efficient, and elegant methodology for establishing why particles change. Why do they combine up or disintegrate and break apart? And then when they do break apart, why do some things remain stable? They don't seem to break apart anymore. And it's because it's not allowed in this, in the evolution equation. It's just, there is no evolutionary step that will take a proton into anything but a proton. So if you go out to the regular quantum field theory world, where we're actually using Feynman diagrams, and we're using quantum electrodynamics, and then quantum thermodynamics, and then quantum, the extension of electrodynamics into the weak system. But the point is, if you do that, there's a contradiction that arises. We have proton decay, and we can't explain it. We've literally set up experiments all across the world for billions of dollars since the 1970s that cannot tell you why the proton is stable. All it can do is to keep pushing back how long the proton lives. I think at this point we're like 10 to the 40th years or something. So the idea is this one explicitly says in one step, the proton is stable. You can't break it apart. There's nothing you can do. It's going to be sticking. We can even go forward to show you how the proton and the neutron can actually bind together and how they can fall apart after they bound together. In other words, nuclear theory. So we have very explicit representation of how you get these other manifestations, whether it's the atom, whether it's the nucleus, whether it's, muons possibly being emitted by nucleons, and what effect that has on the nucleus, etc. But we can get these explicit representations in very, very small ways from this Phoenix way of looking at it.
Now, Ken, if I could jump in really quick, and this is something Remy had asked chat, but I'm also interested. What are some of the predictions, I guess, that Phoenix theory would make? Because I know there are many, and I think this is one of the reasons that people get so excited about it. What are some of the predictions that you might offer? I mean, especially in terms of in terms of propulsion and the things that we look at. What do you think some of the most exciting things that have jumped out at you are?
Oh God, there really so many. Okay. So one of the big ones for me, of course, has to do with warp drive. Sort of how I started this whole battle, from me in the 1980s. But the biggie about warp drive is how do you establish and then ramp up, turn it off, and what is it? How do you make it? And when we go to something like Alcubierre, who did just an unbelievable thing that we didn't even think could be done to general relativity theory. And you look at it a little bit more closely, and you find that it's swamped with what we call negative energy. And it's basically dying for, general relativity that is dying for an explanation of negative energy. And so what Phoenix does so beautifully well is to establish what do you mean by negative energy on a quantum level. Now, when we think about that concept, we think about the Casimir effect, which is an explicit way of really getting quantum mechanics to give you negative energy and negative energy states. And so what we can demonstrate, of course, is that the Casimir effect is true. That's a given. But we can demonstrate how do you continue to derive negative energy states of particle systems. What does that mean in terms of black holes? What are you actually doing? Does negative energy get a chance to leak across an event horizon? Does positive energy, survivable inside of an event horizon? So we have all of these different manifestations. One of the modern string theory things that people are working on, like Douglas Stanford out at Stanford, but one of the things that they're working on is how do you describe the entropy of black holes such that that entropy not only goes up, it hits a boundary and starts to come down, so that entropy itself is not a problem in trying to connect string theory to black holes. And so what we're able to demonstrate is that trick that they're performing with the entropy becoming stabilized and then coming down, I think we call it the page curve, is actually something that we predict as well. The most important thing, I think, sort of running through my head of the stuff, is what Juan Maldacena was doing in the 1990s, called the anti-de Sitter space / conformal field theory duality, for which he conjectures that gravity can be divined from conformal field theories, i.e. quantum mechanical systems, by virtue of this duality that he discovered between the two theories. The problem with his duality is not that it doesn't work, it absolutely works. The problem is that they can't prove it. There's nothing about quantum field theory or general relativity or even string theory that enables for them to make that final link that says, okay, we've proven it. We can see it happens, but we've actually mathematically demonstrated it. That's what I mean by proof. And so what Phoenix does is actually show you where that proof comes from. Okay, and that's our coup de grace when it comes to modern physics, at least, is to demonstrate that yes, exactly what Juan was saying is true. Exactly what Alcubierre was predicting is doable, and this is how you do it. Okay, so we didn't just stop at the front door of understanding Alcubierre. What we're actually saying with Alcubierre is that there are particle systems that will generate a stable warp field, and that stable warp field will travel with this speed. Okay, or you can boost it with these types of particles to travel a lot faster. And that's the beauty about it. You can get negative energy states, which is what's required in that system, from these processes that ordinary quantum mechanical systems or theories will not easily give you, right? Because we seem to have this boundary of the no negative energy. But we demonstrate what the hell is negative energy, and how is it sometimes confusing that some systems can actually have two types of energy. One is the energy that you and I are made out of, which seems to be positive energy. And then it is completely transformable into another system that has negative energy. Okay, and that transformation alone gives that particle the ability to function as the negative energy that Alcubierre's warp drive requires. So that's what we're also saying. So there's a lot. And where we are right now is quantum chaos theory. Really being able to measure how space itself phase changes. So one of the things that comes to mind is Star Trek Voyager. There was an episode where space became chaotic. And that's really the only connection here. So hey, even in Star Trek Voyager, they talk about it, but it's an important concept. That if you make space around you phase into being a chaotic version of space, gravity goes away. It just disappears. There is no gravity. Okay, so whatever vehicle you're trying to fly, will just simply float. You don't have to worry about inertial dampeners and any of those other ingenious things, I might add. But they're not necessary once you've controlled how gravity is actually working in your system. We can even go to the point of how do you produce antimatter? Not just antimatter, the $1 billion for 10 atoms that we're doing today. We're talking about mass production. We even encounter, I don't know why, maybe we do this in nuclear theory, but, we harness antimatter from nuclei, for example, right? How do we make that nucleus actually give us just the maximal amount of antimatter, whether it's positrons or whether it's, and the beauty about using nuclear matter or nucleus is that it's a safe thing to hold in your hand. It's not going to blow up because it's not antimatter. It's producing antimatter, but it's functioning as a battery, right? It's holding the antimatter in it, and it's a safe holding vessel. You touch it, you don't explode. But this stuff will produce it, right? And everybody who does nuclear science knows the atoms that produce positrons, for example. But that's what we're talking about. A safe way of both storing antimatter, getting it to give us the antimatter, and then using the antimatter for whatever purpose we so deem fit. So, but that's an excellent question. Thank you.
Wonderful. Well, thank you as well. Let me go to. Let me see. I want to go to David Chester.
David.
Let me see.
How's it going?
Oh, perfect.
Great. How you doing?
Pretty good. Yeah, so my main question was if this theory is a scattering theory, then can it compute scattering amplitudes? And if so, would the methods provided by your theory be perturbative or non-perturbative?
The way that we produce the scattering amplitudes is in a perturbative way. So, for example, when you saw our exponential of the cyclic generating function, there are two ways of actually turning that exponential of the cyclic generator, e to the gt, we call it. But there are two ways of really dealing with that. One is in a completely perturbative way, for which your series goes to infinity, and the other is actually in a very finite way. So what we explore is both. But when we're dealing explicitly with scattering amplitudes, so we can do the harmonic analysis of those amplitudes, and we get a perturbative series that corresponds to it. Yes. But so, again, we can do it in the other way as well.
So what has been computed so far? Like, can you do tree level stuff, or like one loop, or like how many loop orders and what theories like have you pushed this to yet?
Let me put it this way. What we can show you is the actual, how do you derive the scattering amplitude based on an infinite series. So we can demonstrate that. I could probably just send that to you. And what we can also demonstrate is how we don't want to do that at all, right? There are other ways of computing the field, whatever we're doing with the field. So if we're computing the spatial position, or we're computing the energy level, or whatever, there's actually a very solid, small way of doing that. But one of the important understandings is that the universe does not have an infinite number of vertices. And what's important in that statement, in this way of doing it, in other words, is the generating function actually infinite, right? And the generating function that we're turning to is the cyclic generating function, the GT, the one that's establishing all of the cycles that all of the alphabet that system has. So, but when you're creating a permutation generating function, you exponentiate the cyclic. But the point here is that if you establish that the cyclic generating function is itself not infinite, that it is a finite generating function, and we can show you why that's the case. But if you can establish that the cyclic generating function is finite, we can also then show you that the permutation generating function is equally finite. And the simplest way is to exponentiate the cyclic and get infinite terms, but that's not the appropriate way. It's not the best way. It's not the way that really you want to use. The way to the simple answer is that there's a finite extension of the cyclic generating function that we call the permutation generating function. And then we use the finite one in order to get the answer.
So it sounds like what you're saying is we're not interested in scattering amplitudes then.
Not the way that we do it in normal field theory. Yeah, that's what I would say. But there is a quicker, easier, more efficient way of getting the actual answer. Yes.
But wait, the scattering amplitude is an answer to a physics problem. So
yes, it is.
You're saying, I was asking, how do you get the answer to the physics problem? And you were saying that you basically aren't interested in that problem. It's not, that's just how I'm interpreting what you're saying. I don't know.
Right. No. What I'm saying is that there's a more efficient way of getting the answer. The first thing you want to resolve in dealing with anything in Phoenix is how big is your matrix that you're dealing with. So normally when we think about the universe around us, we're like, okay, well, maybe it's made out of vertices, and maybe at the subatomic level, the vertices are all connected up in some funky way. The idea is how many vertices are you really dealing with? And does that constraint actually tell you something about the universe that we live in? And what Phoenix says, when we show you what we mean by quantum gravity, is that the number of vertices is a theoretical boundary to the universe that we live in. There are certain, in other words, you can construct different universes by virtue of the number of vertices that you're dealing with. How big is your matrix that you're working with? And what we establish is that the points of space around you are really a bag of vertices. There's a finite, distinct number of vertices that every point in space around you has. The way we might say that, another way of saying that, is that every point in space has certain degrees of freedom, right? Certain quantum mechanical degrees of freedom. And those degrees of freedom for every point in space around you is fixed. And the way we fix it is at the number of vertices. So once you establish the fix of the number of points around you, if you know a way or a mechanism, and we do, for establishing how many vertices, how many degrees of freedom every point in space actually has, then that completely determines how gravity acts. It completely determines how the strong nuclear force acts. All of them get bound up into that one thing. What is gravity? What's the gravitational constant? What's the speed of light? What's Planck's constant? They're all bound up in knowing exactly how many vertices space has. So the beauty about that trick for us is, or that determination at least, is that when we look at how Phoenix describes nuclear theory, and we ask the question, what does, indium, 54 become, right? We find that if the number of vertices of space gets altered even by the least, even by one, then those answers rapidly change. And so we can measure how many vertices our space is simply by looking at all of our measurements of nuclear decays. What does, iron 56 decay into? Well, it doesn't. Well, that's important. What does helium 3 decay into? Well, it kind of does. So, but we can establish exactly by virtue of nuclear decay how many vertices, how many degrees of freedom every point in space has. And then we can show that actual number gives rise to other calculations, or rather other determinations about physics. For example, the gravitational constant. For example, the speed of light. For example, Planck's constant. And then demonstrate with those things, how the universe evolves in this limited number of vertices.
Okay, yeah, I mean, the work of Andrew Strominger shows that the numbers of degrees of freedom are increasing over time due to the expansion of the universe. And it sounded like you were saying that the material properties change depending on, I don't know. Yeah, and anyways, best of luck.
Well, thank you. I appreciate that. It's good to see you again. Okay, Tim, I can't hear you.
I'm sorry about that. I hit the wrong button. I muted myself instead of. Okay, yeah, I was going to say thank you to David as well. So let me see. John Schultz had a question. John, do you want to go? Let me ask him to unmute here. And he was asking about the Alcubierre warp drive. Hi, John.
Hi, John.
Hi. Yeah, so the Alcubierre warp drive that you mentioned maybe I just misheard. I'm not a physicist or anything.
Sure.
I'm just a amateur fan. But you mentioned that there's some sort of you have ideas on containing stable antimatter, if I understood correctly, instead of what Michael Perrone mentioned in the comments regarding just bombarding it with protons. Based on what your work and your ideas, do you have any ideas how you would go about creating an experiment to test if you can create even the smallest measurable amount of antimatter that's stable, or that's contained in a stable manner in whatever way? I don't know. That's the extent of what I don't know how to phrase that better, unfortunately. So does that question make sense?
Oh, it does make sense. And obviously, there's a lot to your question. But the idea that I'm gathering, certainly from what you're saying, is in particular about antimatter, and in particular about either stabilizing antimatter or finding a way of producing it in such a way that it can be, utilized to create the warp drive. One of the things that Jeremy and I worked on and discussed a while back was an experiment for which the way that I think we like to put it was you can float stone. And so the idea is, let me put it in this context, that we have, for example, discovered in the last 10 years that silicates are a beautiful way of taking muons and doing two things with them. One is slowing them down such that you can force muons to become atomic, and two, of producing streams of more, in this case, anti-muons. So the effect of silicate or stone is that it has this unbelievable property of doing two things that we would need in order to create antimatter atoms, or in order to create antimatter that's traveling slow enough, which is why it can create atomic forms. It's traveling slow enough to be usable to us. And so the idea behind what Jeremy and I were talking about was utilizing Phoenix's understanding of creating chaotic space, a space for which gravity has a hard time doing anything relevant, using stone. And in that type of an experiment, what you would note is that the stone would actually, under the right conditions, float. And that floating stone is something that is not terribly difficult to do experimentally in using Phoenix. It's difficult if you want to get that same thing if you're using other materials like wood or like metal or like carbon-based materials. And so, again, the experiments for the last 10 years have already demonstrated that silicates, like, silicon dioxide, et cetera, have a beautiful property when it comes to those two properties. The first is slowing down muons when they are produced using the silicate. And the second is that when you use anti-muons, you can actually get the silicate to help generate more anti-muons. So it produces more anti-muons than what impinged it in the first place. So the idea there is creating antimatter that's usable. That's the whole point of that. And once you have usable antimatter, either because it's bound in an atomic structure or because it's just traveling at such a slow rate that you can actually, not, burn a hole through whatever your device is because the muons are really traveling too quickly. But the idea is that it's usable anti-muons. And again, what Jeremy and I were working on is the idea of turning that into an experiment for which you can then show that stone itself has less gravity. It can be lifted very easily under these kinds of conditions. So I hope I've actually answered your question, because I think it was a very marvelous and insightful question.
Yeah, thanks, Ken. That's brilliant. Just to add to that question, if I may, do you have any ETA, estimated time of arrival when you and Jeremy will actually be doing that experiment? Because that will be super interesting to check out the feedback on that.
Well, the beautiful thing about it now is that Jeremy has a whole team together that work exclusively on experimentation. So I'm not on that team only because I work almost exclusively on theory. So I have to apologize about that. But I'm sort of saying that, you know, in terms of his team, this would be the kind of an experiment that I know that they would love working on. I haven't handed off all of the material to them in terms of everything they need to probably, you know, really take it full force to get started. So that's on my end to be able to give that information, all of it over to them. But nevertheless, they would be the ones working on that. So again, great question.
Yeah, thank you, Kim. Very informative. Thanks.
You're welcome.
Yeah, and thank you, John, as well. Okay, so let me see. We have about 5 minutes left. Who else? I think Michael Perrone had a couple of questions. Michael, did you want to ask?
Hey, Mike.
Hey there. No, I don't think I did.
Oh, okay. You were asking about you were saying proton stability, basically, but
that was I forget where that came up, but I don't think
okay.
That was another Michael.
Oh, okay. No worries. So who else has questions? We've got just about 5 minutes left in our Q&A session.
Come on.
Well, and you've gone, Ken, you've gone through so much, right? I mean, that's the thing. This is intense. I would love to have you back to talk about predictions and stuff. I think you were talking about like doing maybe a follow-up session in the future. Now, I should mention that we are virtually crashing the Tesla Tech conference in our next session, so that's going to be a little chaotic. Like half, something like half the people who attend this conference are going to Tesla Tech, and so
Wow.
Mark said, "Well, let's broadcast live from it," and I was like, "Well, that's actually kind of the crazy thing that we would do." So yeah.
Hey, Tim.
Yeah, Michael, did you have a question?
Yeah, I'm kind of curious. There are a couple of statements you made, Ken, that made me think kind of more philosophical questions.
Sure, please.
So, do you think God is a programmer, or do you think he's a Wall Street gambler?
That's good. I like that. Okay. The way I like to think about it, it's that's a good one. I'm gonna say I prefer to think about God in terms of the Matrix movie.
So, well, he's a programmer then, right?
That's right. So God is a programmer, and you know whether you think that programmer is the architect or is what is her name? The architect and the what's our black woman?
Yeah, the old lady. The
yes.
She, I figured so.
Yeah. So yeah, I'm just, I guess I'm convinced. Now, in some ways, the programmer concept is possibly, obviously, a lot larger than any movie does it credit. But nevertheless, this whole way of seeing this as a program, we can literally map everything we just talked about with combinatorics directly to programming. So everything we've talked about with particle physics or with scattering theory or with relativity theory, every foundational thing that allows us to think about the universe in some equation can be mapped directly to programs, to lines of code. And those lines of code are in fact what Stephen Wolfram is talking about, but we have this other way of seeing it. So we can perform derivatives on lines of code, integrals on lines of code, so everything literally that I just said, scatterings of lines of code, everything that we've just been talking about applies directly to computer science.
So
you're going to ask it for a simulation, right? That's the next. That's the next step. Is always simulation. Yeah.
I have a little background in doing scatter experiments. One example that comes to mind is what's called X-ray diffraction.
Yes.
Diffractometer. It's basically you take a crystal and you grind it into a powder, and you put it in this thing, and you shoot an X-ray at it, and you move it, basically rotate it, and then it creates a little spectrum. Okay, and you can tell the interatomic distances and the angles between the different vertices in the crystal. And that kind of stuff. That's an example. Another example I have experienced is a optical scatterometer.
Okay.
Where you have a laser that pointing straight down, and it has a quad sensor in the back, optical sensor.
Okay.
And with that device, you look at what's called specular light, which is straight back. And you can tell the type of defect, a bumper. Yeah. But then on the side, you have these other detectors that they basically measured the scatter light.
Yes.
You can measure the size laterally of the defect, but you can't tell the type.
Okay.
You can only tell that with the specular.
Okay.
Now, the reason I use these two examples is they both have one thing in common. They're limited to the field of view.
Yes.
Okay. So my question is, it's as you described, aren't you missing everything outside your field of view?
Say that last part one more time.
When you assume that it's like a scattering effect, aren't you limiting your data to the field of view?
Yes, yeah, absolutely you are.
Outside.
Absolutely you are. That's exactly right. Yeah. So the way that we would,
So yeah, you can get a very good predictability, but you're not measuring outside the field of view. Basically, other things can affect you.
That's right.
So, for example, going back to the optical scatterometer experiment. Okay, one way you're assuming that your surface is flat.
Yes.
Okay, but if you add a little bit of bending in the surface that's bigger than the field of view of the light, right? That you're using, you'll see some deviation from what you would expect.
That's right.
So that's an example of what I'm talking about. You can't. There's other things out unless you have the big view.
That's right.
You can't tell if your little view is correct.
Well, that's exactly right. Yes, yes. And in fact, that's the beauty about what we demonstrate is that you can divide your system into as many different parts as you want. The sort of the smallest you want to go is to a 3-part system where you account for, the things that you can't see or adequately measure as a background, right? And that background is not, it's not a background that's not interactive. The background is totally interacting with both you, the measurer, and the system that you're trying to measure. And being able to then account for this trinary type of a measurement, right? Where you just really are thinking about you and the target, but you understand that there's a lot about the target that you're not seeing. There's a lot of interactions that are not being accounted for. And then there are a lot of interactions on you coming from some other source of background.
So that kind of comes to my fundamental question, which is, you're assuming, aren't you assuming the universe is 3-dimensional?
No, actually we're not. It's an interesting question, definitely. But what we demonstrate, and this is something that Jeremy was probably hinting at in terms of describing where our graphs come from, or where, how are they built off of networks, etc. But what you can easily demonstrate is that the universe is really acting as a 3-dimensional entity squashed down onto 2 dimensions. Not everything about the universe is 2-dimensional, but the vast majority of stuff about the universe is 2-dimensional. And
could it then be a 4-dimensional universe squashed down to 3 dimensions?
Well, it could be if you want to represent time in that way. So what we demonstrate is that time can be represented as its own entity. It is the thing about the universe that obviously allows the universe to change in any relevant way.
You're saying you have space-time without time?
Space-time about time. I would say you have space that is conjoining with time. But then there are some aspects of space that don't conjoin with time. So you can set space to be chaotic on its own. Or, and this is the interesting thing that I know Jeremy was also raising in many ways, or you can set time to be chaotic or have phase shifts all on its own. So you can actually really weed them apart or combine them back together again. In fact, one of the things that when Tim was mentioning the idea of things that you're really maybe proud about, or things that seem really relevant about how you're doing this work, one of the things that lands squarely on our plate is fluid dynamics, and the idea of
what's that last word you said? Something dynamics? I missed it.
Yeah, I'm sorry, fluid dynamics.
Oh, fluid dynamics.
Yeah, fluid dynamics. I'm sorry, and how fluid dynamics can actually be used. The Navier or Stokes equation, that they actually appear in this theory in a very relevant way as conjoining space and time to each other. And so the idea is utilizing, showing how, first of all, how is that connection even there, but also how do you use that connection in order to get time to do some strange things and space to do some strange things, devoid of each other. And so it allows us to then talk about black holes in a very specific way, or string theory applied to black holes, et cetera, et cetera, et cetera. And also to talk about how do you get a stone to float? Because effectively you're using a sort of notion of fluid dynamics of space itself, of space and time, in order to achieve this anti-gravity effect.
Cool. So when you say anti-gravity and antimatter, you're not interchanging them, are you?
No, not at all. Not at all. Not at all.
So,
Yeah,
I appreciate your answers, and I would like to continue our conversation, but I don't want to take up too much time.
I really appreciate it. Thank you. Thank you. Great.
Your email or something in the chat, that would be appreciated.
Okay, that's no problem.
Just my own feeling is I'm kind of an analog guy. I developed with thought. I learned C in 1982. Okay.
That's all right. That's also, I guess, when Fortran HX was out.
Digital programming is cool, but I still think the universe is analog.
It's all right. Thank you. Thank you. I really appreciate that.
Awesome. Well, okay, so let me do this. I want to put this back on gallery mode. Everyone, please put your hands together. Another big thank you for Mr. Kenneth Briggs and an enormous presentation. So let me see. Actually, I think Rani had Rani. Do you have a really quick? Oh, she just put her hand down. Okay. So what? Well, why don't we do this then?
I didn't have a question. It was just a clap.
Oh, I'm sorry about that. Sorry. Okay. Well, so let me see. Remy had said that he would like to do a quick presentation on. Let me see.
It's not highfalutin stuff. It's not at Ken's level, but.
Oh no, that's okay. Yeah. Well, Remy, would you like to go ahead, sir?
Sure. I'm just completing this paper. Where I believe I don't generally get involved in these areas. I'm more concerned with the engineering physics, but I'm continue finding that I'm bumping up against what they say in textbooks. So one of the things that I'm concerned about with electromagnetic propulsion is the idea that I can push against the 0 points. And there's this whole contention of whether this thing is real. Yes, so in quantum mechanics, you respond to differences in energy, or you use normal ordering to get rid of this embarrassing term.
Oh, and Remy, I'm sorry for interrupting. Your camera is really blurry. I'm not sure.
Yeah, it's deliberate.
Oh, that was deliberate. Oh, okay. I'm sorry.
You don't want to see me unshaven.
I don't mean to pressure you.
Okay, I'll try my best. Let's try. Yeah, it's a bit better.
Yeah, there we go.
So one of the things is whether this 0 point energy is real, is a thing. Yes. As I said, in quantum mechanics, you deal with differences in energy, and you can make it disappear with normal ordering. Yes. But then there's a problem with general relativity, where you've got this huge magnitude of 0-point energy, which if you put it into the stress energy tensor, well, even if it is isotropic, the idea that the pressure from it would cause terrific expansion of the universe. So what I do, I'll just share my screen and I'll show you what I'm working on at the moment. I'm just completing the paper. I've already put it up, but there's just a little section I want to sort out. So let me just share my screen. Bear with me. There we go, share screen. Now, screen 2, this one will do. I'll bring up this. So this is a section I'm literally editing at the moment. I'll take you back to the start of the paper. I'll give you a very quick overview of what I'm up to. Essentially, what I'm trying to do, I'm trying to justify 0-point energy, yeah? Because it's this ethereal quantity that nobody quite believes in. So in the first part of the paper, I just go back to Pauly and what he said, where he tried to cancel the 0 point from the boson fields with the fermion fields, and he came up with some measures to do this. And it so turns out that zero mass fields will dominate this expression. So you can forget the fermion fields, if I'm correct. I'm not only saying that, people like Matt Visser is saying the same thing. Okay, I just run through some basic general relativity. And then I come up to this point. How do we put something which is 10 to the 120 orders of magnitude in the stress energy tensor? And I'm saying that if you look at, say, just a particle, by analogy, it's not tensor density, it's just a particle. When you look at this here, can you see what I'm doing on the screen? Can you?
Oh,
Tim,
I'm sorry. No, I can't actually. All I can see is your face right now.
Bugger it. Can you see the screen at all? No?
No. Oh, that must be on your other machine.
Hang on. I haven't clicked share yet. I haven't clicked share.
Oh, there we go. Okay, so it started. There we go.
There we go. Okay, I'll just run it again. So here's the brief of the paper, what I'm up to. Just the introduction, recount what Pauly's saying when he's trying to get rid of this embarrassment. He's trying to get rid of this 0 point. He's trying to cancel it with the boson fields, with the fermion fields. But you can't do that. Yeah, it's the massless fields are gonna dominate. So basically, the 0 point is going to be determined by an expression like here in equation 5. So when you take it up to a cutoff, Matt Visser is saying you don't need a cutoff. He says it automatically falls out from Lorentz invariance. Yes, but let's just say you've got a cutoff of the Planck frequency, and when you run this integral, obviously you get very big numbers. You're getting something like 10 to the 111, 10 to the 113 joules per meter cubed. It's a huge quantity. And when you compare it to what the astronomers are measuring, they're getting an energy density of something like 10 to the -9 joules per meter cubed. So you've got something at least 10 to the 120 orders of magnitude difference. So what I'm trying to say, how can you possibly reconcile the vacuum energy of quantum field theories with the vacuum energy that's found in relativity? So by analogy, I appeal to the stress energy tensor for a particle. And what's telling here is, when you look at the term E there, which is the energy, you're dealing with, you're dealing with creation and ionization operations. So you're dealing with something which has got real energy, something exists. And the trouble with the 0 point, it computes something at 0 particle count. It's a fluctuation. It has no right, this is the tenet of what I'm saying, it has no right being present at the 0 order in the stress energy tensor. It doesn't make sense. So what I've done is just do a simple kind of Taylor expansion, polynomial expansion. It's two things at once. And then what I'm finding is that the 0 point energy can slot in at the second order term in the Taylor expansion, or third order in the Einstein constant, which is just the 8 pi g over c to the 4th, yes? And it appears to be just a bit of numerology. But when you do, you're finding that you're 10 to the minus 9 off, which is a hell of a lot better than 10 to the 120. Yeah, you're finding that your 0 point is a billion times too small, right? But I justify this. It's just a little bit of numerology at the moment, but it does have some method in the madness. Because if you look at this term in equation 12, you're dealing with a fluctuation. You're not dealing with this term here, where you're dealing with real energies, you know, on the ladder operations where you create a particle out of the vacuum. That's something very definite. You're dealing with fluctuations. So running through the paper, what I'm suggesting is that vacuum energy should be some 10 to the 9 orders of magnitude higher. You've got extra degrees of freedom. So in the paper, I suggest it might be string theory. When you get down to these levels, you're finding extra degrees of freedom. You're finding dimensions compactified. Yes, extra degrees of freedom. What I've suggested here, and I'm making a toy model, is just to say that there's an interaction term between the modes of the 0 points. So here's the 0 point for a particular mode at, say, a particular frequency. I'm saying it interacts with all the other modes, and you're going to have some interaction term like this. And I'm showing it in figure 2 here, where the idea that as the electromagnetic wave fluctuates for a particular frequency, it temporarily becomes a dipole. And all the other fields are doing the same thing as well. So it's experiencing an averaging of all the fields from all the other fluctuations. So there's an interaction term. So what I'm trying to do is just to set up a very simple toy model. It's just Newtonian at present. Yes, so it's just a mass, a damping term, and then in the equation 15, and then a stochastic term, which is the random fluctuation from 0 point. Now, it's giving me results over a narrow window, which is to be expected. So I was just looking at it this afternoon. I'm just looking at my notes here. And for a frequency range of some 10 to the 22 to 10 to the 25, it's giving me a number of about 1 billion. So you might say that's just numerology. So what I have to do with the model, I have to make it relativistic. And ironically, contradictorily, this works at lower frequencies. And the way I see that is that because the effective mass of your 0 point for that mode is so low, it's able to be accelerated very fast by the effective field of all the other modes. Yes, so it's achieving relativistic velocities. So it's counterintuitive. It's the other way around. And then at the other end, at the very high frequencies, well, it's because I'm using this Lorentz-Abrams formula for the radiation resistance. So I should be using the full Dirac model. So I'm going to toy around with these models, and I don't think it's entirely numerology. And I think you'll get this 10 to the 9 factor pop out across the range of frequencies, which have then established a direct link between the quantum vacuum or quantum field theories and general relativity. And once again, you don't put it in at the 0th order, you put it in the 2nd order. You put it in as a fluctuation. That's the only way it can make sense. So I might have hit upon something here. We shall see. Okay, so that I'll stop sharing the screen now. So that just brings my little point about what I'm saying about there might be a way that you can relate, get rid of this 10 to the 20 order magnitude, 120 order magnitude, which has been described as the most embarrassing problem in physics. Yes. Okay, that's it. So okay.
Okay. About that.
Okay, Michael, how you doing?
So, could you go back to your share screen?
Okay, let's go back to share screen.
You know, it almost sounds like that vacuum fluctuation that reminds me of the surface charge on a battery, right? Where it's a very large number for voltage, but you can't actually use it.
Could you go to the page before where you showed the fluctuation? Like a little, like a sign. There you go.
This one? Yeah.
Next page then.
Yeah, you have to speak up, Michael. You're a bit distant from the microphone. You're coming across a little bit low.
Can you go down one page further?
One page further.
Yeah.
Yep.
A little farther. It's on that page.
Further. Yeah.
There. Stop.
Okay.
Okay. So this is your fluctuation, correct?
Yeah. So if you imagine.
Okay. So now this is maybe it's totally out there, but I had this job once where I was making occupancy sensors, where you walk into the room and the light turns on. And,
yeah.
And one of the big problems.
Close to your microphone again. Sorry, you come muffled. Yeah.
Yeah. Michael, have you changed your mic lately? Usually it's pretty clear. Today it does sound a little muddled and you're kind of fading out.
Oh, okay. I haven't changed anything.
Huh.
So what I'm suggesting is in alternating current theory, when you have what's called the 0 point crossing, okay, which is at the point in the middle, where it goes positive to negative at 0, that's where the current is maximum. Okay, and so what happens is when you switch your light on, you don't want it to be on the wrong point on the AC cycle. You follow? Or it creates heat. It creates resistance. So what I'm suggesting is, don't you want to look at that 0 point? You're saying it's a derivative, correct?
I don't really see what you're getting at. I think we're sort of talking at cross purposes. I mean, there's no current because there's no flow of charges. What we're talking about are the fields. Yeah, the random fields and random fluctuations of the 0 point. Yeah, there's no particles. That's the point I'm making as well. You're dealing with 0 particle counts. It's a fluctuation. It has 0 average, but it has a standard deviation. Can't really see what you're saying with the analogy, but I'm trying to think it through. Right. I do know what you mean about
like you're thinking about the electric field and the magnetic field, how they're in 90 degrees out of phase. So when you hit the 0 here, there's another field.
I see what you're saying.
That's coming in and out of the page.
Yeah, I see what you're saying. So you're believing that I should be dealing with two fields. Yes, I should have an E field and a B field. That's what you're suggesting. Possibly. I mean, it's just a simple time model to give a ballpark. I'm just trying to find, this is where you get the B field from the creation operators. Yeah, I'll consider that. But if I remember, let me see. If I remember, the B field will be, is it C squared down on the magnitude of the E field?
You can also consider
yeah. I mean, if you take a plane wave, you'll have the E field equals C times B. So, what is it? Is that going around? Is it? I'll think about that one. I'll take that in and think about that. Yeah, so I'm sure it wouldn't be that difficult to put the magnetic field in. Yeah, I'll take that on board. Yeah, I'll take that on board. Thank you, Michael. I do agree. You've got a point there. Yeah.
I also have a quick thing to mention.
Okay.
Oh yeah, go for it, Michael.
Oh, Michael.
Oops, and he got me. There we go.
Yeah. So anyway, you also have to take into account that the measurements for vacuum in the presence of an atom, you have to take into account the vacuum energy of the self energy of the atom is basically a component of the vacuum energy present at the atom, which is that's many orders of magnitude more than the vacuum energy that's present in completely empty space.
Yeah, that's, as I say, it's an initial paper. I do take on what you're saying, but I'm trying to deal with empty space.
Okay.
Yes, but I will take that point on too.
that's one of the reasons why in it, like the fine structure constant present in atoms predicts a much larger vacuum energy, because part of that vacuum energy is the particle itself at that point in space, or at that location.
So you're talking about the self energy, the self energy that would result if you integrate it down to zero. So the field,
so
the electron acting on itself.
So they were predicting a vacuum energy based on I believe it was spectral line splitting in atoms, and you can't predict, you can't ignore the energy, the mass energy or the self energy of the actual particle at that location when calculating the vacuum energy at that location.
So you're talking both the Lamb shift and you're talking about renormalization as well, aren't you?
I think so.
Yeah.
Something along those lines, yeah.
Yeah, the Lamb shift would be from the perturbation of the surrounding 0-point field.
I think
the embarrassing problem in QED is the renormalization, is getting rid of infinities. Yeah. Yeah, I'll take that on board. I'll have a think of that. Let's say it's what they call an ansatz. It's the initial sort of when you put your work piece on the tool, on the anvil.
You may be able to get away with a second order term or something that way.
Yeah, yeah.
Yeah. Well, Remy, thank you very much for sharing that with us. I sincerely appreciate it. And I feel guilty about pressuring you for the camera. That's just kind of been our policy. So, but
I've got the light in strategically, so you can't see my stubble when you can't see the.
You look rugged with stubble. See, that's better than me. I just look homeless when I don't shave. You look rugged, so you have nothing to feel guilty about.
I'm going to switch it off now.
Okay.
Okay then.
Okay. Well, so why don't we do this? Let's everyone please put your hands together for Remy Cornwall. And that was a great presentation on ONSATs. And so let's go into open discussion now. So basically what I'll do is anyone who wants to unmute themselves, and I guess we'll just try not to talk over each other too much, but anyone who has anything to share, or it looks like Mr. Kenneth Griggs is still with us. If anyone has questions or anything along those lines.
Yes, I have a question for Ken Griff. And my question is on your slide, number 45, you were talking about the commutator differential. I'm interested about the orthogonal symmetry. Can you explain a little bit more about it? Your slide is on number page 45 when you were giving the lecture.
Sorry about that. Can you hear me now?
The commutator differential on
Okay.
the orthogonal part. Can you?
Yep, let me get to that.
Number 45.
Give me 1 second.
You have A, the symmetry, and C, that would be the orthogonal.
Almost there. Okay, come on. There we go. Okay. 45 and okay. So try me one more time. What's your question? Sorry. Oh, there we go. Okay. Yeah. Okay. So the orthogonal matrix that we're talking about here is the matrix that we're normally associating with the transformation matrix. It's what takes you from one of our graphs and how that matrix actually transforms into a new graph or into a new matrix. And so the general two types of matrices that are used in Kaufman's differential calculus fall under those two rubrics. One being a symmetric matrix, which in Phoenix is a matrix describing space, and the other being an orthogonal matrix, which is a matrix describing time or evolution. Did I answer your question, or?
You spoke earlier about the representation of time being its own independent.
That's right.
From
That's
the
right.
other. Normally, Einsteinian, 4-dimension, Toulouse, 5-dimension. The reason I'm interested on that one to know, where can I find more information about your theory, the mathematical theory, because I need to read in more detail.
Okay, so the best source right now is Louis Kaufman's papers, and I've actually referenced them in this paper. Let me find one of the references.
You can put it there on the chat. So the reason is because I have a machine. I'm producing, a 3-dimensional, the way to represent it, the thrust effect I'm producing. I found out that 5 axis, 5-dimensional, like Calusa, fits like a glove.
Okay.
I have the 2 axes are producing orthogonal Lorentz forces, and the other one axis I'm producing a magnetically induced gyroscopic force. I can whether the machine, the rotor is in the vertical or the horizontal position or in between, and then I have the orthogonal effect would be an axis that is reactionary. I represent the reactionary axis, which is orthogonal to all 4 axes, time and the XYZ dimension. And so I've been working on that problem represented in mathematical space. And you mentioned about how the time may be independent. So I'm interested in exploring that more because I want to make I want to publish very soon, and I want to make sure I have an accurate representation with the data and everything I need to do. But it seems to be like that. It's like a glove, and when you mention the orthogonal and the symmetry, yeah, I need to look more into it. So, because I think that will work into my research on what I'm doing, that I can take my data and show it. And
fantastic.
The mathematical structure that will fit it, will describe it well.
Okay. Guys, sorry, I have a family emergency that I have to attend to, but we are in an open session, so I'll just leave it going if that's okay.
Hey, Tim, I share screen.
Sure. Yeah, I would say go for it, and I actually have to run out the door. My wife's car just broke down, so.
Oh my goodness.
Yeah.
Well, God bless you, Tim.
Oh, okay. I'll just leave it up and going, and it's still recording, but no worries at all. So.
Okay. Thank you, Tim. We'll pray for you.
Okay. Thank you, Tim.
So, and I wanted to share something.
Sure. Can you hear me? I can.
Oh, I see. It's my bad. I got the thing minimized. Okay, here we go.
Okay.
Would you be able, Mr. Greg, could you be able to send me a copy of your theory where I can find it, the lecture that you gave today, and more information on detail?
Yeah, I'd be able to do that.
I will send you my email.
Okay, that's great. Thank you.
Okay, so that you can.
So can you see that on your screen?
I think I have it.
Yeah. In minutes, 2004. It's not moving. This is just a image of the background.
Yeah, okay. Michael, can you talk up a little more?
Okay, sorry.
Sorry about that.
How's that? Better? So basically what we have here is the Tic Tac.
Yes.
And this is the infrared imager. And I worked for 10 years for Hughes making images. And so what you see here is above the Tic Tac, there's a dark region. It's like a balloon.
See that there?
Yes.
And if you look at it, it's rotating counterclockwise. You watch closely. Okay, and then over here on the right, there's this like bright region, another little like balloon bright region. And then over below it, there's another region which is like looks like it's going both ways.
Yep.
And then right next to it, there's another little region, and this is looks like it's spinning, but part dark. And what the color differential is the white area where the tic tac is in the center. That's hot. The dark areas are colder.
Very right.
Okay, so these are thermal effects, but they're due to the engineering of the space-time there by the tic tac. Now over here on the left, see this like undulating area here?
Yes.
Okay, that's where your wormhole is.
Huh.
Okay, now watch. I'm going to go to this. These frames are included with the. Hold on a second. My screen down here. So I can put the right. Oh, there it is. Okay.
Yeah. Okay.
Oh, got the wrong one again. There we go. See this one now? So now what it looks like is going on here is think of it like a bow and arrow. Okay, you pull the string of the bow.
Right.
That's on the right side here. And when it releases, that's your ward. And the tic tac is the arrow.
Exactly.
And now notice how the tic tac right before it disappears is like all stretched out. Now, how Puthoff's hypothesis is that the region on the left is expanded space-time.
Yes.
Where basically time is faster there. So, I mean, you can go superluminal in expanded space-time. But it's not superluminal to the person in experience.
That's right.
Okay, so they're not experiencing any of the G-forces. They're
Any of the G-forces or the time dilation or
just
right.
the observer. Now on the right region, where that's the denser space time, and that's basically like if you get closer to a star, basically time slows.
That's right.
Near a black hole's event horizon, time basically stops. So now that's this is basically quantum gravity in application.
Yeah.
Correct?
Yeah, I mean, it's what we would expect if we were looking at a gravity wave for which we have, part of the gravity wave, which is compressing space, and the, maybe the forward part or the aft part of the gravity wave, which is relaxing space. But yeah.
So basically, what I discovered. Let's see if I can. Okay, so can you see this signal I have here? Okay.
Can you hear me?
Yeah, I can hear you. Can you hear me okay?
I got cut off there for a second.
Okay, so what what I have is what I used to work in the heart. This is a signal. This is a nanogravity signal from a pump on a spinning disk. And what I'm measuring it with is a thing called a GMR sensor. It's a giant magneto resistor. It's the part of the read head on your hard drive. And essentially what happens is when the pump goes under it, the edge of the pump creates a magnetic induction signal. That's what the first signal is here. It's as the rising edge of the pump goes up, it produces, and then that's at the speed of light. And then as the other edge goes under the sensor, the magnetic sensor, it produces this other pulse, the opposite polarity. The gravitational induction signal is in the middle here. See this broad signal? You see how it has the surface noise? That's called the noise signal. So basically, this is an example, and now for a nano pit, I got just the opposite. These little signals are there, but it goes the opposite direction. But essentially, and then what's going on here is as the bump, because the bump is closer to the sensor, the space-time, it treats it as denser space-time. And that's why there's a post signal, because the actual signal, the actual gravitational signal is it starts later than the edge. So it's time delayed. Now, I don't have a pit signal right here, but it does the opposite. It goes up like this, but then there's a pre-signal. So when you go into the future, right, so basically moving matter can, a little bit of it goes into the future. Now the other interesting thing I would like to share is when we're talking about quantum tunneling, I'm going to go off the share. Stuck in the share.
Okay.
Sorry about that. Stop.
There you go.
Sorry, I'm technically failed. So the other thing I was about, you're talking about quantum entanglement, correct? And so when I worked for Hughes back in the 80s and 90s, we worked on these things called tunnel diagrams.
Okay.
And that uses a quantum tunnel. And so basically, what happens there is it's like a barrier problem. And the interesting thing about quantum tunneling is the data that's on the opposite side of the barrier is advanced in time. It goes into the future. So it's not actually simultaneous. It's not actually instantaneous. It's actually post-quantum. Okay. And so, and a lot of folks, when they think of entanglement, they think of it as simultaneous. And this also, I think, applies to your conscience.
Yes.
And how we think. But basically, that's how we actually read the future a little bit every time we have a thought.
Yeah, that's, I think one set of researchers were talking about microtubules and the idea that
Penrose.
Right, exactly, Penrose, exactly, and his other researcher out in at Oxford, I think. But yeah, the idea that that these microtubules are creating these entanglements that enable us to really, for the most part, have little short steps forward and backward in time, such that we're just almost bypassing some level of time to achieve the notion of consciousness. Yes.
Well, so the point, my interest in it is that it means that it could suggest that consciousness doesn't end. That something, basically, it's something embedded in the. It's kind of like Bohm's pilot wave theory. The speaker before, I was going to ask him about that. What he was talking about.
Right.
You think that's what we're talking about with the these like generation functions, essentially?
Well, I certainly think that I'm not certain as much, only because I'd have to investigate it a lot more. But I certainly know that in terms of what generating functions enable us to speak about are all types of measurements, even if those measurements are, flipping through space or as it were, conjoining two moments in time or conjoining two moments in space together. There are still measurable phenomena. We talk about entanglement, but yeah, the idea is that entanglement happens both in space and time. And we have to be able to, and we do in physics already, but to weed out which ones we're really dealing with in those discussions.
That we can actually, with electrons, we can change the temporal relationship. That we can make a entanglement state where the two electrons, one of the electrons doesn't entangle to a future time.
Right.
They don't have to be the same.
That's right.
And
yeah, the beauty about some of the work that we've done is to directly ask the question about whether or not, how is it possible that the future dialogues with the past, right? And, definitely the way that we've been assigned to think about physics is that physics is causal. So there's a past, there's a future, and we're only moving into a future, never having the ability to go backwards, blah, blah, blah. And the reality, and I don't agree with that by any stretch. I think that in
the black hole, if I point you to the black hole, you could perceive that nothing's changed.
That's right.
Right?
All right.
You don't know which way you're going.
That's right. You really don't.
You could be going to the past.
Okay, no, I'm moving into the past, and there's nothing I can do about it.
That's the beauty of it.
That's right. But
just a relationship, right?
That's true. And the thing about having negative energy states, for example, is that at least in terms of the field theoretic equations that we use, which are basically any equations that deal with space and time as actual entities, but those field theoretic equations that we use demonstrate to us that negative energy will begin to unfold our whole notion of causality. And so, when Alcubierre was envisioning using negative energy in order to accomplish, the folding of space such that it could produce a warp, a warp acceleration or a warp field, the reasons why physicists came back at him, it was simply because this way of doing it seems to violate causality, and not certainly respecting the idea that Einstein's GR definitely violates causality. But what they were saying is that if we exclude negative energy states, we got causality back, and everyone should be happy. Which then, of course,
I think the problem with Einstein was he got this award for discovering electric. And basically,
Brownian motion.
And electrons and photons. I like to say he was blinded by the light of electrons, and he missed the holes all around, because that's where the energy is, in all those holes, or protons.
Yeah, I mean, in so many ways, Einstein's fight, obviously, with quantum mechanics obviously it seems to have been disruptive, but of course it wasn't, because he's the one who gave us entanglement. If he hadn't cracked into quantum mechanics as deeply as he did, we would all not have any notion of entanglement in a relevant way today. So I dismiss Einstein in other ways, but in that way he did help us.
Well, I believe Einstein, not because he's Einstein, but because I think that his life was it.
Yeah. This is, for me, it's never about, any notion of hero work.
But that goes back to me thinking God's a she. So.
Yes, exactly. The whole notion of Maleva, right? When I try to describe the 1905 Undergang, a year for Einstein, the main thing that comes to mind is that he was deeply in love with Maleva.
Hold that thought, Ken. Hold that thought, Bernie. That picture there of the chief in is that Utah by any chance?
Yeah.
You know how I know?
How?
Because I studied geoglyphs. I got a paper on the called the Oxide. It's archaeology. And when I was doing Google, I was looking for other features that you could see from where we were, and I came across that. I said, oh, yes, yeah, I think I still got a copy of it somewhere. That's a pretty cool feature, don't you think?
It is awesome.
So if you ever get a chance, check out Kokopili. You know who Kokopili is? Kokopili.
Okay.
The guy with he's playing a flute. And he's got like the wild hair, dude. That's because he's got the head of a bee in the body of a bee. And he's here for light telephone. So if you Google Kokopili geoglyph, you can see him from space.
Wow.
And then right next to him is Lutz.
Sorry, sorry to interject. Someone called Bern Crone, I think, sharing the screen. I think they may inadvertently have shared it, because we've just seen them use Paint 3D in Windows 10.
There, yeah. Sorry. I'm meaning to share it, actually.
Yeah, that's pretty cool, Bernie. I like that.
So I'm trying to create here a geometric dimensional vector or force vector unified field of everything. It has to do with the octave scale, Walter Russell's work, the platonic solids, color, sound, resonance.
This isn't platonic.
Sorry?
You don't live in a platonic world.
Well,
it's not flat.
Well, that's your one-dimensional disk, right? And then you have your two-dimensional, like your polarized rod that from light, electric 1D field on a disk, 2D polarized rod of opposing magnetism.
Oh, it's got gold three-dimensional.
It also includes gravity. That's like your three vector at that point that encloses your volume for the first time, which then creates that 3D sphere. And then your 4D is that sphere connecting to the higher dimension through one more D of time time space, essentially your quantum or your
tetrahedron on the left there.
And then after your 4, it goes to 5 being and 6, 7, 8 with the higher dimensional platonic solids, but it's like trying to comprehend that high of dimensional theory, right?
Yeah, that's cool. Well, you know, the strongest material is a tetrahedron. That's what.
So the way I look at the 1 dimension is like it's a disk. It's like your record. It's a record. It's a page in a book. It's recording all information in that moment of time.
So it's got a stylus. You know what I mean by a stylus? Like a you know, the old diamond stylus on the really good record player had a diamond stylus.
Right, but so like it's a moment of time from the perception of the consciousness or all of the consciousnesses,
that's cool.
And it's recording all information within that localized moment of space-time. And then as you're flipping through the greater space-time through like the solar system moving within the galaxy and whatnot, it's like an 8mm film, or like you're flipping through the pages of a book, and the consciousness is the cartoon that is created in the motion of those flipping between, right?
So Bernie, you got that on a website, or is that just like a presentation?
This is just what I've been working on it. It's in many of my journals for I've been writing on and working on for 10 years, but I haven't published it or put it onto any internet sites or anything.
Yeah, no, I like the whole concept. I think you're totally on something.
Thanks, brother. I appreciate that. And it's like, so I did this during a live stream marathon the other day, just through paint, putting together as many of these references as I can, and then as well as a little bit of my own artwork and stuff. But I got some actual graphic digital design artists that I work with that will actually turn this into something much more coherent and unified in the coming future.
Cool.
Lastly, I just want to point out that the Indian heads there, the one picture in the center right, that is a road going up to an oil derrick, and so it's essentially like on the scale of the Nazca lines and stuff like that. And this is actually in Medicine Hat, Alberta, Canada, only a couple hundred kilometers or less than 150 kilometers away from where I live. And yeah, it's like that right there redefines world history, because who made that in Canada and when? But there's all sorts of hidden mystery.
That's interesting. Why? How? Is it on public land or is it on private land?
Sorry?
Is it on public land or private land?
It's in public, in the Badlands there, in the and so
probably got a permit to drill there.
We'll have to check out the Farnham Research or Farnham Foundation. He's the discoverer of it, and he actually found a system he calls geoglyphs that are megalithic structures within these different sites that plot out and map and connect to every other ancient megalithic site across the world. And it's too much for me to try to describe right now, but it's just mind-blowing and revolutionary. It's crazy. Like, it links like the Bosnian pyramids, the Egyptian pyramids, Yanaguni Islands. All of them are mapped out in this Alberta Canadian room. So
it's on a ley line.
Yeah, oh yeah, it's a major ley line.
Can I ask the question now, please? Can I to Ken, please?
Sorry, 1 sec. Okay, sorry about that. Yes.
Thanks. Great contribution.
Still here? I don't know if he's still here.
What can I do for you, good sir?
You still got your screen on share, yeah?
Yeah, yeah.
That's not me. That's Bernie's got the screen on.
Yeah, yeah.
But I don't see Ken here anymore.
Yeah, he's gone, I think.
Yeah, we're down to 14.
Yeah, who are you looking to ask?
I want to have a word with Ken. I want to have a discussion which might be of general applicability to everybody. Yeah, I just wanted to ask him a question. It's all right. It's all right. You unshare your screen.
Yeah, for sure. Sorry about that.
Yeah, thanks a lot.
Stop share. There we go. Sorry about that.
Okay, I think he's gone. He's gone.
Yeah, looks like it's you, me, Sam.
Yeah. It's 2 o'clock. 2 o'clock in in the UK, so I might be logging off too. Yeah, 2 o'clock now.
I had fun.
Michael, did Mike from Toronto with Faraday Research ever show up today?
I don't know.
Okay, probably not then. Do you mind if I share a video I did the interview with this electrical engineer the other night? He created his own end machine, his own pulse motor, as well as he's now doing a Don Smith generator.
Sure. That's information.
Just about. Is it playing the sound or no?
I can hear you.
But you can't hear the.
If you have the volume turned up.
Mike, is it all right instead if I post the link in the chat and you play it instead?
I can try that if you want.
I muted myself there just to see if it was me that was causing that feedback there, but I guess it wasn't.
It's like 2.5 hours. A lot. Can you hear that okay? All right. Okay, let me go to share. My penalty from autodidactic. I have with me. Bernie, the burner and mind's eye science guy without the bow tie, and Mike from Parallel Research. And we're going to have a bit of a chat today about all things.
What's that? Can you guys see that okay?
Yeah, absolutely.
Basically been doing a lot of experiments on free energy, so we're going to touch on that, and then get a bit of a grounding into what electricity really
Of course, I don't like that kind of stuff. So, welcome, guys. Hello, everyone in the chat, and welcome, Mike and Bernie. Hello, hello. You have the full Bernie. That frees up.
Oh, okay. Hello to all you beautiful souls in YouTube land. Tonight is our part 2 with Mike from Heritage Research.
Maybe put it to like 5 minutes in or something.
First time that we are streaming multiple YouTube channels simultaneously on autodidactic. This is we have a problem that not only is it one scale, we also have a problem with friends. I'm going to put the link. So, this is trying to confirm what I just talked about. And that is smart. So, here's the other. I've been talking about opening up the data. Motor in the generator air goes to high voltage. And then the high voltage transformer goes to the when he started set up in this configuration, this motor here gets wound down so heavy that it starts drawing about 10 amps. Okay, that's a lot of stress on the motor. Then you have a problem that generator. Not only is it wound down, you also have a problem with medicine.
Hey, Bernie, it was kind of boring. Where's the good stuff?
Sorry, gotta skip ahead there. There's a part there where we go over Jared Morin's work, and I'd say that.
Wait, okay. So that you see down in the left here, you can see the screen capture.
Yeah, probably about 45 minutes in or so on it.
Okay.
Oh, we go over Eric Dollard's induction. Eric Dollard's induction generator. Maybe.
What's that, about 40 or here?
That's about 20 minutes. Or
20 minutes.
Yeah, right there.
Okay. Is that Edison?
I believe so. Right at the end of this presentation, or like this little video would be the part to bring up, because then Mike really goes in depth in explaining the induction and stuff. Although if you haven't seen Eric Dollard's most recent upload, yeah, this is pretty good. This is Eric Dollard's most recent work on their cosmic induction generator.
I was able to really move forward when a couple of years back, a lot of people were going up with it. So this is
Have you seen Eric Dollard's?
What's that?
You're familiar with Eric Dollard's work, right? No? Oh my gosh. It's too much to get into right now, so I'd say just like skip to the end of this guy talking when all four of us or three of us come back in, and we'll be able. That's a good part to come in. That's their cosmic induction generator.
Acoustic resonance. What did you say that was called?
So this is possibly transmutation through different frequencies, changing the ionized gas into different plasma elements through what harmonics they're putting through it.
Is that an RF field or is that just electric?
RF, yeah.
Aren't they worried about getting cooked?
Eric, so
multi-screen.
yeah, he's too much to explain myself. Just let a couple minutes of the conversation play here, and Mike's electrical engineering knowledge is quite good.
Sponsored by Sir Shark. There you go. Let's try that again. There. Figuring it out.
So I
there you go.
tonight because I figured it's very relevant with your Don Smith generator as well as what you're talking about with the spark gap generator or spark gap.
Yeah, you're using the same method to create that. So if I build off that, I just have to get different parts. So like the two Tesla coils included each other. And when you take the neon tube or a fluorescent bulb in between the two Tesla coils, there will be area in the middle of that tube that's in the front. That's where the two fields basically collide. They counter space like a theory. So that is kind of the mystery of how that's, what's actually happening there, because basically a black space in between the fields. So that's it's like an energy vacuum almost. Almost like a black hole.
Almost the center of the voting coil. And like Tim Wheeler's carousel there with like the center of the magnetic field. It's also black hole. Yeah, the toroid, like Daniel Newton and the one-stop energy, their resonance coils, like their more advanced rodent coils. And they as well, when they have vortex, like the same black hole in the middle of the interaction. That's the center of it.
It's similar to like, just a regular motor coil. So when you get the back EMF and it collapses, it can only collapse in on itself so far in the center. And that's when it's called a blotched wall. All right? And when it hits the blotched wall, it can't go any further. So what happens is it's actually the opposite direction.
You have an audio cord, auxiliary audio cord plugged in at all? And does anybody have an auxiliary audio cord are you guys having that horrible like static as well in the sound? Here. Maybe it's just mine that's.
So this is more what you think is the voice.
So is it a balance? Someone's going into it, someone else that balance. So is it like
What are we watching here?
Like, is there that horrible for everybody? Like,
Start there. Okay.
I can't hear you. All I can hear is like.
Yeah, I got
Did the evil alien sounds end for everybody else now? Like, Mark, were you hearing that crazy, like?
Yeah, what was that?
I have no idea. It seemed to be coming from Michael's end, though, I guess. That was weird.
Is anyone else still on?
We have Harold here. Harold, you're with us. Is Tim still here? I was showing Mark. Do you know if my buddy Mike from Faraday Research, did he show up in the Zoom at all today or no? I sent him the link. He's very, very. He's a career electrical engineer. He works in the, I think, aerospace industry in Toronto. He does his own 3D printing, but he built his own end machine. He built his own pulse motor, as well as he's now working on a Don Smith over Unity generator. But that's what I was getting Mike to show. There was a little bit of the interview, but for some reason his stream, his stream was glitching right out. Do you mind if I try doing a little bit more of it?
No, not interested.
No. It's glitching right out. Do you mind if I try?
Not interested in that crap at all, actually. Oh my God! I'm sorry, but before I was incapacitated.
Hey, Mark, how's your arsophone experiment going?
Filter shit on this waveguide is filtering out too much of the microwaves. Got to remove it. It's a two-person job, so I'm waiting for an assistant to come in here and give me a hand.
You mentioned that the book is available in Amazon.
Yeah.
Okay. I think I'm going to get that one this week. I was waiting to move to my new location to set down my lab and do everything and start doing experiment again.
Okay, try that out. Get the book and check it out.
Is Glenn a ghost?
Glenn, are you ghosting us?
Is that the only experiment you're working on at the moment? The arsophone?
Well, there's a lot of experiments we're working on.
Oh, okay. Well, that's good.
No, I'm just sitting here writing a patent.
Okay.
So just listening to you guys talk. A couple of guys actually were pretty interesting there at the end.
Oh, you liked my stuff. Thank you, Glenn. Thank you.
What are you working on?
I was talking about the guys who were talking about the Phoenix thing, and one after him it was talking about the energy density. Those two talks were really good. I'm gonna have to relook at them.
I have this guy who keeps contacting me and telling me that somebody on APEC said something similar to his patent and he wants to sue.
Well, anybody can sue about anything. It just has to prove that I've got to be careful with this one because there's the idea came from something that somebody posted somewhere else. I just have to write it in a different manner.
Yeah, I think the whole concept of intellectual property, when taken down to that level, is
Who
is
wanted
very
to
long.
sue?
Because this
Like,
stuff really comes from the Akashic records. I mean, if you meditate hard enough, you can find these discoveries that have already been discovered.
yes, Mark, absolutely. Like,
I'm talking to Glenn, Bernie.
I'm just saying in general, though. Like, you're bang
Is there a
on.
way to mute him?
Yeah, if it's been published, they won't patent it. If they know it's been published. That's the way you have to find some kind of what they call parent claim that has never been claimed before. It doesn't matter. Even if something's been published, if some unique aspect of it hasn't been talked about, you can still write a claim. And that's the key. And what a lot of these people who submit patents don't realize is if they leave out a key claim out of their patent, somebody can literally rewrite their patent almost word for word and resubmit it, and they'll have to pay that person royalties on their own patent. That's the reason a lot of people don't like. That's the reason why a lot of people say somebody stole their patent. Yeah, they stole your patent, but legally. You know, so you got to be careful there. A lot of people don't want to do patents nowadays because of that, because there are companies out there that the way they make money is stealing people's claims and trying to make them pay money. I've had people send me letters on my patents. I just throw them away.
Oh, did you ever have anyone chase after you for real, like actual file?
No. No, I'm pretty sure somebody's probably stole some of my ideas somewhere in the world, but there's nothing. In fact, I don't care.
But like I said, they're not your ideas. They come from the Akashic records and they've already been invented.
Yeah.
Nothing. We're not inventing anything new here.
That's a patents are a human thing, not a universe thing. Yeah, everything we do today probably has already been done someplace in the universe, but it's only been patented here on this earth because we only know about what's on this earth. So, kind of saying that is.
I think the value comes to the person who actually makes something happen, who actually build it. That's where the credit goes, and that's where.
I would prefer the credit over the darn patent royalties. You know, if you want to steal my patents, go ahead, but make sure you put my name on it when you steal it. And I was also going to ask if any of you guys were looking for some patents to license, because I've got several of them I'd like to get out there.
I don't know. I'm sure that anything that we would try and build, even if it was completely, designed here in the lab and nobody read any of these patents, somebody probably has patented it already. Anything that we would design.
I've been surprised that a lot of my ideas I submit have been patented, but I've also been surprised that the patent office are actually a bunch of, my opinion, I don't want to call them idiots, but they tend to be such that they just go out and almost sometimes and find anything and send to you to scare you so you don't go any further. And my process has been is I get it, I read the letter, I get scared, I put it down for a week or two, I get it back, I reread it and say, no, they're stupid. And then I write back and tell them how they're wrong. And everyone I've done that way has went through the patent office. As long as you can write back to them against what they said in a pretty reasonable manner, it seems to go through, regardless of what it is.
Yeah, I mean, I like Elon Musk's attitude toward it. He just files patents so that the patent trolls don't trace him.
Trace to him or what?
Chase him so that the patent trolls don't come after him, just to protect himself.
I don't know how he does that, but it's all about the claims. If you have to really pay attention that you've claimed everything, because like I said, if you miss one claim and these patent trolls decide that it's a parent claim, but plus they have to have the patent. They can't just send you a letter and say you got your idea without proving it to you. That's where you have to throw them away. If I never get another one, that means they were just trying to get money out of me, trying to scam me.
Yeah, and this other guy keeps sending me emails he just emails everyone in the world and hopes to get a response, filing motions and shit.
Unless you get
I mean, I'm
lawyer-
not even building anything. Like,
unless you get a letter straight from a lawyer's office that you can actually call and talk to, it's meaningless. You can send you letters and call you all day long. I've had people who've called me and complained about stuff, and it's like, I'd say, okay, good, do something. I never hear back from them.
Well, once we actually start building actual hardware, that's when we're going to need to hire a lawyer to dingle out all that shit.
Yeah, I don't know how anybody can say you're doing the same thing you're doing if all you're doing is building stuff based upon what you've read. Because that's open literature, free to anybody, and you can do anything you want to with what's in open literature. You can actually do anything you want to every patent that's out there patented, as long as you don't make money off of it. It's when you make money.
We plan on making money off of it.
Yeah. They can, if you're taking their patent, building it and shorting it online like this, they could probably get a court order to stop you. But if you find something online and you think, on a patent, you think it's cool, you build it and use it at home, there's nothing they can really do about that.
What if you never saw their patent and you're just building it and it looks similar?
If that's the case and you try to patent and make money off of it and they find out, yeah, they could go after you.
And what could they do already?
If they have a patent, what they would do is they should get a lawyer to have you stop and cease.
Cease and desist, yeah.
Yeah, they can't just come right out and sue you. If you stop, then there's really what
can they force you to pay them royalties, and how much is that?
They can't force you to pay royalties unless you're making money.
Yeah, if you are making money.
If you are making money and they can go take it to court and prove that you've stolen their ideas, yeah, they can make you pay.
How could they prove that I stole their ideas and didn't just come up with it on my own?
Well, if they have a patent that predates what you're doing, and the patent rights are still in place.
So then they don't have to prove that I saw their patent and stole it. They just have a right to the idea?
Yeah, if they've already patented, yeah.
Oh, so they have a right to an idea. Okay. Well, one thing that's interesting is the pious patents are exactly how I would build a craft, and they're very generalized as well. So I don't know.
Yeah, there's too much information left out of the pious patents, and some of it doesn't make sense. And one good piece of it that don't make sense is this high voltage thing he puts on there. If you're going to put those high voltages at the frequencies that he's talking about on it, the air will catch fire around your craft, and you won't have a propulsion unless you asymmetry having it catch fire on one side versus the other. Because they sell gigahertz Tesla coils on eBay that literally have a flame like a candle. And Pyrus is talking about terahertz, basically, even higher than that. You will catch the air on fire at very high frequencies, and technically, then what you basically have built is just a balloon. You just a buoyancy.
He's talking about a waveguide, a craft that has a waveguide in its hull that creates inertial mass cancellation.
But he has these very high voltage devices that, what do you call?
Well, that's in a different patent, probably.
No, he has it on his device, and it's at every corner of the device.
Hmm.
And the way it talks, that he is electrifying the surface.
How specific does the copy have to be? If you change one tiny thing, does it no longer?
If you can come up with a parent claim that's different from their patents, then you can patent it. It's just got to be a parent claim, not a dependent claim or a child claim, what they would call.
What do you mean by parent?
The parent claim is basically has to be there to make it work. And a child claim is like where you built a circuit and you can replace a piece of it either with a transistor or a MOSFET or something like that. Those are child claims. It's just something you can put in there that it
Well, you
still
need
works.
the microwaves and the homogeneous magnetic field for it to work.
Yeah. The parent
But-
claims basically have to be there to make it work. And if if somebody has written a patent that uses everything that you're using, but you've used one extra thing in there, that can change the patent too, change the parent claim.
Okay, what if you just go and build it in China?
Then you can have the Chinese steal it. They steal patents all the time.
Yeah.
You wouldn't be able to sell it in the United States and maybe some other countries that have patent agreements with the United States. But the rest of the world, you could sell it to.
I know that's just like a legal quagmire that we're probably going to fall into at some point. And I think by the time we fall into it, countries will start looking at this technology differently, and countries will start looking at themselves differently, because it will bring about, extraterrestrial contact or open contact with ET.
You need to go out there on some of the open sources and start looking through the patents and see if you can find it. But sometimes these things are really, really hard to find, basically because they name them differently. It's like the homopolar generator is really a Faraday generator, which has been in physics books since the early 1900s or maybe the late 1800s. And the military changed the name to homopolar generator. And if you try to look up Faraday generators, you won't find the homopolars until you type in homopolar. So they're hard to find, is what I'm saying. But if somebody has contacted you and said you're stealing their patented idea, ask them to send you the patent so you can look at it. And then you can read the patent and decide whether what they're saying is
Oh,
true.
they're not saying that I'm stealing their idea. They're saying that they filed a patent pending and somebody on APEC spoke about it, and it's really their idea. And therefore it's my fault and I should pay him.
Well, if you didn't see his patent pending, there's what proof does he have you saw it? Did you go to the patent office and get it?
No.
I don't know how he has, like I said, I don't think he can really do is have his lawyer send you a letter to.
He doesn't have a lawyer. He does everything pro se.
Yeah, well, as long as you don't have a court degree to tell you to stop talking, you can talk as much as you want to. Now, if he has a large company and he's making money off of this stuff, and what you're saying is detrimental to him making a profit, he could probably sue you, but it doesn't sound like that's the case.
What happened with the Wright brothers where they got a patent on wing warping, which is like basically ailerons?
Yeah.
Would something like that still stand? Or have they changed patent laws?
Patents are all about the claims. And claims can be written differently and still mean the same thing, but you'll have to get a lawyer involved sometime for that. But if they don't send you a court order telling you to stop talking about it or stop doing what you're doing about it, then I would just keep doing it and ignore them.
Yeah, I'm sure I will receive one of those one day. So I have to think about how to attack that problem. Can they get a court order to cease and desist for like a company that has 1,000 employees or something like that? Tell them to stop manufacturing whatever they're manufacturing.
If they can prove to a lawyer that you're still in their idea, then he can get a court order.
He can get a court order without us being represented.
Yeah, the lawyer has to present the evidence to the court.
And there's no defense. There's no defense for the cease and desist.
No, they just have to prove that, if they got the videos from the APC and they took it to a judge and they could prove to the judge that was their idea, then the judge can agree and send you a court order. But until that happens,
and we don't get notified before that happens to defend ourselves.
No, you wouldn't. You'd have to defend yourself after the fact. Then you go get your own lawyer.
According to what I read, on the patent book is that.
And if we get any damages from that false claim, can we then countersue them for 1,000 people being out of work for a week?
You can sue anybody for anything you want to, whether you make money or not. I can't tell you that. It's
I
all
guess
up
that's
to
true.
how good your lawyer is and how bad the judge was or how drunk he was the day he was in court. It's just there's a case where a ladder company got sued because a farmer went out on a cold day, put one leg of the ladder on some cow poop, and then the next day it warmed up and he went out there and got on the same ladder in the same place and the ladder slipped. He sued the company because they didn't tell him he couldn't put it on cow shit and won. There's been cases where people have poured Coke on the floor and got up and slipped and sued the owner of the store when they're the one that poured it on the floor because they were saying their workers weren't fast enough to clean it up. So you can be sued for anything.
That's true. But you don't need an excuse to sue.
You don't need an excuse to sue, but you don't have to stop and insist until you get a court order. And the only way they can sue you for money is if you harmed them in some way because of it.
Or if they harm me. All right, wonderful. I'd rather not even think about this shit because it doesn't really help you in your day to day.
Yeah, it's a big pain in the butt when people start doing that. I wrote a patent and got it through the patent office at NASA, and somebody sent me an email and said, we've been doing this for years. And it's like, and my response was, well, that's good. I got the patent. And I never heard from them again. I never made any money off of it. So, well, it was NASA.
Have you ever made any money off of any patent?
No, but I haven't pursued the patents. I had an IP guy to look at the beginning of the year, but he hasn't had any luck. So you really have to go with them to these places with a demo. And that's a lot of time and a lot of money. And this COVID thing, I was going to do that after I retired, but then COVID hit. So, and now I don't.
A demo of your patent?
Yeah. I typically don't patent anything unless I've demoed it first, made a demo of it.
Mm-hmm.
The only time I've ever submitted patents that I didn't demo was if all the technologies that make it up have already been proven.
Okay, here's an interesting conversation we should probably have one day here at APEC. An extraterrestrial meets, Joe Schmo in the 1950s and hands over all this technology, and then Joe Schmo goes and files a patent. Does that patent really belong to him if it was prior art?
Only if the alien wants to sue him.
No, but if Joe Schmo wants to sue somebody else, can the other person claim prior art because it came from the alien? This is a relevant question that will come up one day.
Well, if the alien becomes a legal U.S. citizen, you could say yes. But as long as he's not recognized as a human being on this earth, the answer would be
he's not
no.
a human being of this earth, and the IP came from extraterrestrials.
If the IP came from something that doesn't belong to basically this country or the space, you could probably take it. But the U.S. tends to not steal from other countries. Or they probably do, but you don't hear about it.
One question is, as far as I know, only the inventor, the originator of the idea, can apply for a patent. Anybody else is a liar. I mean,
that happens. There was a farmer who actually invented the first computer in the United States, and it was a mechanical computer. He did it in his barn. He knew this professor from some university on the East Coast that he had him come over and look at it, but the professor took that idea and went and patented it at the patent office. And the only reason why you don't hear about the lawsuit the lawsuit ended with the farmer winning, but the only reason you've never heard about it is this lawsuit ended at about the same time Nixon was being thrown out of presidency. So he was the big news, not this computer thing. And the other story is that the Bell Labs has always been They always say Bell Labs invented the transistor, but they're wrong. When Bell Labs went to patent the transistor, they found out that some guy had patented like 19 years earlier. And so they went back and invented the other one. You know, there's a PNP and an NPN type. When Bell Lab went to do it, they did one of those types which had been patented, and so they invented the other one and patented it. So they're not really the guys who invented the transistor or the first transistor. But the first transistor that was patented 19 years older was, you know, something like a brick instead of the little small ones that Bell Lab did.
One question. I mean, I hear those books, Colonel Corso, saying that actually he gave Alien gave him the secret of the transistor, and he went and gave it to Bell Labs. So Bell Labs never invented a transistor. What about those assertions? I mean, it's been
until that alien comes and talks to me, I won't believe that. In fact, when an alien comes back and gets me and takes me back home, then I'll just forget about this world anyway.
Yeah, but the book of Colonel
where's home?
Sold a lot of millions of books, and people bought it.
I prefer not to believe in any of the alien UFO stuff, not because it might not be true, but because it doesn't affect my daily life or anything I do. When it starts affecting that, then I'll start believing.
That's a good philosophy.
It's affecting my life in many, many ways.
If it's affecting your life, believe it, but it doesn't affect mine any. You know, people have asked me about UFOs, and I said I don't care about them. You know, but if one landed in my backyard, I'd steal it.
Yeah, I mean, there's a couple issues with patents. There's the prior art concept. Then there's the there's also a defense that it was obvious that it was. I think that's a defense.
I get around that pretty easily a lot of times. Like the patent office has sent me something, and kind of hint that it was prior art or done by somebody else, and give me a patent or something, and I argue back against it that it wasn't obvious. If it had been obvious, it would already been patented. And they buy it. So.
Mm-hmm. No. But one of the things I read about patent is that the law allows anybody to take any patent from the patent office and build one device for themselves as long as they don't sell it. When they start selling, that's when they get in trouble. But to build it for themselves, and that may be your case, Mark, in which if you are doing somebody else's invention, I mean, hey, the person cannot sue you. You know, only when you start making money. If he
I mean that is the plan. We want to make money.
Yeah, but that's what I said earlier too to Mark. But also, if you're doing something online, like we're doing this, and somebody claims they have a patent on what you're talking about, and what you're talking about might harm them making money down the road, then they might can sue you for that reason too. So if somebody says that you're talking about their idea, then you need to ask them to send the patent to you so you can look at it, so you can decide if it is, and tell them that if what I'm doing is in your patent, then we'll stop doing it online. But it's on the person that contacts you to prove that what you're doing is his idea that's been patented, not you. If you don't have anything that says that he did it, then why would you even listen to him?
Yeah, the real issue is like the Salvador Pais patents. When you have patents that are made by somebody who had insider knowledge and extraterrestrial contacts and stuff, well, can't really say that it was his idea.
I wrote an analysis of his patents, and to me, it's just basically a pile of crap.
Okay, but let's say it's not a pile of crap. Let's say that actually happens. So there is somebody who comes forth with an idea that was not his originally, how do you handle that situation? Can he go ahead and sue for intellectual property rights when it wasn't his intellectual property to begin with?
If you can get if he takes you to court and you can prove that it wasn't, then he can't get it. Yeah, if it's somebody else, if you can prove it's somebody else's, then you can sue him for libel.
Yeah, that would be.
These trolls are all about scaring you.
I know.
Like they want you to give them money. And if that's the case, like I said, the first thing you need to do is say, hey, send me your patent so I can read it. And
no, another trick I have with them, if they're like really like they go down the blackmail route, I say no problem. I'll give you all the money you want. Give me your bank account number and your address. And then then when they hand that over, I'm like, okay, I'm going to turn this over to the FBI.
Well, if they call
I've actually done that before.
Just tell them to contact your lawyer. Ask them for their address and say, I'll have my lawyer contact you.
The address and your bank account number. Social Security, credit card, please.
The first time somebody does that with them, you should just say, oh, okay, we'll see you, bye. And then if he calls you back again, you ask him, says, well, if you think I've stolen your idea, please send me your patent so I can review it. Or say so I can have my lawyer review it. I always stole your lawyer in there. That scares them. They think you're going to get the law in there, they'll run away. But like I said,
one of the formative books that I've read was from the Wright brothers. They actually got their patent on wing warping, and really all a patent was in those days, at least, was a license to sue, because very few patent battles actually end up with a verdict, because you have to have a judge who fully understands the patent and understands whether there was infringed. They're very lengthy, expensive affairs, and they were suing Curtiss, who wanted to build airplanes, and it basically destroyed the entire American airplane business, because nobody could build airplanes because the Wright brothers were out and suing everyone for wing warping.
It's all about money, but if you have a lot of money to waste and you want to sue everybody, that's fine. But if somebody,
it ended it at World War I when the Army basically brought in both parties and said, here's your settlement, sign it and go build us airplanes.
Yeah. But back then it was a lot easier to steal people's patents than it is today. But like I said, they still have to, if they can't send you a patent to show that you're taking their idea, then they're full of shit. And if their patent is from another country and hasn't been filed in the United States, they're still full of shit. Unless the U.S. has a patent agreement with them, which we do with some countries. Germany may be one of them. But they've got to send you the patent to prove.
I understand that. I'm just like thinking of the legal quagmire of building, going into manufacturing stages with this kind of technology. I guess that's probably years away from now, but still, there's going to be parasites who are going to jump at any opportunity to try and sue you.
I'm sure every company that's went into business has had parasites go after them, and that's why they have lawyers. Don't contact me, contact my lawyer. That usually will take most of these quagmires away.
Yeah, but what if they're, what if they have a legitimate claim that they patented something and our idea looked identical to it? It was inadvertent and yada yada yada. What do they actually get out of it? Is there a limit to the royalties they can ask for?
The royalties you got the patent is between the inventor and whoever's paying the royalties. They sign a license agreement.
Okay, so
much is based upon how much they agreed to. In my understanding, in today's market, 5% is pretty norm.
5% of what?
The royalties.
5% of what?
Well, if you have an idea and you license it to a company for 5%.
5% of what?
They make 5% in profit, then make $10 million in profit, you get 5% of that $10 million. A lot of inventors don't realize that that companies won't pay much for royalties on your patent.
Well, what if there's 17 patents that are claimed against the device? 5% of all those means you make nothing.
Yeah, probably so. A lot of inventors don't realize that they will not get very much out of own royalties out of their patents, and that's the reason why a lot of people don't ever get their patents as made, because they think they own 100% of it and you get 100% of the royalties. It's not. These companies are taking a chance that they can make money on you, and so they want to get the higher return. Capital investors.
There's a reason why you didn't mass manufacture the device in the first place.
That's the reason why when you write one of these license agreements with a company, you write into the license agreements that they have to pay you X many dollars a year. That kind of forces them to make the device. Otherwise, they're just paying you money for nothing.
Mm-hmm.
And that's actually one mistake a lot of vendors don't do. Is a company will take their idea, never make it, and they never make a dime. They sit there with it and let the license expire before they make it. So that's the reason when you write a license agreement, make sure you write into there that they pay you X amount of money a year for at least so many years until the license expires, until the patent expires. So at least you made something. You can also write in it if they haven't produced it, made it within a certain many years, then the license agreement is null and void too. So it's all about the license agreement. But if you want to make more money, from your invention, then build a company around it. And that way you own, say maybe you own 50% of the company patent, so you may get 5% or less out of the patent, but you get 50% out of the company. So you make more money that way.
Yeah, I'm sure any device that we build or any of these spacecraft over here will have many, many patents involved with it.
If you can build an alien, if you can build, I don't want to say alien, if you can build a spacecraft that could leave this, not only leave this Earth, but leave this solar system, you will be a billionaire, guaranteed. You will.
Yeah, I think minimum wage workers will be billionaires one day. That's another issue when it's $1 million an egg.
Yeah. But yeah.
But in today's dollars, yes, you'll definitely be a billionaire.
I've been telling people for years that if you could invent the next propulsion system that doesn't expel mass out back, you will own the space industry.
Oh, didn't Boeing already do that with their gyroscope devices?
That's only works real well in space. It won't take you off this Earth.
It won't take off, yeah, but it works.
It works in space. I'm actually surprised NASA hasn't built spacecrafts around that device, because they've been building those since the 70s.
They are pretty freaking heavy. We're actually planning on building one over here in the lab.
But one question is that the gyroscope only works here on two principles. One, an external force, they resist it. The other one, in the presence of gravity, like the gyroscope, when it is spinning vertical, it would produce a force, at an angle 90 degrees from the bottom. Let's say spinning
it produces a linear
Why
thrust.
So it would depend only on gravity. So power into space will not produce anything.
Have to have two of them, and really I don't know. Go look at Mike Gamble's presentations. He'll tell you why they work. I don't want to tell you how they work.
Yeah, you need two gyroscopes, and they need to be spinning on more than one axis, in opposite
gravity
together.
Well, but you still need gravity or an external force.
It's not related to gravity. No, it doesn't need gravity.
Well, one need gravity, the other one an external force, because, like, for example, at sea, the gyroscope on a ship, they respond to an external force, like the wave moving, and they react to it. When the vertical gyroscope,
the external force is the rest of the universe.
Gravity.
Go watch Mike Gamble's presentations, and you don't have to argue about this.
Yeah, go watch Mike Gamble's presentation.
Yeah, that's true. I've seen Mike Gamble, because I've been doing experiment with gyroscope, and I found a way to, how to make a.
This. There's a 4 gyroscope system.
Yeah, I've seen it. It's a cool one.
I'm going to bring this to Tesla Tech, by the way, and put it on a table with balls, with ping pong balls as bearings, and you'll be able to remote control it and play with it.
I heard that
to go up.
Tim's going to do his presentations.
Who's doing presentations?
Tim said he was doing the presentations at the Tesla Tech.
Oh yeah, we're going to be there, and
I'll be there too.
Yeah, exciting. When are you coming in?
Oh, I think I'll be there the 11th. Probably sometime before 3.
Oh, nice. Okay.
Can you make your gyroscope produce a force upward that will be higher thrust-to-weight ratio? What is the thrust-to-weight ratio right now?
The thrust-to-weight ratio on these devices is between 5 and 10% at best.
In the presence of gravity, the force is always 90 degrees perpendicular to the gravity vector.
No, it isn't. It's whatever direction you're facing it in, but it's the thrust-to-weight ratio topped out at around 7 or 8%. So it's not taking off, but it is a propellantless thrust. Now they should be using it on like the New Horizons spacecraft, or any of these spacecraft that are visiting, moving around in space. I would expect them to have gyroscopes instead of thrusters.
I think it would make a good device to put on the nose of your spacecraft to actually turn it, make it turn directions more than it would be a good thruster. But as long as it's giving out thrust, if you're in a weightless environment, its weight doesn't matter anymore. You're still going to accelerate it.
Yep, that's true.
But when you get in the gravity well, that's a different story.
Yeah, exactly. But if you make the craft weightless, then with dynamic nuclear orientation, suddenly it will.
Yeah, just a few millinewtons of force will get you going up after 1 million years to the speed of light after a long time.
I think at 1G you'll reach the speed of light in just a couple of days.
Yeah, couldn't tell you. I haven't done the math.
I read that somewhere. You could do the math pretty easily.
But yeah, you don't need a lot of force once you're in space. Once you're out of the gravity well in space, if you're still close to the Earth, you're still in trouble. But once you get out, far from any big masses, get outside our solar system, then yeah, you're fine.
The gravity at the International Space Station is about 0.9 something of the gravity here on the planet.
Yeah,
it's actually the centrifugal force is what's keeping it up there.
Yeah.
Centrifugal force.
So somebody is calling you about that Alphon stuff. Is that what I'm understanding, or is it something else?
No, it's not about the Amy sent me a cease and desist for talking about the Alphon stuff. That happened at Estes Park.
Are we still online? Are you still being recorded? I'm not going to talk about Amy. We're being recorded.
Being recorded.